Section 1 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. The Elements of Geology by William Harmon Norton. Preface and Introductory Note. Geology is a science of such rapid growth that no apology is expected when from time to time a new textbook is added to those already in the field. The present work, however, is the outcome of the need of a textbook of very simple outline, in which causes and their consequences should be knit together as closely as possible, a need long felt by the author in his teaching, and perhaps by other teachers also. The author has ventured, therefore, to depart from the common usage which subdivides geology into a number of departments: dynamical, structural, physiographic, and historical, and to treat in immediate connection with each geological process the landforms and the rock structures which it has produced. It is hoped that the facts of geology and the inferences drawn from them have been so presented as to afford an efficient discipline in inductive reasoning. Typical examples have been used to introduce many topics, and it has been the author's aim to give due proportion to both the wide generalizations of our science and to the concrete facts on which they rest. There have been added a number of practical exercises, such as the author has used for several years in the classroom. These are not made so numerous as to displace the problems which no doubt many teachers prefer to have their pupils solve impromptu during the recitation, but may, it is hoped, suggest their use. In historical geology, a broad view is given of the development of the North American continent and the evolution of life upon the planet. Only the leading types of plants and animals are mentioned, and special attention is given to those which mark the lines of descent of forms now living. By omitting much technical detail of a mineralogical and paleontological nature, and by confining the field of view almost wholly to our own continent, space has been obtained to give to what are deemed for beginners the essentials of the science a fuller treatment than perhaps is common. It is assumed that field work will be introduced with the commencement of the study. The common rocks are therefore briefly described in the opening chapters. The drift also receives early mention, and teachers in the northern states who begin geology in the fall may prefer to take up the chapter on the Pleistocene immediately after the chapter on glaciers. Simple diagrams have been used freely, not only because they are often clearer than any verbal statement, but also because they readily lend themselves to reproduction on the blackboard by the pupil. The text will suggest others which the pupil may invent. It is hoped that the photographic views may also be used for exercises in the classroom. The generous aid of many friends is recognized with special pleasure. To Professor W. M. Davis of Harvard University there is owing a large obligation for the broad conceptions and luminous statements of geologic facts and principles with which he has enriched the literature of our science, and for his stimulating influence in education. It is hoped that both in subject matter and in method the book itself makes evident this debt. But besides a general obligation shared by geologists everywhere, and in varying degrees by perhaps all authors of recent American textbooks in earth science, there is owing a debt direct and personal. The plan of the book, with its use of problems and treatment of landforms and rock structures in immediate connection with the processes which produce them, was submitted to Professor Davis, and, receiving his approval, was carried into effect, although without the sanction of precedent at the time. Professor Davis also kindly consented to read the manuscript throughout, and his many helpful criticisms and suggestions are acknowledged with sincere gratitude. Parts of the manuscript have been reviewed by Dr. Samuel Calvin and Dr. Frank M. Wilder of the State University of Iowa, Dr. S. W. Bayer of the Iowa College of Agriculture and Mechanic Arts, Dr. U. S. Grant of Northwestern University, Professor J. A. Udden of Augustana College, Illinois, Dr. C. H. Gordon of the New Mexico State School of Mines, Principal Maurice Ricker of the High School, Burlington, Iowa, and the following former students of the author who are engaged in the earth sciences: Dr. W. C. Alden of the United States Geological Survey and the University of Chicago. Mr. Joseph Sniffen, instructor in the Academy of the University of Chicago, Morgan Park. Professor Martin Irons, Fort Worth University, Texas. Professor A. M. Jane, Dakota University. Professor G. H. Bretnall, Monmouth College, Illinois. Professor Howard E. Simpson, Colby College, Maine. Mr. E. J. Cable, instructor in the Iowa State Normal College. Principal C. C. Gray of the High School, Fargo, North Dakota. And Mr. Charles Persons of the High School, Hannibal, Missouri. A large number of the diagrams of the book were drawn by Mr. W. W. White of the Art School of Cornell College. To all these friends, and to the many who have kindly supplied the illustrations of the text, whose names are mentioned in an appended list, the writer returns his heartfelt thanks. William Harmon Norton, Cornell College, Mount Vernon, Iowa, July, 1905. Introductory Note. During the preparation of this book, Professor Norton has frequently discussed its plan with me by correspondence, and we have considered together the matters of scope, arrangement, and presentation. As to the scope, the needs of the young student and not of the expert have been our guide. The book is therefore a textbook, not a reference volume. In arrangement, the twofold division of the subject was chosen because of its simplicity and effectiveness. The principles of physical geology come first. The several chapters are arranged in what is believed to be a natural order, appropriate to the greatest part of our country, so that from a simple beginning a logical sequence of topics leads through the whole subject. The historical view of the science comes second, with many specific illustrations of the physical processes previously studied, but now set forth as part of the story of the earth, with its many changes of aspect and its succession of inhabitants. Special attention is here given to North America, and care is taken to avoid overloading with details. With respect to method of presentation, it must not be forgotten that the textbook is only one factor in good teaching, and that in geology, as in other sciences, the teacher, the laboratory, and the local field are other factors, each of which should play an appropriate part. The text suggests observational methods, but it cannot replace observation in field or laboratory. It offers certain exercises, but space cannot be taken to make it a laboratory manual as well as a book for study. It explains many problems, but its statements are necessarily more terse than illustrative descriptions that a good and experienced teacher should supply. Frequent use is made of induction and inference in order that the student may come to see how reasonable a science is geology, and that he may avoid the too common error of thinking that the opinions of authorities are reached by a private road that is closed to him. The further extensions of this method of presentation is urged upon the teacher, so that the young geologist may always learn the evidence that leads to a conclusion, and not only the conclusion itself. W. M. Davis, Harvard University, Cambridge, Massachusetts, July 1905. End of section 1. Section 2 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. The Elements of Geology by William Harmon Norton. Introduction. The Scope and Aim of Geology. Geology deals with the rocks of the earth's crust. It learns from their composition and structure how the rocks were made and how they have been modified. It ascertains how they have been brought to their present places and wrought to their various topographic forms, such as hills and valleys, plains and mountains. It studies the vestiges which the rocks preserve of ancient organisms which once inhabited our planet. Geology is the history of the earth and its inhabitants, as read in the rocks of the earth's crust. To obtain a general idea of the nature and method of our science before beginning its study in detail, we may visit some valley, such as that illustrated in the frontispiece, on whose sides are rocky ledges. Here the rocks lie in horizontal layers. Although only their edges are exposed, we may infer that these layers run into the upland on either side and underlie the entire district. They are part of the foundation of solid rock which everywhere is found beneath the loose materials of the surface. The ledges of the valley of our illustration are of sandstone. Looking closely at the rock, we see that it is composed of myriads of grains of sand cemented together. These grains have been worn and rounded. They are sorted also, those of each layer being about of a size. By some means they have been brought hither from some more ancient source. Surely these grains have had a history before they here found a resting place, a history which we are to learn to read. The successive layers of rock suggest that they were built one after another from the bottom upward. We may be as sure that each layer was formed before those above it as that the bottom courses of stone in a wall were laid before the courses which rest upon them. We have no reason to believe that the lowest layers which we see here were the earliest ever formed. Indeed, some deep boring in the vicinity may prove that the ledges rest upon other layers of rock which extend downward for many hundreds of feet below the valley floor. Nor may we conclude that the highest layers here were the latest ever laid, for elsewhere we may find still later layers lying upon them. A short search may find in the rock relics of animals, such as the imprints of shells, which lived when it was deposited; and as these are of kinds whose nearest living relatives have now their home in the sea, we infer that it was on the flat sea floor that the sandstone was laid. Its present position, hundreds of feet above sea level, proves that it has since emerged to form part of the land, while the flatness of the beds shows the movement was so uniform and gentle as not to break or strongly bend them from their original attitude. The surface of some of these layers is ripple marked; hence the sand must once have been as loose as that of shallow sea bottoms and sea beaches to-day, which is thrown into similar ripples by movements of the water. In some way the grains have since become cemented into firm rock. Note that the layers on one side of the valley agree with those on the other, each matching the one opposite at the same level. Once they were continuous across the valley. Where the valley now is, was once a continuous upland built of horizontal layers. The layers now show their edges, or outcrop, on the valley sides, because they have been cut by the valley trench. The rock of the ledges is crumbling away. At the foot of each step of rock lie fragments which have fallen. Thus the valley is slowly widening. It has been narrower in the past. It will be wider in the future. Through the valley runs a stream. The waters of rain which have fallen on the upper parts of the stream's basin are now on their way to the river and the sea. Rock fragments and grains of sand creeping down the valley slopes come within reach of the stream and are washed along by the running water. Here and there they lodge for a time in banks of sand and gravel, but sooner or later they are taken up again and carried on. The grains of sand which were brought from some ancient source to form these rocks are on their way to some new goal. As they are washed along the rocky bed of the stream, they slowly rasp and wear it deeper. The valley will be deeper in the future. It has been less deep in the past. In this little valley we see slow changes now in progress. We find also in the composition, the structure, and the attitude of the rocks, and the landforms to which they have been sculpted, the record of a long succession of past changes, involving the origin of sand grains and their gathering and deposit upon the bottom of some ancient sea, the cementation of their layers into solid rock, the uplifting of the rocks to form a land surface, and, last of all, the carving of a valley in the upland. Everywhere, in the fields, along the river, among the mountains, by the seashore, and in the desert, we may discover slow changes now in progress, and the record of similar changes in the past. Everywhere we may catch glimpses of a process of gradual change, which stretches backward into the past and forward into the future, by which the forms and structures of the face of the earth are continually built and continually destroyed. The science which deals with this long process is geology. Geology treats of the natural changes now taking place upon the earth and within it, the agencies which produce them, and the landforms and rock structures which result. It studies the changes of the present in order to be able to read the history of the earth's changes in the past. The various agencies which have fashioned the face of the earth may be divided into two general classes. In Part I we shall consider those which work upon the earth from without, such as the weather, running water, glaciers, the wind, and the sea. In Part II we shall treat of those agencies whose sources are within the earth, and among whose manifestations are volcanoes and earthquakes, and the various movements of the earth's crust. As we study each agency, we shall notice not only how it does its work, but also the records which it leaves in the rock structures and the landforms which it produces. With this preparation, we shall be able, in Part III, to read in the records of the rocks the history of our planet and the successive forms of life which have dwelt upon it. End of Section 2.
Section 3 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Roger Moline. The Elements of Geology by William Harmon Norton. Chapter 1, Part 1. Part 1. External Geological Agencies. Chapter 1. The Work of the Weather. In our excursion to the valley with sandstone ledges, we witnessed a process which is going forward in all lands. Everywhere the rocks are crumbling away, the fragments are creeping down hillsides to the streamways and are carried by the streams to the sea, where they are rebuilt into rocky layers. When again the rocks are lifted to form land, the process will begin anew. Again they will crumble and creep down slopes and be washed by streams to the sea. Let us begin our study of this long cycle of change at the point where rocks disintegrate and decay under the action of the weather. In studying now a few outcrops and quarries, we shall learn a little of some common rocks and how they weather away. Stratification and jointing. At the sandstone ledges we saw that the rock was divided into parallel layers. The thicker layers are known as strata, and the thin leaves into which each stratum may sometimes be split are termed laminae. To a greater or less degree these layers differ from each other in fineness of grain, showing that the material has been sorted. The planes which divide them are called bedding planes. Besides the bedding planes there are other division planes, which cut across the strata from top to bottom. These are found in all rocks and are known as joints. Two sets of joints, running at about right angles to each other, together with the bedding planes, divide the sandstone into quadrangular blocks. Sandstone. Examining a piece of sandstone, we find it composed of grains quite like those of river sand or of sea beaches. Most of the grains are of a clear, glassy mineral called quartz. These quartz grains are very hard and will scratch the steel of a knife blade. They are not affected by acid, and their broken surfaces are irregular like those of broken glass. The grains of sandstone are held together by some cement. This may be calcareous, consisting of soluble carbonate of lime. In brown sandstones the cement is commonly ferruginous, hydrated iron oxide, or iron rust, forming the bond, somewhat as in the case of iron nails which have rusted together. The strongest and most lasting cement is silicious, and sand rocks whose grains are closely cemented by silica, the chemical substance of which quartz is made, are known as quartzites. We are now prepared to understand how sandstone is affected by the action of the weather. On ledges where the rock is exposed to view, its surface is more or less discolored, and the grains are loose and may be rubbed off with the finger. On gentle slopes the rock is covered with a soil composed of sand, which evidently is crumbled sandstone, and dark carbonaceous matter derived from the decay of vegetation. Clearly it is by the dissolving of the cement that the rock thus breaks down to loose sand. A piece of sandstone with calcareous cement, or a bit of old mortar, which is really an artificial stone also made of sand cemented by lime, may be treated in a test tube with hydrochloric acid to illustrate the process. A limestone quarry. Here also we find the rock stratified and jointed. On the quarry face the rock is distinctly seen to be altered for some distance from its upper surface. Below the altered zone the rock is sound and is quarried for building, but the altered upper layers are too soft and broken to be used for this purpose. If the limestone is laminated, the laminae here have split apart, although below they hold fast together. Near the surface the stone has become rotten and crumbles at the touch, while on the top it is completely broken down to a thin layer of limestone meal, on which rests a fine reddish clay. Limestone is made of minute grains of carbonate of lime, all firmly held together by a calcareous cement. A piece of the stone placed in a test tube with hydrochloric acid dissolves with brisk effervescence, leaving the insoluble impurities, which were disseminated through it, at the bottom of the tube as a little clay. We can now understand the changes in the upper layers of the quarry. At the surface of the rock the limestone has completely dissolved, leaving the insoluble residue as a layer of reddish clay. Immediately below the clay the rock has disintegrated into meal where the cement between the limestone grains has been removed, while beneath this the laminae are split apart where the cement has been dissolved only along the planes of lamination where the stone is more porous. As these changes in the rock are greatest at the surface and diminish downward, we infer that they have been caused by agents working downward from the surface. At certain points these agencies have been more effective than elsewhere. The upper rock surface is pitted. Joints are widened as they approach the surface, and along these seams we may find that the rock is altered even down to the quarry floor. A shale pit. Let us now visit some pit where shale, a laminated and somewhat hardened clay, is quarried for the manufacture of brick. The laminae of this fine-grained rock may be as thin as cardboard in places, and close joints may break the rock into small rhombic blocks. On the upper surface we note that the shale has weathered to a clayey soil in which all traces of structure have been destroyed. The clay and the upper layers of the shale beneath it are reddish or yellow, while in many cases the color of the unaltered rock beneath is blue. The sedimentary rocks. The three kinds of layered rocks whose acquaintance we have made, sandstone, limestone, and shale, are the leading types of this great group of stratified, or sedimentary, rocks. This group includes all rocks made of sediments, their materials having settled either in water upon the bottoms of rivers, lakes, or seas, or on dry land, as in the case of deposits made by the wind and by glaciers. Sedimentary rocks are divided into the fragmental rocks, which are made of fragments, either coarse or fine, and the far less common rocks, which are constituted of chemical precipitates. The sedimentary rocks are divided according to their composition into the following classes. 1. The arenaceous, or quartz rocks, including beds of loose sand and gravel, sandstone, quartzite, and conglomerate, a rock made of cemented rounded gravel or pebbles. 2. The calcareous or lime rocks, including limestone and a soft white rock formed of calcareous powder known as chalk. 3. The argillaceous or clay rocks, including muds, clays, and shales. These three classes pass by mixture into one another. Thus there are limy and clayey sandstones, sandy and clayey limestones, and sandy and limy shales. Granite. This familiar rock may be studied as an example of the second great group of rocks, the unstratified, or igneous rocks. These are not made of cemented sedimentary grains, but of interlocking crystals which have crystallized from a molten mass. Examining a piece of granite, the most conspicuous crystals which meet the eye are those of feldspar. They are commonly pink, white, or yellow, and break along smooth cleavage planes which reflect the light like tiny panes of glass. Mica may be recognized by its glittering plates, which split into thin elastic scales. A third mineral, harder than steel, breaking along irregular surfaces like broken glass, we identify as quartz. How granite alters under the action of the weather may be seen in outcrops where it forms the bedrock or country rock underlying the loose formations of the surface, and in many parts of the northern states where granite boulders and pebbles more or less decayed may be found in a surface sheet of stony clay called the drift. Of the different minerals composing granite, quartz alone remains unaltered. Mica weathers to detached flakes which have lost their elasticity. The feldspar crystals have lost their luster and hardness, and even have decayed to clay. Where long-weathered granite forms the country rock, it often may be cut with spade or trowel for several feet from the surface, so rotten is the feldspar, and here the rock is seen to break down to a clayey soil containing grains of quartz and flakes of mica. These are a few simple illustrations of the surface changes which some of the common kinds of rocks undergo. The agencies by which these changes are brought about we will now take up under two divisions: chemical agencies, producing rock decay, and mechanical agencies, producing rock disintegration. The chemical work of water. As water falls on the earth in rain, it has already absorbed from the air carbon dioxide, or carbonic acid gas, and oxygen. As it sinks into the ground and becomes what is termed groundwater, it takes into solution from the soil humus acids and carbon dioxide, both of which are constantly being generated there by the decay of organic matter. So both rain and groundwater are charged with active chemical agents, by the help of which they corrode and rust and decompose all rocks to a greater or less degree. We notice now three of the chief chemical processes concerned in weathering: solution, the formation of carbonates, and oxidation. Solution. Limestone, although so little affected by pure water that 5,000 gallons would be needed to dissolve a single pound, is easily dissolved in water charged with carbon dioxide. In limestone regions well water is therefore hard. On boiling the water for some time, the carbon dioxide gas is expelled, the whole of the lime carbonate can no longer be held in solution, and much of it is thrown down to form a crust or scale in the kettle or in the tubes of the steam boiler. All waters which flow over limestone rocks or soak through them are constantly engaged in dissolving them away, and in the course of time destroy beds of vast extent and great thickness. The upper surface of limestone rocks becomes deeply pitted, as we saw in the limestone quarry, and where the mantle of waste has been removed it may be found so intricately furrowed that it is difficult to traverse. Beds of rock salt buried among the strata are dissolved by seeping water, which issues in salt springs. Gypsum, a mineral composed of hydrated sulfate of lime and so soft that it may be scratched with the fingernail, is readily taken up by water, giving to the water of wells and springs a peculiar hardness difficult to remove. The dissolving action of moisture may be noted on marble tombstones of some age, marble being a limestone altered by heat and pressure and composed of crystalline grains. By assuming that the date on each monument marks the year of its erection, one may estimate how many years on the average it has taken for weathering to loosen fine grains on the polished surface, so that they may be rubbed off with the finger, to destroy the polish, to round the sharp edges of tool marks in the lettering, and at last to open cracks and seams and break down the stone. We may notice also whether the gravestones weather more rapidly on the sunny or the shady side, and on the sides or on the top. The weathered surface of granular limestone containing shells shows them standing in relief. As the shells are made of crystalline carbonate of lime, we may infer whether the carbonate of lime is less soluble in its granular or in its crystalline condition. The formation of carbonates. In attacking minerals, water does more than merely take them into solution. It decomposes them, forming new chemical compounds of which the carbonates are among the most important. Thus feldspar consists of the insoluble silicate of alumina, together with certain alkaline silicates which are broken up by the action of water containing carbon dioxide, forming alkaline carbonates. These carbonates are freely soluble and contribute potash and soda to soils and river waters. By the removal of the soluble ingredients of feldspar, there is left the silicate of alumina, united with water or hydrated, in the condition of a fine plastic clay which, when white and pure, is known as kaolin, and is used in the manufacture of porcelain. Feldspathic rocks which contain no iron compounds thus weather to whitish crusts, and even apparently sound crystals of feldspar, when ground to thin slices and placed under the microscope, may be seen to be milky in color throughout, because an internal change of kaolin has begun. Oxidation. Rocks containing compounds of iron weather to reddish crusts, and the seams of these rocks are often lined with rusty films. Oxygen and water have here united with the iron, forming hydrated iron oxide. The effects of oxidation may be seen in the alteration of many kinds of rocks, and in red and yellow colors of soils and subsoils. Pyrite is a very hard mineral of a pale brass color, found in scattered crystals in many rocks, and is composed of iron and sulfur, iron sulfide. Under the attack of the weather it takes up oxygen, forming iron sulfate, or green vitriol, a soluble compound, and insoluble hydrated iron oxide, which as a mineral is known as limonite. Several large masses of iron sulfide were placed some years ago on the lawn in front of the National Museum at Washington. The mineral changed so rapidly to green vitriol that enough of this poisonous compound was washed into the ground to kill the roots of the surrounding grass. Agents of mechanical disintegration. Heat and cold. Rocks exposed to the direct rays of the sun become strongly heated by day and expand. After sunset they rapidly cool and contract. When the difference in temperature between day and night is considerable, the repeated strains of sudden expansion and contraction at last become greater than the rocks can bear, and they break, for the same reason that a glass cracks when plunged into boiling water. Rocks are poor conductors of heat, and hence their surfaces may become painfully hot under the full blaze of the sun, while the interior remains comparatively cool. By day the surface shell expands and tends to break loose from the mass of the stone. In cooling in the evening, the surface shell suddenly contracts on the unyielding interior and in time is forced off in scales. Many rocks, such as granite, are made up of grains of various minerals which differ in color and in their capacity to absorb heat, and which therefore contract and expand in different ratios. In heating and cooling, these grains crowd against their neighbors and tear loose from them, so that finally the rock disintegrates into sand. The conditions for the destructive action of heat and cold are most fully met in arid regions, when vegetation is wanting for lack of sufficient rain. The soil not being held together by the roots of plants is blown away over large areas, leaving the rocks bare to the blazing sun in a cloudless sky. The air is dry, and the heat received by the earth by day is therefore rapidly radiated at night into space. There is a sharp and sudden fall of temperature after sunset, and the rocks, strongly heated by day, are now chilled perhaps even to the freezing point. In the Sahara the thermometer has been known to fall 131 degrees Fahrenheit within a few hours. In the light air of the Pamir Plateau in Central Asia, a rise of 90 degrees Fahrenheit has been recorded from 7 o'clock in the morning to 1 o'clock in the afternoon. On the mountains of southwestern Texas, there are frequently heard crackling noises as the rocks of that arid region throw off scales from a fraction of an inch to 4 inches in thickness, and loud reports are made as huge boulders split apart. Desert pebbles weakened by long exposure to heat and cold have been shivered to fine sharp-pointed fragments on being placed in sand heated to 180 degrees Fahrenheit. Beds half a foot thick, forming the floor of limestone quarries in Wisconsin, have been known to buckle and arch and break to fragments under the heat of the summer sun. Frost. By this term is meant the freezing and thawing of water contained in the pores and crevices of rocks. All rocks are more or less porous and all contain more or less water in their pores. Workers in stone call this quarry water, and speak of a stone as green before the quarry water has dried out. Water also seeps along joints and bedding planes and gathers in all seams and crevices. Water expands in freezing, 10 cubic inches of water freezing to about 11 cubic inches of ice. As water freezes in the rifts and pores of rocks, it expands with the irresistible force illustrated in the freezing and breaking of water pipes in winter. The first rift in the rock, perhaps too narrow to be seen, is widened little by the wedges of successive frosts, and finally the rock is broken into detached blocks, and these into angular chipstone by the same process. It is on mountain tops and in high latitudes that the effects of frost are most plainly seen. "Every summit," says Whymper, "amongst the rock summits upon which I have stood has been nothing but a piled up heap of fragments. In Iceland, in Spitzbergen, in Kamchatka, and in other frigid lands, large areas are thickly strewn with sharp-edged fragments into which the rock has been shattered by frost." Organic agents. We must reckon the roots of plants and trees among the agents which break rocks into pieces. The tiny rootlet in its search for food and moisture inserts itself into some minute rift, and as it grows, slowly wedges the rock apart. Moreover, the acids of the root corrode the rocks with which they are in contact. One may sometimes find in the soil a block of limestone wrapped in a mesh of roots, each of which lies in a little furrow where it has eaten into the stone. Rootless plants called lichens often cover and corrode rocks as yet bare of soil, but where lichens are destroying the rock less rapidly than does the weather, they serve in a way as a protection. Conditions favoring disintegration and decay. The disintegration of rocks under frost and temperature changes goes on most rapidly in cold and arid climates, and where vegetation is scant or absent. On the contrary, the decay of rocks under the chemical action of water is favored by a warm, moist climate and abundant vegetation. Frost and heat and cold can only act within the few feet from the surface to which the necessary temperature changes are limited, while water penetrates and alters the rocks to great depths. The pupil may explain. In what ways the presence of joints and bedding planes assists in the breaking up and decay of rocks under the action of the weather. Why it is a good rule of stonemasons never to lay stones on edge, but always on their natural bedding planes. Why stones fresh from the quarry sometimes go to pieces in early winter, when stones which have been quarried for some months remain uninjured. Why quarrymen in the northern states often keep their quarry floors flooded during winter. Why laminated limestone should not be used for curbstone. Why rocks composed of layers differing in fineness of grain and in ratios of expansion do not make good building stone. Fine-grained rocks with pores so small that capillary attraction keeps the water which they contain from readily draining away are more apt to hold their pores 10/11 full of water than are rocks whose pores are larger, which, therefore, are more likely to be injured by frost. Which is subject to greater temperature changes, a dark rock or one of a light color? The north side or the south side of a valley? End of section 3. Recording by Roger Moline. Section 4 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Roger Moline. The Elements of Geology by William Harmon Norton. Section 4. Chapter 1, Part 2. The Mantle of Rock Waste. We have seen that rocks are everywhere slowly wasting away. They are broken in pieces by frost, by tree roots, and by heat and cold. They dissolve and decompose under the chemical action of water and the various corrosive substances which it contains, leaving their insoluble residues as residual clays and sands upon the surface. As a result, there is everywhere forming a mantle of rock waste which covers the land. It is well to imagine how the country would appear were this mantle with its soil and vegetation all scraped away or had it never been formed. The surface of the land would then be everywhere of bare rock, as unbroken as a quarry floor. The thickness of the mantle. In any locality the thickness of the mantle of rock waste depends as much on the rate at which it is constantly being removed as on the rate at which it is forming. On the face of cliffs it is absent, for here waste is removed as fast as it is made. Where waste is carried away more slowly than it is produced, it accumulates in time to great depth. The granite of Pike's Peak is disintegrated to a depth of 20 feet. In the city of Washington, granite rock is so softened to a depth of 80 feet that it can be removed with pick and shovel. About Atlanta, Georgia, the rocks are completely rotted for 100 feet from the surface, while the beginnings of decay may be noticed at thrice that depth. In places in southern Brazil, the rock is decomposed to a depth of 400 feet. In southwestern Wisconsin, a reddish residual clay has an average depth of 13 feet on broad uplands, where it has been removed to the least extent. The country rock on which it rests is a limestone with about 10% of insoluble impurities. At least how thick then was that portion of the limestone which has rotted down to the clay? Distinguishing characteristics of residual waste. We must learn to distinguish waste formed in place by the action of weather from the products of other geological agencies. Residual waste is unstratified. It contains no substances which have not been derived from the weathering of the parent rock. There is a gradual transition from residual waste into the unweathered rock beneath. Waste resting on sound rock evidently has been shifted and was not formed in place. In certain regions of southern Missouri the land is covered with a layer of broken flints and red clay while the country rock is limestone. The limestone contains nodules of flint and we may infer that it has been of the decay and removal of thick masses of limestone that the residual layer of clay and flints has been left upon the surface. Flint is a form of quartz, dull lustered, usually gray or blackish in color, and opaque except on thinnest edges, where it is translucent. Over much of the northern states there is spread an unstratified stony clay called the drift. It often rests on sound rocks. It contains grains of sand, pebbles, and boulders composed of many different minerals and rocks that the country rock cannot furnish. Hence the drift cannot have been formed by the decay of the rock of the region. A shale or limestone, for example, cannot waste to a clay containing granite pebbles. The origin of the drift will be explained in subsequent chapters. The differences in rocks are due more to their soluble than their insoluble constituents. The latter are few in number and are much the same in rocks of widely different nature, being chiefly quartz, silicate of alumina, and iron oxide. By the removal of their soluble parts, very many and widely different rocks rot down to a residual clay, gritty with particles of quartz, and colored red or yellow with iron oxide. In a broad way, the changes which rocks undergo in weathering are an adaptation to the environment in which they find themselves at the earth's surface, an environment different from that in which they were formed undersea or underground. In open air, where they are attacked by various destructive agents, few of the rock-making minerals are stable compounds except quartz, the iron oxides, and the silicate of alumina, and so it is to one or more of these comparatively insoluble substances that most rocks are reduced by long decay. Which produces a mantle of finer waste, frost or chemical decay? Which a thicker mantle? In what respects would you expect that the mantle of waste would differ in warm humid lands like India, in frozen countries like Alaska, and in deserts such as the Sahara? The soil. The same agencies which produce the mantle of waste are continually at work upon it, breaking it up into finer and finer particles and causing its more complete decay. Thus on the surface, where the waste has weathered longest, it is gradually made fine enough to support the growth of plants, and is then known as soil. The coarser waste beneath is sometimes spoken of as subsoil. Soil usually contains more or less dark, carbonaceous, decaying organic matter, called humus, and is then often termed the humus layer. Soil forms not only on waste produced in place from the rock beneath, but also on materials which have been transported, such as sheets of glacial drift and river deposits. Until rocks are reduced to residual clays, the work of the weather is more rapid and effective on the fragments of the mantle of waste than on the rocks from which waste is being formed. Why? Any fresh excavation of cellar or cistern, or cut for road or railway, will show the characteristics of the humus layer. It may form only a gray film on the surface, or we may find it a layer a foot or more thick, dark or even black, above, and growing gradually lighter in color as it passes by insensible gradations into the subsoil. In some way the decaying vegetable matter continually forming on the surface has become mingled with the material beneath it. How humus and the subsoil are mingled. The mingling of humus and the subsoil is brought about by several means. The roots of plants penetrate the waste, and when they die leave their decaying substance to fertilize it. Leaves and stems falling on the surface are turned under by several agents. Earthworms and other animals whose home is in the waste drag them into their burrows either for food or to line their nests. Trees overthrown by the wind, roots and all, turn over the soil and subsoil and mingle them together. Bacteria also work in the waste and contribute to its enrichment. The animals living in the mantle do much in other ways toward the making of soil. They bring the coarser fragments from beneath to the surface, where the waste weathers more rapidly. Their burrows allow air and water to penetrate the waste more freely and to affect it to greater depths. Ants. In the tropics the mantle of waste is worked over chiefly by ants. They excavate underground galleries and chambers, extending sometimes as much as 14 feet below the surface, and build mounds which may reach as high above it. In some parts of Paraguay and southern Brazil, these mounds, like gigantic potato hills, cover tracts of considerable area. In search for its food, the dead wood of trees, the so-called white ant constructs runways of earth about the size of gas pipes, reaching from the base of the tree to the topmost branches. On the plateaus of Central Africa, explorers have walked for miles through forests, every tree of which was plastered with these galleries of mud. Each grain of earth used in their construction is moistened and cemented by slime as it is laid in place by the ant, and is thus acted on by organic chemical agents. Sooner or later these galleries are beaten down by heavy rains, and their fertilizing substances are scattered widely by the winds. Earthworms. In temperate regions the waste is worked over largely by earthworms. In making their burrows, worms swallow earth in order to extract from it any nutritive organic matter which it may contain. They treat it with their digestive acids, grind it in their stony gizzards, and void it in castings on the surface of the ground. It was estimated by Darwin that in many parts of England each year, on every acre, more than 10 tons of earth pass through the bodies of earthworms and are brought to the surface, and that every few years the entire soil layer is thus worked over by them. In all these ways the waste is made fine and stirred and enriched. Grain by grain, the subsoil with its fresh mineral ingredients is brought to the surface, and the rich organic matter which plants and animals have taken from the atmosphere is plowed under. Thus nature plows and harrows on the great world's farm to make ready and ever to renew a soil fit for the endless succession of her crops. The world processes by which rock are continually wasting away are thus indispensable to the life of plants and animals. The organic world is built on the ruins of the inorganic, and because the solid rocks have been broken down into soil, men are able to live upon the earth. Solar energy. The source of the energy which accomplishes all this necessary work is the sun. It is the radiant energy of the sun which causes the disintegration of rocks, which lifts vapor into the atmosphere to fall as rain, which gives life to plants and animals. Considering the earth in a broad way, we may view it as a globe of solid rock, the lithosphere surrounded by two mobile envelopes, the envelope of air, the atmosphere, and the envelope of water, the hydrosphere. Under the action of solar energy, these envelopes are in constant motion. Water from the hydrosphere is continually rising in vapor into the atmosphere, the air of the atmosphere penetrates the hydrosphere, for its gases are dissolved in all waters, and both air and water enter and work upon the solid earth. By their action upon the lithosphere they have produced a third envelope, the mantle of rock waste. This envelope also is in movement, not indeed as a whole, but particle by particle. The causes which set its particles in motion, and the different forms which the mantle comes to assume, we will now proceed to study. Movements of the mantle of rock waste. At the sandstone ledges which we first visited, we saw not only that the rocks were crumbling away, but also that grains and fragments of them were creeping down the slopes of the valley to the stream and were carried by it onward toward the sea. This process is going on everywhere. Slowly, it may be, and with many interruptions, but surely, the waste of the land moves downward to the sea. We may divide its course into two parts: the path to the stream, which we will now consider, and its carriage onward by the stream, which we will defer to a later chapter. Gravity. The chief agent concerned in the movement of waste is gravity. Each particle of waste feels the unceasing downward pull of the earth's mass and follows it when free to do so. All agencies which produce waste tend to set its particles free and in motion, and therefore cooperate with gravity. On cliffs, rocks fall when wedged off by frost or by roots of trees, and when detached by any other agency. On slopes of waste, water freezes in chinks between stones and in pores between particles of soil, and wedges them apart. Animals and plants stir the waste, heat expands it, cold contracts it. The strokes of the raindrops drive loose particles down the slope, and the wind lifts and lets them fall. Of all these movements, gravity assists those which are downhill, and retards those which are uphill. On the whole, therefore, the downhill movements prevail, and the mantle of waste, block by block and grain by grain, creeps along the downhill path. A slab of sandstone laid on another of the same kind at an angle of 17 degrees and left in the open air was found to creep down the slope at the rate of a little more than a millimeter a month. Explain why it did so. Rain. The most efficient agent in the carriage of waste to the streams is the rain. It moves particles of soil by the force of the blows of the falling drops, and washes them down all slopes to within reach of permanent streams. On surfaces unprotected by vegetation, as on plowed fields and in arid regions, the rain wears furrows and gullies both in the mantle of waste and in exposures of unaltered rock. At the foot of a hill we may find that the soil has accumulated by creep and wash to the depth of several feet, while where the hillside is steepest the soil may be exceedingly thin or quite absent, because removed about as fast as formed. Against the walls of an abbey built on a slope in Wales 700 years ago, the creeping waste has gathered on the uphill side to a depth of 7 feet. The slow-flowing sheet of waste is often dammed by fences and walls, whose uphill side gathers waste in a few years so as to show a distinctly higher surface than the downhill side, especially in plowed fields where the movement is least checked by vegetation. Talus. At the foot of cliffs there is usually to be found a slope of rock fragments which clearly have fallen from above. Such a heap of waste is known as talus. The amount of talus in any place depends both on the rate of its formation and the rate of its removal. Talus forms rapidly in climates where mechanical disintegration is most effective, where rocks are readily broken into blocks because closely jointed and thinly bedded rather than massive, and where they are firm enough to be detached in fragments of some size instead of in fine grains. Talus is removed slowly where it decays slowly, either because of the climate or the resistance of the rock. It may be rapidly removed by a stream flowing along its base. In a moist climate a soluble rock, such as massive limestone, may form talus little if any faster than the talus weathers away. A loose textured sandstone breaks down into incoherent sand grains which in dry climates, where unprotected by vegetation, may be blown away as fast as they fall, leaving the cliff bare to the base. Cliffs of such slow decaying rocks as quartzite and granite, when closely jointed, accumulate talus in large amounts. Talus slopes may be so steep as to reach the angle of repose, that is, the steepest angle at which the material will lie. This angle varies with different materials, being greater with coarse and angular fragments than with fine rounded grains. Sooner or later a talus reaches that equilibrium where the amount removed from its surface just equals that supplied from the cliff above. As the talus is removed and weathers away, its slope retreats together with the retreat of the cliff, as seen in Figure 9. Graded slopes. Where rocks weather faster than their waste is carried away, the waste comes at last to cover all rocky ledges. On the steeper slopes it is coarser and in more rapid movement than on slopes more gentle, but mountain sides and hills and plains alike come to be mantled with sheets of waste which everywhere is creeping toward the streams. Such unbroken slopes, worn or built to the least inclination at which the waste supplied by weathering can be urged onward, are known as graded slopes. Of far less importance than the silent gradual creep of waste, which is going on at all times everywhere about us, are the startling local and spasmodic movements which we are now to describe. Avalanches. On steep mountain sides, the accumulated snows of winter often slip and slide in avalanches to the valleys below. These rushing torrents of snow sweep their tracks clean of waste and are one of nature's normal methods of moving it along the downhill path. Landslides. Another common and abrupt method of delivering waste to streams is by slips of the waste mantle in large masses. After long rains and after winter frosts, the cohesion between the waste and the sound rock beneath is loosened by seeping water underground. The waste slips on the rock surface thus lubricated and plunges down the mountainside in a swift roaring torrent of mud and stones. We may conveniently mention here a second type of landslide, where masses of solid rock as well as the mantle of waste are involved in the sudden movement. Such slips occur when valleys have been rapidly deepened by streams or glaciers and their sides have not yet been graded. A favorable condition is where the strata dip, that is, incline downwards, towards the valley, or are broken by joint planes dipping in the same direction. The upper layers, including perhaps the entire mountainside, have been cut across by the valley trench and are left supported only on the inclined surface of the underlying rocks. Water may percolate underground along this surface and loosen the cohesion between the upper and the underlying strata by converting the upper surface of a shale to soft wet clay, by dissolving layers of a limestone, or by removing the cement of a sandstone and converting it into loose sand. When the inclined surface is thus lubricated, the overlying masses may be launched into the valley below. The solid rocks are broken and crushed in sliding and converted into waste consisting, like that of talus, of angular unsorted fragments, blocks of all sizes being mingled pell-mell with rock meal and dust. The principal effects of landslides may be gathered from the following examples. At Gona, India, in 1893, the face of a spur 4,000 feet high of the lower ranges of the Himalayas slipped into the gorge of the headwaters of the Ganges River in successive rock falls which lasted for 3 days. Blocks of stone were projected for a mile, and clouds of limestone dust were spread over the surrounding country. The debris formed a dam 1,000 feet high, extending for 2 miles along the valley. A lake gathered behind this barrier, gradually rising until it overtopped it in a little less than a year. The upper portion of the dam then broke, and a terrific rush of water swept down the valley in a wave which, 20 miles away, rose 160 feet in height. A narrow lake is still held by the strong base of the dam. In 1896, after 40 days of incessant rain, a cliff of sandstone slipped into the Yangtze River in China, reducing the width of the channel to 80 yards and causing formidable rapids. At Flims, in Switzerland, a prehistoric landslip flung a dam 1,800 feet high across the headwaters of the Rhine. If spread evenly over a surface of 28 square miles, the material would cover it to a depth of 660 feet. The barrier is not yet entirely cut away, and several lakes are held in shallow basins on its hummocky surface. A slide from the precipitous river front of the Citadel Hill of Quebec in 1889 dashed across Champlain Street, wrecking a number of houses and causing the death of 45 persons. The strata here are composed of steeply dipping slate. In lofty mountain ranges there may not be a single valley without its traces of landslides, so common there is this method of the movement of waste, and of building to grade over steepened slopes. Rock sculpture by weathering. We are now to consider a few of the forms into which rock masses are carved by the weather. Boulders of weathering. In many quarries and outcrops we may see that the blocks into which one or more of the uppermost layers have been broken along their joints and bedding planes are no longer angular, as are those of the layers below. The edges and corners of these blocks have been worn away by the weather. Such rounded cores, known as boulders of weathering, are often left to strew the surface. Differential weathering. This term covers all cases in which a rock mass weathers differently in different portions. Any weaker spots or layers are etched out on the surface, leaving the more resistant in relief. Thus massive limestones become pitted where the weather drills out the weaker portions. In these pits, when once they are formed, moisture gathers, a little soil collects, vegetation takes root, and thus they are further enlarged until the limestone may be deeply honeycombed. On the sides of cañons and elsewhere where the edges of strata are exposed, the harder layers project as cliffs, while the softer weather back to slopes covered with a talus of the harder layers above them. It is convenient to call the former cliff makers and the latter slope makers. Differential weathering plays a large part in the sculpture of the land. Areas of weak rock are wasted to plains, while areas of hard rock adjacent are still left as hills and mountain ridges, as in the valleys and mountains of eastern Pennsylvania. But in such instances the lowering of the surface of the weaker rock is also due to the wear of streams, and especially to the removal by them from the land of the waste which covers and protects the rocks beneath. Rocks owe their weakness to several different causes. Some, such as beds of loose sand, are soft and easily worn by rains. Some, as limestone and gypsum, for example, are soluble. Even hard, insoluble rocks are weak under the attack of the weather when they are closely divided by joints and bedding planes, and are thus readily broken up into blocks by mechanical agencies. Outliers and monuments. As cliffs retreat under the attack of the weather, portions are left behind where the rock is more resistant or where the attack for any reason is less severe. Such remnant masses, if large, are known as outliers. When? Note the rain furrows on the slope at the foot of the monuments. In the foreground are seen fragments of petrified trunks of trees, composed of silica and extremely resistant to the weather. On the removal of the rock layers in which these fragments were embedded, they are left to strew the surface in the same way as are the residual flints of southern Missouri. Flat-topped because of the protection of a resistant horizontal capping layer, they are termed mesas, a term applied also to the flat-topped portions of dissected plateaus. Retreating cliffs may fall back a number of miles behind their outliers before the latter are finally consumed. Monuments are smaller masses and may be but partially detached from the cliff face. In the breaking down of sheets of horizontal strata, outliers grow smaller and smaller and are reduced to massive rectangular monuments resembling castles. The rock castle falls into ruin, leaving here and there an isolated tower. The tower crumbles to a lonely pillar, soon to be overthrown. The various and often picturesque shapes of monuments depend on the kind of rock, the attitude of the strata, and the agent by which they are chiefly carved. Thus pillars may have a capital formed of a resistant stratum. Monuments may be undercut and come to rest on narrow pedestals, wherever they weather more rapidly near the ground, either because of the greater moisture there, or, in arid climates, because worn at their base by drifting sands. Stony clays disintegrating under the rain often contain boulders which protect the softer material beneath from the vertical blows of raindrops, and thus come to stand on pedestals of some height. One may sometimes see on the ground beneath dripping eaves pebbles left in the same way, protecting tiny pedestals of sand. Mountain peaks and ridges. Most mountains have been carved out of great, broadly uplifted folds and blocks of the earth's crust. Running water and glacier ice have cut these folds and blocks into masses divided by deep valleys, but it is by the weather, for the most part, that the masses thus separated have been sculptured to the present forms of the individual peaks and ridges. Frost and heat and cold sculpture high mountains to sharp, tusk-like peaks and ragged, serrate crests, where their waste is readily removed. The Matterhorn of the Alps is a famous example of a mountain peak whose carving by the frost and other agents is in active progress. On its face, scarcely a rock anywhere is firmly attached, and the fall of loosened stones is incessant. Mountain climbers who have camped at its base tell how huge rocks from time to time come leaping down its precipices, followed by trains of dislodged smaller fragments and rock dust, and how at night one may trace the course of the boulders by the sparks which they strike from the mountain walls. Mount Assiniboine, Canada, resembles the Matterhorn in form and has been carved by the same agencies. The Needles of Arizona are examples of sharp mountain peaks in a warm, arid region, sculptured chiefly by temperature changes. Chemical decay, especially when carried on beneath a cover of waste and vegetation, favors the production of rounded knobs and dome-shaped mountains. The weather curve. We have seen that weathering reduces the angular block quarried by the frost to a rounded boulder by chipping off its corners and smoothing away its edges. In much the same way, weathering at last reduces to rounded hills the earth blocks cut by streams or formed in any other way. High mountains may at first be sculptured by the weather to savage peaks, but toward the end of their life history they wear down to rounded hills. The weather curve, which may be seen on the summits of low hills, is convex upward. In Fig. 22, representing a cubic block of stone whose face are a yard square, how many square feet of surface are exposed to the weather by a cubic foot at a corner A, by one situated in the middle of an edge B, by one in the center of a side C? How much faster will A and B weather than C, and what will be the effect on the shape of the block? The cooperation of various agencies in rock sculpture. For the sake of clearness, it is necessary to describe the work of each geological agent separately. We must not forget, however, that in nature no agent works independently and alone, that every result is the outcome of a long chain of causes. Thus, in order that the mountain peak may be carved by the agents of disintegration, the waste must be rapidly removed, a work done by many agents, including some which we are yet to study; and in order that the waste may be removed as fast as formed, the region must first have been raised well above the level of the sea, so that the agents of transportation could do their work effectively. The sculpture of the rocks is accomplished only by the cooperation of many forces. The constant removal of waste from the surface by creep and wash and carriage by streams is of the highest importance, because it allows the destruction of the land by means of weathering to go on as long as any land remains above sea level. If waste were not removed, it would grow to be so thick as to protect the rock beneath from further weathering, and the processes of destruction which we have studied would be brought to an end. The very presence of the mantle of waste over the land proves that on the whole rocks weather more rapidly than their waste is removed. The destruction of the land is going on as fast as the waste can be carried away. We have now learned to see, in the mantle of waste, the record of the destructive action of the agencies of weathering on the rocks of the land surface. Similar records we shall find buried deeply among the rocks of the crust in old soils, and in rocks pitted and decayed, telling of old land surfaces long wasted by the weather. Ever since the dry land appeared these agencies have been as now quietly and unceasingly at work upon it, and have ever been the chief means of the destruction of its rocks. The vast bulk of the stratified rocks of the earth's crust is made up almost wholly of the waste thus worn from ancient lands. In studying the various geological agencies, we must remember the almost inconceivable times in which they work. The slowest process, when multiplied by the immense time in which it is carried on, produces great results. The geologist looks upon the land forms of the earth's surface as monuments which record the slow action of weathering and other agents during the ages of the past. The mountain peak, the rounded hill, the wide plain which lies where hills and mountains once stood, tell clearly of the great results which slow processes will reach when given long time in which to do their work. We should accustom ourselves also to think of the results which weathering will sooner or later bring to pass. The tombstone and the boulder of the field, which each year lose from their surfaces a few crystalline grains, must in time be wholly destroyed. The hill whose rocks are slowly rotting underneath a cover of waste must become lower and lower as the centuries and millenniums come and go, and will finally disappear. Even the mountains are crumbling away continually, and therefore are but fleeting features of the landscape. End of section 4. Recording by Roger Moline.
Section 5 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 2. The Work of Groundwater. Land waters. We have seen how large is the part that water plays at and near the surface of the land in the processes of weathering and in the slow movement of waste down all slopes to the streamways. We now take up the work of water as it descends beneath the ground, a corrosive agent still, and carrying in solution as its load the invisible waste of rocks derived from their soluble parts. Land waters have their immediate source in the rainfall. By the heat of the sun, water is evaporated from the reservoir of the ocean and from most surfaces everywhere. Mingled as vapor with the air, it is carried by the winds over sea and land, and condensed it returns to the earth as rain or snow. That part of the rainfall which descends on the ocean does not concern us, but that which falls on the land accomplishes, as it returns to the sea, the most important work of all surface geological agencies. The rainfall may be divided into three parts. The first dries up, being discharged into the air by evaporation either directly from the soil or through vegetation. The second runs off over the surface to flood the streams. The third soaks in the ground, and is henceforth known as ground or underground water. The descent of groundwater. Seeping through the mantle of waste, groundwater soaks into the pores and crevices of the underlying rock. All rocks of the upper crust of the earth are more or less porous, and all drink in water. Impervious rocks, such as granite, clay, and shale, have pores so minute that the water which they take in is held fast within them by capillary attraction, and none drains through. Pervious rocks, on the other hand, such as many sandstones, have pore spaces so large that water filters through them more or less freely. Besides its seepage through the pores of pervious rocks, water passes to lower levels through the joints and cracks by which all rocks near the surface are broken. Even the closest grained granite has a pore space of 1 in 400, while sandstone may have a pore space of 1 in 4. Sand is so porous that it may absorb a third of its volume of water, and loose loam even as much as 1/2. The groundwater surface is the name given to the upper surface of groundwater, the level below which all rocks are saturated. In dry seasons, the groundwater surface sinks, for groundwater is constantly seeping downward under gravity. It is evaporated in the waste, and its moisture is carried upward by capillarity in the roots of plants to the surface to be evaporated in the air. In wet seasons, these constant losses are more than made good by fresh supplies from that part of the rainfall which soaks into the ground, and the groundwater surface rises. In moist climates, the groundwater surface, Figure 24, lies, as a rule, within a few feet of the land surface and conforms to it in a general way, although with slopes of less inclination than those of the hills and valleys. In the dry climates, permanent groundwater may be found only at depths of hundreds of feet. Groundwater is held at its height by the fact that its circulation is constantly impeded by capillarity and friction. If it were as free to drain away as our surface streams, it would sink, soon after a rain, to the level of the deepest valleys of the region. Wells and springs. Excavations made in permeable rocks below the groundwater surface fill to its level and are known as wells. Where valleys cut this surface, permanent streams are formed, the water either oozing forth along ill-defined areas or issuing at definite points called springs, where it is concentrated by the structure of the rocks. A level tract where the groundwater surface coincides with the surface of the ground is a swamp or marsh. By studying a spring, one may learn much of the ways and work of groundwater. Spring waters differs from that of the stream into which it flows in several respects. If we test the spring with a thermometer during successive months, we shall find that its temperature remains much the same year-round. In summer it is markedly cooler than the stream. In winter it is warmer, and remains unfrozen, while the latter perhaps is locked in ice. This means that its underground path must lie at such a distance from the surface that it is little affected by summer's heat and winter's cold. While the stream is often turbid with surface waste washed into it by rains, the spring remains clear. Its water has been filtered during the slow movement through many small underground passages and the pores of rocks. Commonly the spring differs from the stream in that it carries a far larger load of dissolved rock. Chemical analysis proves that streams contain various minerals in solution, but these are usually in quantities so small that they are not perceptible to the taste or feel. But the water of springs is often well charged with soluble minerals. In its slow, long journey underground, it has searched out the soluble parts of the rocks through which it seeps, and has dissolved as much of them as it could. When spring water is boiled away, the invisible load which it has carried is left behind, and in composition is found to be practically identical with that of the soluble ingredients of the country rock. Although to some extent the soluble waste of rocks is washed down surface slopes by the rain, by far the larger part is carried downward by groundwater and is delivered to streams by springs. In limestone regions, springs are charged with calcium carbonate, the carbonate of lime. And where the limestone is magnesian, they contain magnesium carbonate also. Such waters are hard. When used in washing, the minerals which they contain combine with the fatty acids of soap to form insoluble curdy compounds. When springs rise from rocks containing gypsum, they are hard with calcium sulfate. In granite regions, they contain more or less soda and potash from the decay of feldspar. The flow of springs varies much less during the different seasons of the year than does that of surface streams. So slow is the movement of groundwater through the rocks that even during long droughts, large amounts remain stored above the levels of surface drainage. Movements of groundwater. Groundwater is in constant movement toward its outlets. Its rate varies according to many conditions, but always is extremely slow. Even through loose sands beneath the beds of rivers, it sometimes does not exceed 1/5 of a mile a year. In any region, two zones of flow may be distinguished. The upper zone of flow extends from the groundwater surface downward through the waste mantle and any permeable rocks on which the mantle rests. As far as the first impermeable layer, when descending movement of the water is stopped. The deep zones of flow occupy any pervious rocks which may be found below the impervious layer which lies nearest to the surface. The upper zone is a vast sheet of water saturating the soil and rocks, and slowly seeping downward through their pores and interstices along the slopes to the valleys, where in part it discharges in springs and often unites also in a wide underflowing stream which supports and feeds the river, Figure 24. A city in a region of copious rains, built on the narrow floodplains of a river, overlooked by hills, depends for its water supply on driven wells, within the city limits, sunk in the sand a few yards from the edge of the stream. Are these wells fed by water from the river percolating through the sand, or by groundwater on its way to the stream, and possibly contaminated with the sewage of the town? At what height does the underground water stand in the wells of your region? Does it vary with the season? Have you ever known wells to go dry? It may be possible to get data from different wells and to draw a diagram showing the groundwater surface as compared with the surface of the ground. Fissure springs and artesian wells. The deeper zones of flow lie in pervious strata, which are overlain by some impervious stratum. Such layers are often carried by their dip to great depths, and water may circulate in them to far below the level of the surface streams and even of the sea. When a fissure crosses a water-bearing stratum, or aquifer, Water is forced upward by the pressure of the weight of the water contained in the higher parts of the stratum, and may reach the surface as a fissure spring. A boring which taps such an aquifer is known as an artesian well, a name derived from a province in France where wells of this kind have been long in use. The rise of the water in artesian wells and in fissure springs also depends on the following conditions illustrated in Figure 29. The aquifer dips toward the region of the wells from higher ground, where it outcrops and receives its water. It is enclosed between an impervious layer above and watertight or waterlogged layers beneath. The weight of the column of water thus enclosed in the aquifer causes the water to rise in the well, precisely as the weight of the water in a standpipe forces it in connected pipes to the upper stories of buildings. Which will supply the larger region with artesian wells, an aquifer whose dip is steep or one whose dip is gentle? Which of the two aquifers, their thickness being equal, will have the larger outcrop and therefore be able to draw upon the larger amount of water from the rainfall? Illustrate with diagrams. The zone of solution. Near the surface, where the circulation of groundwater is most active, it oxidizes, corrodes, and dissolves the rocks through which it passes. It leaches soils and subsoils of their lime and other soluble minerals upon which plants depend for their food. It takes away the soluble cements of rocks. It widens fissures and joints and opens winding passages along the bedding planes. It may even remove whole beds of soluble rocks, such as rock salt, limestone, or gypsum. The work of groundwater in producing landslides has already been noticed. The zone in which the work of groundwater is thus for the most part destructive we may call the zone of solution. Caves. In massive limestone rocks, groundwater dissolves channels which sometimes form large caves. Figure 30. The necessary conditions for the excavation of caves of great size are well shown in central Kentucky, where an upland is built throughout of thick horizontal beds of limestone. The absence of layers of insoluble or impervious rocks in its structure allows of free circulation of groundwater within it by the way of all natural openings in the rock. These waterways have been gradually enlarged by solution and wear until the upland is honeycombed with caves. 500 open caverns are known in one county. Mammoth Cave, the largest of these caverns, consists of a labyrinth of chambers and winding galleries whose total length is said to be as much as 30 miles. One passage, 4 miles long, has an average width of about 60 feet and an average height of 40 feet. One of the great halls is 300 feet in width and is overhung by a solid arch of limestone 100 feet above the floor. Galleries at different levels are connected by well-like pits, some of which measure 225 feet from top to bottom. Through some of the lowest of these tunnels flows Echo River, still at work dissolving and wearing away the rock, while on its dark way to appear at the surface as a great spring. Natural bridges. As a cavern enlarges and the surface of the land above it is lowered by weathering, the roof at last breaks down and the cave becomes an open ravine. A portion of the roof may for a while remain, forming a natural bridge. Sinkholes. In limestone regions, channels underground may become so well developed that the water of rains rapidly drains away through them. Groundwater stands low and wells must be sunk deep to find it. Little or no surface water is left to form brooks. Thus, across the limestone upland of central Kentucky, one meets but 3 surface streams in 100 miles. Between their valleys, surface water finds its way underground by means of sinkholes. These are pits, commonly funnel-shaped, formed by the enlargement of crevice or joint by percolating water, or by the breakdown of some portion of the roof of a cave. By clogging of the outlet, a sinkhole may come to be filled by a pond. Central Florida is a limestone region with its drainage largely subterranean and in part below the level even of the sea. Sinkholes are common, and many of them are occupied by lakelets. Great springs mark the point of issue of underground streams, while some rise from beneath the sea. Silver Spring, one of the largest, discharges from a basin 800 feet wide and 30 feet deep, a little river, navigable for some steamers to its source. About the spring there are no surface streams for 60 miles. The karst. Along the eastern coast of the Adriatic, as far south as Montenegro, lies a belt of limestone mountains singularly worn and honeycombed by the solvent action of water. Where forests have been cut from the mountain sides and the red soil has washed away, the surface of the white limestone forms a pathless desert of rock where each square rod has been corroded into an intricate branch work of shallow furrows and sharp ridges. Great sinkholes, some of them 600 feet deep and more, pockmark the surface of the land. The drainage is chiefly subterranean. Surface streams are rare, and a portion of their courses is often underground. Fragmentary valleys come suddenly to an end at walls of rock where the rivers which occupy the valleys plunge into dark tunnels to reappear some miles away. Groundwater stands so far below the surface that it cannot be reached by wells, and the inhabitants depend on rainwater stored for household uses. The finest cavern of Europe, the Adelsberg Grotto, is in this region. Karst, the name of a part of this country, is now used to designate any region or landscape thus sculptured by the chemical action of surface and groundwater. We must remember that karst regions are rare, and striking as is the work of subterranean streams. It is far less important that the work done by sheets of underground water slowly seeping through all subsoils and porous rocks in other regions. Even when gathered into definite channels, groundwater does not have the erosive power of surface streams, since it carries with it little or no rock waste. Regions whose underground drainage is so perfect that the development of surface streams has been retarded or prevented escape to a large extent the leveling action of surface running waters, and may therefore stand higher than the surrounding country. The hill honeycombed by Luray Cavern, Virginia, has been attributed to this cause. Cavern deposits. Even in the zone of solution, water may under certain circumstances deposit as well as erode. As it trickles from the roof of caverns, the lime carbonate which it has taken into solution from the layers of limestone above is deposited by evaporation in the air in icicle-like pendants called stalactites. As the drops splash on the floor, there are built up in the same way thicker masses called stalagmites, which may grow to join the stalactites above, forming pillars. A stalagmitic crust often seals with rock the earth which accumulates in caverns, together with whatever relics of cave dwellers, either animals or men, it may contain. Can you explain why slender stalactites formed by the drip of single drops are often hollow pipes? The zone of cementation. With increasing depth, subterranean water becomes more and more sluggish in its movements and more highly charged with minerals dissolved from the rocks above. At such depths it deposits these minerals in the pores of rocks, cementing their grains together, and in crevices and fissures, forming mineral veins. Thus below the zone of solution, where the work of water is to dissolve, lies the zone of cementation, where its work is chemical deposit. A part of the invisible load of waste is thus transferred from rocks near the surface to those at greater depths. As the land surface is gradually lowered by weathering and the work of rain and streams, rocks which have lain deep within the zone of cementation are brought within the zone of solution. Thus, there are exposed to view limestones, whose cracks were filled with calcite, crystallized carbonate of lime, with quartz or other minerals, and sandstones whose grains were well cemented many feet below the surface. Cavity filling. Small cavities in the rocks are often found more or less completely filled with minerals deposited from solution by water in its constant circulation underground. The process may be illustrated by the deposit of salt crystals in a cup of evaporating brine. But in the latter instance, the solution is not renewed, as in the case of cavities in the rocks. A cavity thus lined with inward-pointing crystals is called a geode. Concretions. Groundwater seeping through the pores of rocks may gather minerals disseminated through them into nodular masses called concretions. Thus, silica disseminated through limestone is gathered into nodules of flint. While geodes grow from the outside inwards, concretions grow outwards from the center, nor are they formed in already existing cavities as are geodes. In soft clays, concretions may, as they grow, press the clay aside. In many other rocks, concretions are made by the process of replacement. Molecule by molecule, the rock is removed, and the mineral of the concretion substituted in its place. The concretion may in this way preserve intact the lamination lines or other structures of the rock. Clays and shales often contain concretions of lime carbonate, of iron carbonate, or of iron sulfide. Some fossil, such as a leaf or shell, frequently forms the nucleus around which the concretion grows. Why are building stones more easily worked when green than after their quarry water is dried out? Deposits of groundwater in arid regions. In arid lands where groundwater is drawn by capillarity to the surface and there evaporates, it leaves as surface incrustations the minerals held in solutions. White limey incrustations of this nature cover considerable tracts in northern Mexico. Evaporating beneath the surface, groundwater may deposit a limy cement in beds of loose sand and gravel. Such firmly cemented layers are not uncommon in western Kansas and Nebraska, where they are known as mortar beds. Thermal springs. While the lower limit of surface drainage is sea level, subterranean water circulates much below that depth, and is brought again to the surface by hydrostatic pressure. In many instances, springs have a higher temperature than the average annual temperature of the region, and are then known as thermal springs. In regions of present or recent volcanic activity, such as the Yellowstone National Park, we may believe that the heat of thermal springs is derived from uncooled lavas, perhaps not far below the surface. But when hot springs occur at a distance of hundreds of miles from any volcano, as in the case of the hot springs of Bath, England, it is probable that their waters have risen from the heated rocks of the Earth's interior. The springs of Bath have a temperature of 120 degrees Fahrenheit, 70 degrees above the average annual temperature of the place. If we assume that the rate of increase in the Earth's internal heat is here the average rate, 1 degree Fahrenheit to every 60 feet of descent, we may conclude that the springs of Bath rise from at least a depth of 4,200 feet. Water may descend to depths from which it can never be brought back by hydrostatic pressure. It is absorbed by highly heated rocks deep below the surface. From time to time, some of this deep-seated water may be returned to open air in the steam of volcanic eruptions. Surface deposits of springs. Where subterranean water returns to the surface, highly charged with minerals in solution, on exposure to the air it is commonly compelled to lay down much of its invisible load in chemical deposits about the spring. These are thrown down from solution either because of cooling, evaporation, the loss of carbon dioxide, or the work of algae. Many springs have been charged under pressure with carbon dioxide from subterranean sources, and are able therefore to take up large quantities of lime carbonate from the limestone rocks through which they pass. On reaching the surface, the pressure is relieved, the gas escapes, and the lime carbonate is thrown down in deposits called travertine. The gas is sometimes withdrawn, and the deposit produced in large part by the action of algae and other humble forms of plant life. At the Mammoth Hot Springs in the valley of the Gardiner River, Yellowstone National Park, beautiful terraces and basins of travertine are now building. chiefly by means of algae which cover the bottoms, rims, and sides of the basins and deposit lime carbonate upon them in successive sheets. The rock, snow white where dry, is coated with red and orange gelatinous mats where the algae thrive in the overflowing waters. Similar terraces of travertine are found to a height of 1,400 feet up the valley side. We may infer that the springs which formed these ancient deposits discharged near what was then the bottom of the valley, and that as the valley has been deepened by the river, the groundwater of the region has found lower and lower points of issue. In many parts of the country, calcareous springs occur which coat with lime carbonate mosses, twigs, and other objects over which their waters flow. Such are popularly known as petrifying springs, although they merely encrust the objects and do not convert them into stone. Silica is soluble in alkaline waters, especially when these are hot. Hot springs, rising through alkaline siliceous rocks such as lavas, often deposit silica in a white spongy formation known as siliceous sinter, both by evaporation and by the action of algae which secrete silica from the waters. It is in this way that the cones and mounds of the geysers in the Yellowstone National Park and in Iceland have been formed. Where water oozes from the earth, one may sometimes see a rusty deposit on the ground, and perhaps an iridescent scum upon the water. The scum is often mistaken for oil, but at a touch it cracks and breaks, as oil would not do. It is a film of hydrated iron oxide or limonite, and the spring is an iron or chalybeate spring. Compounds of iron have been taken into solution by groundwater from soil and rocks, and are now changed to the insoluble oxide on exposure to the oxygen of the air. In wet ground, compounds leached by groundwater from the soil often collect in reddish deposits a few feet below the surface, where their downward progress is arrested by some impervious clay. At the bottom of bogs and shallow lakes, iron ores sometimes accumulate to a depth of several feet. Decaying organic matter plays a large part in these changes. In its presence, the insoluble iron oxides which give color to most red and yellow rocks are decomposed, leaving the rocks of a gray or bluish color, and the soluble iron compounds which result are readily leached out, effects seen where red or yellow clays have been bleached about some decaying tree root. The iron thus dissolved is laid down as limonite when oxidized, as about a chalybeate spring. But out of contact with the air and in the presence of carbon dioxide supplied by decaying vegetation, as in a peat bog, it may be deposited as iron carbonate, or siderite. Total amount of underground waters. In order to realize the vast work in solution and cementation which underground waters are now doing and have done in all geological ages, we must gain some conception of their amount. At a certain depth, estimated at about 6 miles, the weight of the crust becomes greater than the rocks can bear, and all cavities and pores in them must be completely closed by the enormous pressure which they sustain. Below a depth of even 3 or 4 miles, it is believed that groundwater cannot circulate. Estimating the average pore spaces of the different rocks of the Earth's crust above this depth, and the average percents of their pore spaces occupied by water, it has been recently computed that the total amount of groundwater is equal to a sheet of water 100 feet deep, covering the entire surface of the earth. End of section 5, recorded by Andrew Nelson, Atlanta, Georgia.
Section 6 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton, Chapter 3, Part 1.
Rivers and valleys. The runoff. We have traced the history of that portion of the rainfall which soaks into the ground. Let us now return to that part which washes along the surface and is known as the run-off. Fed by rains and melting snows, the run-off gathers into courses, perhaps but faintly marked at first, which join more definite and deeply cut channels, as twigs their stems. In a humid climate, the larger ravines through which the run-off flows soon descend below the groundwater surface. Here springs discharge along the sides of the little valleys, and permanent streams begin. The water supplied by the run-off here joins that part of the rainfall which had soaked into the soil, and both now proceed together by way of the stream to the sea. River floods. Streams vary greatly in volume during the year. At stages of flood, they fill their immediate banks or overrun them and inundate any low lands adjacent to the channel. At stages of low water, they diminish to but a fraction of their volume when at flood. At times of flood, rivers are fed chiefly by the run-off. At times of low water, largely or even wholly by springs. How then will the water of streams differ at these times in turbidity and in the relative amount of solids carried in solution? In parts of England, streams have been known to continue flowing after 18 months of local drought, so great is the volume of water which in humid climates is stored in the rocks above the drainage level, and so slowly is it given off in springs. In Illinois and the states adjacent, rivers remain low in winter, and a spring freshet follows the melting of the winter's snows. A June rise is produced by the heavy rains of early summer. Low water follows in July and August, and streams are again swollen to a moderate degree under the rains of autumn. The discharge of streams. The percent of rainfall discharged by rivers varies with the amount of rainfall, the slope of the drainage area, the texture of the rocks, and other factors. With an annual rainfall of 50 inches in an open country, about 50% is discharged, while with a rainfall of 20 inches, only 15% is discharged, part of the remainder being evaporated, and part passing underground beyond the drainage area. Thus the Ohio discharges 30% of the rainfall of its basin, while the Missouri carries away but 15%. A number of the streams of the semi-arid lands of the West do not discharge more than 5% of the rainfall. Other things being equal, which will afford the larger proportion of runoff? A region underlain with granite rock or with coarse sandstone? Grassland or forest? Steep slopes or level land? A well-drained region or one abounding in marshes and ponds? Frozen or unfrozen ground? Will there be a larger proportion of runoff after long rains or after a season of drought? After long and gentle rains, or after the same amount of precipitation in a violent rain? During the months of growing vegetation, from June to August, or during the autumn months? Desert streams. In arid regions, the groundwater surface lies so low that for the most part streamways do not intersect it. Streams, therefore, are not fed by springs, but instead lose volume as their waters soak into the thirsty rocks over which they flow. They contribute to the groundwater of the region instead of being increased by it. Being supplied chiefly by the runoff, they wither at times of drought to a mere trickle of water, to a chain of pools, or go wholly dry, while at long intervals rains fill their dusty beds with sudden, raging torrents. Desert rivers therefore periodically shorten and lengthen their courses, withering back at times of drought for scores of miles, or even for 100 miles from the point reached by their waters during seasons of rain. The geological work of streams. The work of streams is of three kinds: transportation, erosion, and deposition. Streams transport the waste of the land. They wear or erode their channels both on bed and banks, and they deposit portions of their load from time to time along their courses, finally laying it down in the sea. Most of the work of streams is done at times of flood. Transportation. The invisible load of streams. Of the waste which a river transports, we may consider first the invisible load which it carries in solution, supplied chiefly by springs, but also in part by the run-off and from the solution of the rocks of its bed. More than half of the dissolved solids in the water of the average river consists of the carbonates of lime and magnesia. Other substances are gypsum, sodium sulfate, Glauber's salts, magnesium sulfate, Epsom salts, sodium chloride, common salt, and even silica, the least soluble of the common rock-making materials. The amount of this invisible load is surprisingly large. The Mississippi, for example, transports each year 113 million tons of dissolved rock to the Gulf. The visible load of streams. This consists of the silt which the stream carries in suspension, and the sand and gravel and larger stones which it pushes along its bed. Especially in times of flood, one may note the muddy water, its silt being kept from settling by the rolling, eddying currents, and often, by placing his ear close to the bottom of a boat, one may hear the clatter of pebbles as they are hurried along. In mountain torrents, the rumble of boulders as they clash together may be heard some distance away. The amount of the load which a stream can transport depends on its velocity. A current of 2/3 of a mile per hour can move fine sand, while one of 4 miles per hour sweeps along pebbles as large as hens' eggs. The transporting power of a stream varies as the 6th power of its velocity. If its velocity is multiplied by 2, its transporting power is multiplied by the 6th power of 2. It can now move stones 64 times as large as it could before. Stones weigh from 2 to 3 times as much as water, and in water lose the weight of the volume of water which they displace. What proportion, then, of their weight in air do stones lose when submerged? Measurement of stream loads. To obtain the total amount of waste transported by a river is an important but difficult matter. The amount of water discharged must first be found by multiplying the number of square feet in the average cross-section of the stream by its velocity per second, giving the discharge per second in cubic feet. The amount of silt to a cubic foot of water is found by filtering samples of the water taken from different parts of the stream and at different times in the year, and drying and weighing the residues. The average amount of silt to the cubic foot of water multiplied by the number of cubic feet of water discharged per year gives the total load carried in suspension during that time. Adding to this the estimated amount of sand and gravel rolled along the bed which in many swift rivers greatly exceeds the lighter material held in suspension, and adding also the total amount of dissolved solids, we reach the exceedingly important result of the total load of waste discharged by the river. Dividing the volume of this load by the area of the river basin gives another result of the greatest geological interest: the rate at which the region is being lowered by the combined action of weathering and erosion, or the rate of denudation. The rate of denudation of river basins. This rate varies widely. The Mississippi Basin may be taken as a representative land surface because of the varieties of surface, altitude, and slope, climate, and underlying rocks which are included in its great extent. Careful measurements show that the Mississippi Basin is now being lowered at a rate of 1/4000th of a foot a year, or 1 foot in 4,000 years. Taking this as the average rate of denudation for the land surfaces of the globe, estimates have been made of the length of time required at this rate to wash and wear the continents to the level of the sea. As the average elevation of the lands of the globe is reckoned at 2,411 feet, this result would occur in 9 or 10 million years if the present rate of denudation should remain unchanged. But even if no movements of the earth's crust should lift or depress the continents, the rate of wear and the removal of waste from their surfaces will not remain the same. It must constantly decrease as the lands are worn nearer to sea level and their slopes become more gentle. The length of time required to wear them away is therefore far in excess of that just stated. The drainage area of the Potomac is 11,000 square miles. The silt brought down in suspension in a year would cover a square mile to the depth of 4 feet. At what rate is the Potomac Basin being lowered from this cause alone? It is estimated that the upper Ganges is lowering its basin at the rate of 1 foot in 823 years, and the Po 1 foot in 720 years. Why so much faster than the Potomac and the Mississippi? How streams get their loads. The load of streams is derived from a number of sources, the larger part being supplied by the weathering of valley slopes. We have noticed how the mantle of waste creeps and washes to the streamways. Watching the runoff during a rain, as it hurries muddy with waste along the gutter or washes down the hillside, we may see the beginning of the route by which the larger part of their load is delivered to rivers. Streams also secure some of their load by wearing it from their beds and banks, a process called erosion. Erosion. Streams erode their beds chiefly by means of their bottom load, the stones of various sizes and the sand and even the fine mud which they sweep along. With these tools they smooth, grind, and rasp the rock of their beds, using them in much the fashion of sandpaper or a file. Weathering of river beds. The erosion of stream beds is greatly helped by the work of the weather. Especially at low water, more or less of the bed is exposed to the action of frost and heat and cold. Joints are opened, rocks are pried loose and broken up and made ready to be swept away by the stream at time of flood. Potholes. In rapids, streams also drill out their rocky beds. Where some slight depression gives rise to an eddy, the pebbles which gather in it are whirled round and round, and acting like the bit of an auger, bore out a cylindrical pit called a pothole. Potholes sometimes reach a depth of a score of feet. Where they are numerous, they aid materially in deepening the channel, as the walls between them are worn away and they coalesce. Waterfalls. One of the most effective means of erosion which the river possesses is the waterfall. The plunging water dislodges stones from the face of the ledge over which it pours, and often undermines it by excavating a deep pit at its base. Slice after slice is thus thrown down from the front of the cliff, and the cataract cuts its way upstream, leaving a gorge behind it. Niagara Falls. The Niagara River flows from Lake Erie at Buffalo in a broad channel, which it has cut but a few feet below the level of the region. Some 13 miles from the outlet, it plunges over a ledge 170 feet high into the head of a narrow gorge which extends for 7 miles to the escarpment of the upland in which the gorge is cut. The strata which compose the upland dip gently upstream and consist at top of a massive limestone, at the falls about 80 feet thick, and below of soft and easily weathered shale. Beneath the falls the underlying shale is cut and washed away by the descending water and retreats also because of weathering, while the overhanging limestone breaks down in huge blocks from time to time. Niagara is divided by Goat Island into the Horseshoe Falls and the American Falls. The former is supplied by the main current of the river, and from the semicircular sweep of its rim, a sheet of water in places at least 15 or 20 feet deep plunges into a pool a little less than 200 feet in depth. Here the force of the falling water is sufficient to move about the fallen blocks of limestone and use them in the excavation of the shale of the bed. At the American Falls, the lesser branch of the river, which flows along the American side of Goat Island, pours over the side of the gorge and breaks upon a high talus of limestone blocks which its smaller volume of water is unable to grind to pieces and remove. A series of surveys have determined that from 1842 to 1890 the Horseshoe Falls retreated at the rate of 2.8 feet per year, while the American Falls retreated at the rate of 0.64 feet in the same period. We cannot doubt that the same agency which is now lengthening the gorge at this rapid rate has cut it back its entire length of 7 miles. While Niagara Falls have been cutting back a gorge 7 miles long and from 200 to 300 feet deep, the river above the falls has eroded its bed scarcely below the level of the upland on which it flows. Like all streams, which are the outlets of lakes, the Niagara flows out of Lake Erie clear of sediment, as from a settling basin, and carries no tools with which to abrade its bed. We may infer from this instance how slight is the erosive power of clear water on hard rock. Assuming that the rate of recession of the combined volumes of the American and Horseshoe Falls was 3 feet a year below Goat Island, and assuming that this rate has been uniform in the past, how long is it since the Niagara River fell over the edge of the escarpment where now is the mouth of the present gorge? The profile of the bed of the Niagara along the gorge, figure 39, shows alternating deeps and shallows which cannot be accounted for, except in a single instance, by the relative hardness of the rocks of the riverbed. The deeps do not exceed that at the foot of the Horseshoe Falls at the present time. When the gorge was being cut along the shallows, how did the falls compare in excavating power, in force and volume with the Niagara of today? How did the rate of recession at those times compare with the present rate? Is the assumption made above that the rate of recession has been uniform, correct. The first stretch of shallows below the falls causes a tumultuous rapid impossible to sound. Its depth has been estimated at 35 feet. From what data could such an estimate be made? Suggest a reason why the Horseshoe Falls are convex upstream. At the present rate of recession, which will reach the head of Goat Island the sooner, the American or the Horseshoe Falls? What will be the fate of the falls left behind when the other has passed beyond the head of the island? The rate at which a stream erodes its bed depends in part upon the nature of the rocks over which it flows. Will a stream deepen its channel more rapidly on massive or on thin-bedded and close-jointed rocks, on horizontal strata or on strata steeply inclined? Deposition. While the river carries its invisible load of dissolved rock on without stop to the sea, its load of visible waste is subject to many delays en route. Now and again it is laid aside, to be picked up later and carried some distance further on its way. One of the most striking features of the river, therefore, is the waste accumulated along its course, in bars and islands on the channel, beneath its bed, and in floodplains along its banks. All this alluvium, to use a general term for river deposits, with which the valley is cumbered, is really en route to the sea. It is only temporarily laid aside to resume its journey later on. Constantly the river is destroying and rebuilding its alluvial deposits, here cutting and there depositing along its banks, here eroding and there building a bar, here excavating its bed and there filling it up, and at times carrying the material picked up at one point some distance on downstream before depositing it at another. These deposits are laid down by slackening currents where the velocity of the stream is checked, as on the inner side of curves, and where the slope of the bed is diminished, and in the lee of islands, bridge piers, and projecting points of land. How slight is the check required to cause a current to drop a large part of its load may be inferred from the law of the relation to the transporting power to the velocity. If the velocity is decreased 1/2, the current can move fragments but 1/64 the size of those which it could move before, and must drop all those of larger size. Will a river deposit more at low water or at flood, when rising or falling? Stratification. River deposits are stratified, as may be seen in any fresh cut in banks or bars. The waste of which they are built has been sorted and deposited in layers, one above another, some of finer and some of coarser material. The sorting action of running water depends on the fact that its transporting power varies with the velocity. A current whose diminishing velocity compels it to drop coarse gravel, for example, is still able to move all the finer waste of its load, and separating it from the gravel, carries it on downstream, while at a later time slower currents may deposit on the gravel bed layers of sand, and still later slack water may leave on these a layer of mud. In case of materials lighter than water, the transporting power does not depend on the velocity, and logs of wood, for instance, are floated on to the sea on the slowest as well as the most rapid currents. Cross-bedding. A section of a bar exposed at low water may show that it is formed of layers of sand or coarser stuff inclined downstream as steeply often as the angle of repose of the material. From a boat anchored over the lower end of a submerged sandbar, we may observe the way in which this structure, called crossbedding, is produced. Sand is continually pushed over the edge of the bar at B, figure 42, and comes to rest in successive layers on the sloping surface. At the same time, the bar may be worn away at the upper end, A, and thus slowly advance downstream. While the deposit is thus cross-bedded, it constitutes as a whole a stratum whose upper and lower surfaces are about horizontal. In sections of riverbanks, one may often see a vertical succession of cross-bedded strata, each built in the way described. Water wear. The coarser material of river deposits, such as cobblestones, gravel, and the larger grains of sand, are water-worn, or rounded, except when near their source. Rolling along the bottom, they have been worn round by impact and friction as they rubbed against one another and the rocky bed of the stream. Experiments have shown that angular fragments of granite lose nearly half their weight and become well rounded after travelling 15 miles in rotating cylinders partly filled with water. Marbles are cheaply made in Germany out of small limestone cubes set revolving in a current of water between a rotating bed of stone and a block of oak, the process requiring but about 15 minutes. It has been found that in the upper reaches of mountain streams a descent of less than a mile is sufficient to round pebbles of granite. Land forms due to river erosion. River valleys. In their courses to the sea, rivers follow valleys of various forms, some shallow and some deep, some narrow and some wide. Since rivers are known to erode their beds and banks, it is a fair presumption that, aided by the weather, they have excavated the valleys in which they flow. Moreover, a bird's-eye view or a map of a region shows the significant fact that the valleys of a system unite with one another in a branchwork, as twigs meet their stems and the branches of a tree its trunk. Each valley, from that of the smallest rivulet to that of the master stream, is proportionate to the size of the stream which occupies it. With a few explainable exceptions, the valleys of tributaries join that of the trunk stream at a level. There is no sudden descent or break in the bed at the point of juncture. These are the natural consequences which must follow if the land has long been worked upon by streams, and no other process has ever been suggested which is competent to produce them. We must conclude that valley systems have been formed by the river systems which drained them, aided by the work of the weather. They are not gaping fissures in the earth's crust, as early observers imagined, but are the furrows which running water has drawn upon the land. As valleys are made by the slow wear of streams and the action of the weather, they pass in their development through successive stages, each of which has its own characteristic features. We may therefore classify rivers and valleys according to the stage which they have reached in their life history from infancy to old age. End of Section 6, recorded by Uncommon.
Section 7 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton, Chapter 3, Part 2.
Young river valleys. Infancy. The Red River of the North, a region in northwest Minnesota, and the adjacent portions of North Dakota and Manitoba, was so recently covered by the waters of an extinct lake known as Lake Agassiz that the surface remains much as it was left when the lake was drained away. The flat floor, spread smooth with lake-laid silts, is still a plain, to the eye as level as the sea. Across it the Red River of the North and its branches run in narrow, ditch-like channels, steep-sided and shallow, not exceeding 60 feet in depth, their gradients differing little from the general slopes of the region. The trunk streams have but few tributaries. The river system, like a sapling with few limbs, is still undeveloped. Along the banks of the trunk streams, short gullies are slowly lengthening headwards, like growing twigs, which are sometime to become large branches. The flat interstream areas are as yet but little scored by drainage lines, and in wet weather water lingers in ponds in any initial depressions on the plain. Contours. In order to read the topographic maps of the textbook and the laboratory, the student should know that contours are lines drawn on maps to represent relief. All points on any given contour being of equal height above sea level. The contour interval is the uniform vertical distance between two adjacent contours and varies on different maps. To express regions of faint relief, a contour interval of 10 or 20 feet is commonly selected, while in mountainous regions a contour interval of 250, 500, or even 1,000 feet may be necessary in order that the contours may not be too crowded for easy reading. Whether a river begins its life on a lake plain, as in the example just cited, or on a coastal plain lifted from beneath the sea, or on a spread of glacial drift left by the retreat of continental ice sheets, such as covers much of Canada and the northeastern parts of the United States, its infantile stage presents the same characteristic features: a narrow and shallow valley, with undeveloped tributaries and undrained interstream areas. Groundwater stands high, and exuding in the undrained initial depressions forms marshes and lakes. Lakes. Lakes are perhaps the most obvious of these fleeting features of infancy. They are short-lived, for their destruction is soon accomplished by several means. As a river system advances towards maturity, the deepening and extending valleys of the tributaries lower the groundwater surface and invade the undrained depressions of the region. Lakes having outlets are drained away as their basin rims are cut down by the outflowing streams, a slow process where the rim is of hard rock, but a rapid one where it is of soft material such as glacial drift. Lakes are effaced also by the filling of their basins. Inflowing streams and the wash of rains bring in waste. Waves abrade the shore and strew the debris worn from it over the lake bed. Shallow lakes are often filled with organic matter from decaying vegetation. Does the outflowing stream from a lake carry sediment? How does this fact affect its erosive power on hard rock, on loose material? Lake Geneva is a well-known example of a lake in process of obliteration. The inflowing Rhone has already displaced the waters of the lake for a length of 20 miles, with the waste brought down from the high Alps. For this distance there extends up the Rhone valley an alluvial plain, which has grown lakeward at the rate of 1.5 miles since Roman times, as proved by the distance inland at which a Roman port now stands. How rapidly a lake may be silted up under exceptionally favourable conditions is illustrated by the fact that over the bottom of the artificial lake of 35 square miles formed behind the great dam across the Colorado River at Austin, Texas, sediments 39 feet deep gathered in 7 years. Lake Mendota, one of the many beautiful lakes of southern Wisconsin, is rapidly cutting back the soft glacial drift of its shores by means of the abrasion of its waves. While the shallow basin is thus broadened, it is also being filled with the waste, and the time is brought nearer when it will be so shoaled that vegetation can complete the work of its effacement. Along the margin of a shallow lake, mosses, water lilies, grasses, and other water-loving plants grow luxuriantly. As their decaying remains accumulate on the bottom, the ring of marsh broadens inward, the lake narrows gradually to a small pond set in the midst of a wide bog, and finally disappears. All stages in this process of extinction may be seen among the countless lakelets which occupy sags in the recent sheets of glacial drift in the northern states, and more numerous than the lakes which still remain are those already thus filled with carbonaceous matter derived from the carbon dioxide of the atmosphere. Such fossil lakes are marked by swamps or level meadows underlain with muck. The advance to maturity. The infantile stage is brief. As a river advances towards maturity, the initial depressions, the lake basins of its area, are gradually effaced. By the furrowing action of the rain wash and the headward lengthening of tributaries, a branchwork of drainage channels grows until it covers the entire area, and not an acre is left on which the fallen raindrop does not find already cut for it an uninterrupted downward path, which leads it on by way of gully, brook, and river to the sea. The initial surface of the land, by whatever agency it was modelled, is now wholly destroyed. The valley is all reduced to valley slopes. The longitudinal profile of a stream. This at first corresponds with the initial surface of the region on which the stream begins to flow, although its way may lead through basins and down steep descents. The successive profiles to which it reduces its bed are illustrated in Figure 51. As the gradient or rate of descent of its bed is lowered, the velocity of the river is decreased until its lessening energy is wholly consumed in carrying its load, and it can no longer erode its bed. The river is now at grade, and its capacity is just equal to its load. If now its load is increased, the stream deposits and thus builds up or aggrades its bed. On the other hand, if its load is diminished, it has energy to spare, and resuming its work of erosion, degrades its bed. In either case, the stream continues aggrading or degrading until a new gradient is found where the velocity is just sufficient to move the load, and here again it reaches grade. Valleys. Vigorous rivers, well armed with waste, make short work of cutting their beds to grade, and thus erode narrow, steep-sided gorges only wide enough at the base to accommodate the stream. The steepness of the valley slopes depends upon the relative rates at which the bed is cut down by the stream and the sides are worn back by the weather. In resistant rock, a swift, well-laden stream may saw out a gorge whose sides are nearly or even quite vertical. But as a rule, young valleys whose streams have not yet reached grade are V-shaped. Their sides flare at the top, because here the rocks have longest been opened up to the action of the weather. Some of the deepest canyons may be found where a rising landmass, either mountain range or plateau, has long maintained, by its continued uplift, the rivers of the region above grade. In the northern hemisphere, the north sides of river valleys are sometimes of more gentle slope than the south sides. Can you suggest a reason? The Grand Canyon of the Colorado River in Arizona. The Colorado River trenches the high plateau of northern Arizona with a colossal canyon 218 miles long and more than a mile in greatest depth. The rocks in which the canyon is cut are for the most part flat-lying, massive beds of limestones and sandstones, with some shales beneath which in places harder crystalline rocks are disclosed. Where the canyon is deepest, its walls have been profoundly dissected. Lateral ravines have widened into immense amphitheatres, leaving between them long ridges of mountain height, buttressed and rebuttressed with flanking spurs and carved into majestic architectural forms. From the extremity of one of these promontories, it is 2 miles or more across the gulf to the point of the one opposite, and the heads of the amphitheatres are 13 miles apart. The lower portion of the canyon is much narrower, figure 54, and its walls of dark crystalline rock sink steeply to the edge of the river, a swift, powerful stream a few hundred feet wide, turbid with reddish silt, by means of which it continually rasps its rocky bed as it hurries on. The Colorado is still deepening its gorge. In the Grand Canyon its gradient is 7 1/2 feet to the mile, but as in all ungraded rivers, the descent is far from uniform. Graded reaches in soft rock alternate with steeper declivities in hard rock, forming rapids such as, for example, a stretch of 10 miles where the fall averages 21 feet to the mile. Because of these dangerous rapids, the few exploring parties who have traversed the Colorado Canyon have done so at the hazard of their lives. The canyon has been shaped by several agencies. Its depth is due to the river, which has sawed its way far toward the base of a lofty rising plateau. Acting alone, this would have produced a slit-like gorge little wider than the breadth of the stream. The impressive width of the canyon and the magnificent architectural masses which fill it are owing to two causes. Running water has gulched the walls, and weathering has everywhere attacked and driven them back. The horizontal, harder beds stand out in long lines of vertical cliffs, often hundreds of feet in height, at whose feet talus slopes contain the outcrop of the weaker strata. As the upper cliffs have been sapped and driven back by the weather, broad platforms are left at their bases, and the sides of the canyon descend to the river by gigantic steps. Far up and down the canyon, the eye traces these horizontal layers like the flutings of an elaborate moulding, distinguishing each by its contour as well as by its color and thickness. The Grand Canyon of the Colorado is often and rightly cited as an example of the stupendous erosion which may be accomplished by a river, and yet the Colorado is a young stream, and its work is no more than well begun. It has not yet wholly reached grade, and the great task of the river and its tributaries, the task of levelling the lofty plateau to a low plain and of transporting it grain by grain to the sea, still lies almost entirely in the future. Waterfalls and rapids. Before the bed of a stream is reduced to grade, it may be broken by abrupt descents which give rise to waterfalls and rapids. Such breaks in a river's bed may belong to the initial surface over which it began its course. Still more commonly are they developed in the rock mass through which it is cutting its valley. Thus, whenever a stream leaves harder rocks to flow over softer ones, the latter are quickly worn below the level of the former, and a sharp change in slope with a waterfall or rapid results. At the time of flood, young tributaries with steeper courses than that of the trunk stream may bring down stones and finer waste which the gentler current cannot move along, and throw them as a dam across its way. The rapids thus formed are also ephemeral, for as the gradient of the tributaries is lowered, the main stream becomes able to handle the smaller and finer load which they discharge. A rare class of falls is produced where the minor tributaries of a young river are not able to keep pace with their master stream in the erosion of their beds because of their smaller volume, and thus join it by plunging over the side of its gorge. But as the river approaches grade and slackens its down-cutting, the tributaries sooner or later overtake it, and, effacing their falls, unite with it on a level. Waterfalls and rapids of all kinds are evanescent features of a river's youth. Like lakes, they are soon destroyed, and if any long time had already elapsed since their formation, they would have been obliterated already. Local base levels, that balanced condition called grade, where a river neither degrades its bed by erosion nor aggrades it by deposition, is first attained along reaches of soft rocks, ungraded outcrops of hard rocks remaining as barriers which give rise to rapids or falls. Until these barriers are worn away, they constitute local base levels, below which level the stream, up valley from them, cannot cut. They are eroded to grade one after another, beginning with the least strong, or the one nearest the mouth of the stream. In a similar way, the surface of a lake in a river's course constitutes for all inflowing streams a local base level, which disappears when the basin is filled or drained. Mature and old rivers. Maturity is the stage of a river's complete development and most effective work. The river system now has well under way its great task of wearing down the land mass which it drains and carrying it particle by particle to the sea. The relief of the land is now at its greatest, for the main channels have been sunk to grade, while the divides remain but little worn below their initial altitudes. Groundwater now stands low. The runoff washes directly to the streams, with the least delay and loss by evaporation in ponds and marshes. The discharge of the river is therefore at its height. The entire region is dissected by streamways. The area of valley slopes is now largest and sheds to the streams a heavier load of waste than ever before. At maturity, the river system is doing its greatest amount of work, both in erosion and in the carriage of water and of waste to the sea. Lateral erosion. On reaching grade, a river ceases to scour its bed, and it does not again begin to do so until some change in load or volume enables it to find grade at a lower level. On the other hand, a stream erodes its banks. At all stages in its history, and with graded rivers, this process, called lateral erosion or planation, is especially important. The current of a stream follows the outer side of all curves or bends in the channel, and on this side it excavates its bed the deepest and continually wears and saps its banks. On the inner side, deposition takes place in the more shallow and slower moving water. The inner bank of bends is thus built out while the outer bank is worn away. By swinging its curves against the valley sides, a graded river continually cuts a wider and wider floor. The V valley of youth is thus changed by planation to a flat floored valley with flaring sides which gradually become subdued by the weather to gentle slopes. While widening their valleys, streams maintain a constant width of channel, so that a wide floored valley does not signify that it ever was occupied by a river of equal width. The gradient. The gradients of graded rivers differ widely. A large river with a light load reaches grade on a faint slope, while a smaller stream, heavily burdened with waste, requires a steep slope to give it velocity sufficient to move the load. The Platte, a graded river of Nebraska, with its headwaters in the Rocky Mountains, is enfeebled by the semi-arid climate of the Great Plains, and surcharged with waste brought down both by its branches in the mountains and by those whose tracks lie over the soft rocks of the plains. It is compelled to maintain a gradient of 8 feet to the mile in western Nebraska. The Ohio reaches grade with a slope of less than 4 inches to the mile from Cincinnati to its mouth, and the powerful Mississippi washes along its load with a fall of but 3 inches per mile from Cairo to the Gulf. Other things being equal, which of graded streams will have the steeper gradient, a trunk stream or its tributaries, a stream supplied with gravel or one with silt? Other factors remaining the same, what changes would occur if the Platte should increase in volume? What changes would occur if the load should be increased in amount or in coarseness? The old age of rivers. As rivers pass their prime, as denudation lowers the relief of the region, less waste and finer is washed over the gentler slopes of the lowering hills. With smaller loads to carry, the rivers now deepen their valleys and find grade with fainter declivities nearer the level of the sea. This limit of the level of the sea beneath which they cannot erode is known as base level. Footnote: the term base level is also used to designate the close approximation to sea level to which streams are able to subdue the land. As streams grow old, they approach more and more closely to base level, although they are never able to attain it. Some slight slope is needed that water may flow and waste be transported over the land. Meanwhile, the relief of the land has ever lessened. The master streams and their main tributaries now wander with sluggish currents over the broad valley floors which they have planed away, while under the erosion of their innumerable branches and the wear of the weather, the divides everywhere are lowered and subdued to more and more gentle slopes. Mountains and high plateaus are thus reduced to rolling hills and at last to plains, surmounted only by such hills as may still be unreduced to the common level, because of the harder rocks of which they are composed, or because of their distance from the main erosion channels. Such regions of faint relief, worn down to near base level by sub-aerial great agencies, are known as peneplains, almost plains. Any residual masses which rise above them are called monadnocks, from the name of a conical peak of New Hampshire which overlooks the now uplifted peneplain of southern New England. In its old age, a region becomes mantled with thick sheets of fine and weathered waste, slowly moving over the faint slopes toward the waterways and unbroken by ledges of bare rock. In other words, the waste mantle also is now graded, and as waterfalls have been effaced in the riverbeds, So now any ledges in the wide streams of waste are worn away and covered beneath smooth slopes of fine soil. Groundwater stands high and may exude in areas of swamp. In youth, the land mass was rough-hewn and cut deep by stream erosion. In old age, the faint reliefs of the land dissolve away, chiefly under the action of the weather, beneath their cloak of waste. The cycle of erosion. The successive stages through which a land mass passes while it is being levelled to the sea constitute together a cycle of erosion. Each stage of the cycle from infancy to old age leaves, as we have seen, its characteristic records in the forms sculptured on the land, such as the shapes of valleys and the contours of hills and plains. The geologist is thus able to determine by the landforms of any region the stage in the erosion cycle to which it now belongs, and knowing what are the earlier stages of the cycle, to read something of the geological history of the region. Interrupted cycles. So long a time is needed to reduce a landmass to base level that the process is seldom, if ever, completed during a single uninterrupted cycle of erosion. Of all the various interruptions which may occur, the most important are gradual movements of the earth's crust, by which a region is either depressed or elevated relative to sea level. The depression of a region hastens its old age by decreasing the gradient of streams, by destroying their power to excavate their beds and carry their loads to a degree corresponding to the amount of the depression, and by lessening the amount of work they have to do. The slackened river currents deposit their waste in hood plains, which increase in height as the subsidence continues. The lower courses of the rivers are invaded by the sea and become estuaries, while the lower tributaries are cut off from the trunk stream. Elevation, on the other hand, increases the activity of all agencies of weathering, erosion and transportation, restores the region to its youth, and inaugurates a new cycle of erosion. Streams are given a steeper gradient, greater velocity, and increased energy to carry their loads and wear their beds. They cut through the alluvium of their floodplains, leaving it on either bank as successive terraces, and entrench themselves in the underlying rock. In their older and wider valleys they cut narrow, steep-walled inner gorges, in which they flow swiftly over rocky floors, broken here and there by falls and rapids where a harder layer of rock has been discovered. Winding streams on plains may thus incise their meanders in solid rock as the plains are gradually uplifted. Streams which are thus restored to their youth are said to be revived. As streams cut deeper and the valley slopes are steepened, the mantle of waste of the region undergoing elevation is set in more rapid movement. It is now removed particle by particle faster than it forms. As the waste mantle thins, weathering attacks the rocks of the region more energetically until an equilibrium is reached again. The rocks waste rapidly, and their waste is as rapidly removed. Dissected peneplains. When a rise of the land brings one cycle to an end and begins another, the characteristic landforms of each cycle are found together, and the topography of the region is composite until the second cycle is so far advanced that the landforms of the first cycle are entirely destroyed. The contrast between the land surfaces of the later and the earlier cycles is most striking when the earlier had advanced to age and the later is still in youth. Thus many peneplains which have been elevated and dissected have been recognized by the remnants of their ancient erosion surfaces and the length of time which has elapsed since their uplift has been measured by the stage to which the new cycle has advanced. The Piedmont Belt. As an example of an ancient peneplain uplifted and dissected, we may cite the Piedmont Belt, a broad upland lying between the Appalachian Mountains and the Atlantic coastal plain. The surface of the Piedmont is gently rolling. The divides, which are often smooth areas of considerable width, rise to a common plain, and from them one sees in every direction an even skyline, except where in places some lone hill or ridge may lift itself above the general level. Figure 62. The surface is an ancient one, for the mantle of residual waste lies deep upon it. Soils are reddened by long oxidation, and the rocks are rotted to a depth of scores of feet. At present, however, the waste mantle is not forming so rapidly as it is being removed. The streams of the upland are actively engaged in its destruction. They flow swiftly in narrow, rock-walled valleys over rocky beds. This contrast between the young streams and the aged surface which they are now so vigorously dissecting can only be explained by the theory that the region once stood lower than at present and has recently been upraised. If now we imagine the valleys refilled with the waste which the streams have swept away and the upland lowered, we restore the Piedmont region to the condition in which it stood before its uplift and dissection, a gently rolling plain surmounted here and there by isolated hills and ridges. The surface of the ancient Piedmont plain, as it may be restored from the remnants of it found on the divides, is not in accordance with the structures of the country rocks. Where these are exposed to view, they are seen to be far from horizontal. On the walls of river gorges they dip steeply and in various directions, and the streams flow over their upturned edges. As shown in Figure 67, the rocks of the Piedmont have been folded and broken and tilted. It is not reasonable to believe that when the rocks of the Piedmont were thus folded and otherwise deformed, the surface of the region was a plain. The upturned layers have not always stopped abruptly at the even surface of the Piedmont plain, which now cuts above them. They are the bases of great folds and tilted blocks which must once have risen high in air. The complex and disorderly structures of the Piedmont rocks are those seen in great mountain ranges, and there is every reason to believe that these rocks, after their deformation, rose to mountain height. The ancient Piedmont plain cuts across these upturned rocks as independently of their structure as the even surface of the sawed stump of some great tree is independent of the direction of its fibres. Hence the Piedmont plain, as it was before its uplift, was not a coastal plain formed of strata spread in horizontal sheets beneath the sea and then uplifted, nor was it a structural plain due to the resistance of erosion from some hard, flat-lying layer of rock. Even surfaces developed on rocks of discordant structure, such as the Piedmont shows, are produced by long denudation, and we may consider the Piedmont as a peneplain formed by the wearing down of mountain ranges and recently uplifted. The Laurentian peneplain. This is the name given to a denuded surface on very ancient rocks which extends from the Arctic Ocean to the St. Lawrence River and Lake Superior, with small areas also in northern Wisconsin and New York. Throughout this U-shaped area, which encloses Hudson Bay within its arms, the country rocks have the complicated and contorted structures which characterize mountain ranges. But the surface of the area is by no means mountainous. The skyline, when viewed from the divides, is unbroken by mountain peaks or rugged hills. The surface of the arm west of Hudson Bay is gently undulating, and that of the eastern arm has been roughened to low rolling hills and dissected in places by such deep river gorges as those of the Ottawa and Saguenay. This immense area may be regarded as an ancient peneplain truncating the bases of long-vanished mountains and dissected after elevation. In the examples cited, the uplift has been a broad one, and to comparatively little height. Where peneplains have been uplifted to great height and have since been well dissected, and where they have been upfolded and broken and up-tilted, their recognition becomes more difficult. Yet recent observers have found evidences of ancient lowland surfaces of erosions on the summits of the Allegheny Ridges, the Cascade Mountains, figure 69, and the western slope of the Sierra Nevadas. The Southern Appalachian region. We have here an example of an area the latter part of whose geological history may be deciphered by means of its landforms. The generalized section of figure 70, which passes from west to east across a portion of the region in eastern Tennessee, shows on the west a part of the broad Cumberland Plateau. On the east is a roughened upland platform, from which rise in the distance the peaks of the Great Smoky Mountains. The plateau, consisting of strata but little changed from their original flat-lying attitude, and the platform developed on rocks of disordered structure made crystalline by heat and pressure, both stand at the common level of the line AB. They are separated by the Appalachian Valley, 40 miles wide, cut in strata which have been folded and broken into long, narrow blocks. The valley is traversed lengthwise by long, low ridges. The outcropping edges of the harder strata, which rise to about the same level, that of the line CD, between these ridges stretch valley lowlands at the level EF, excavated in the weaker rocks, while somewhat below them lie the channels of the present streams, now busily engaged in deepening their beds. The valley lowlands, were they planed by graded or ungraded streams? Have the present streams reached grade? Why did the streams cease widening the floors of the valley lowlands? How long since? When will they begin anew the work of lateral planation? What effect will this have on the ridges if the present cycle of erosion continues long uninterrupted? The ridges of the Appalachian Valley. Why do they stand above the valley lowlands? Why do their summits lie in about the same plane? Refilling the valleys intervening between these ridges with the material removed by the streams, what is the nature of the surface thus restored? Does this surface, CD, accord with the rock structures on which it has been developed? How may it have been made? At what height did the land stand then, compared with its present height? What elevations stood above the surface, CD? Why? What name may you use to designate them? How does the length of time needed to develop the surface CD compared with that needed to develop the valley lowlands? The platform and plateau, why do they stand at a common level AB? Of what surface may they be remnants? Is it accordant with the rock structure? How was it produced? What unconsumed masses overlooked it? Did the rocks of the Appalachian Valley stand above this surface when it was produced? Did they then stand below it? Compare the time needed to develop this surface with that needed to develop CD. Which surface is the older? How many cycles of erosion are represented here? Give the erosion history of the region by cycles, beginning with the oldest, the work done in each, and the work left undone. What brought each cycle to a close, and how long, relatively, it continued. End of section 7.
Section 8 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. The Elements of Geology by William Harmon Norton. Chapter 4, Part 8. River deposits. The characteristic features of river deposits and the forms which they assume may be treated under 3 heads: 1. Valley deposits, 2. Basin deposits, and 3. Deltas. Valley deposits. Floodplains are the surfaces of the alluvial deposits, which streams build along their courses at times of flood. A swift current then sweeps along the channel, while a shallow sheet of water moves slowly over the floodplain, spreading upon it a thin layer of sediment. It has been estimated that each inundation of the Nile leaves a layer of fertilizing silt 0.03 of an inch thick over the floodplain of Egypt. Floodplains may consist of a thin spread of alluvium over the flat rock floor of a valley which is being widened by the lateral erosion of a graded stream. Floodplain deposits of great thickness may be built by aggrading rivers even in valleys whose rock floors have never been thus widened. A cross-section of a floodplain shows that it is highest next the river, sloping gradually thence to the valley sides. These wide natural embankments are due to the fact that the river deposit is heavier near the bank, where the velocity of the silt-laden channel current is first checked by contact with the slower-moving overflow. Thus banked off from the stream, the outer portions of a floodplain are often ill-drained and swampy, and here vegetal deposits such as peat may be interbedded with river silts. A map of a wide floodplain such as that of the Mississippi or the Missouri shows that the courses of the tributaries on entering it are deflected downstream. Why? The aggrading streams by which floodplains are constructed gradually build their immediate banks and beds to higher and higher levels, and therefore find it easy at times of great floods to break their natural embankments and take new courses over the plain. In this way they aggrade each portion of it in turn by means of their shifting channels. Braided channels. A river actively engaged in aggrading its valley with coarse waste builds a floodplain of comparatively steep gradient, and often flows down it in a fairly direct course and through a network of braided channels. From time to time a channel becomes choked with waste, and the water, no longer finding room in it, breaks out and cuts and builds itself a new way which reunites down valley with the other channels. Thus there becomes established a network of ever-changing channels enclosing low islands of sand and gravel. Terraces. While aggrading streams thus tend to shift their channels, degrading streams, on the contrary, become more and more deeply entrenched in their valleys. It often occurs that a stream, after having built a floodplain, ceases to aggrade its bed because of a lessened load or for other reasons, such as an uplift of the region, and begins instead to degrade it. It leaves the original floodplain out of reach of even the highest floods. When again it reaches grade at a lower level, it produces a new floodplain by lateral erosion in the older deposits, remnants of which stand as terraces on one or both sides of the valley. In this way a valley may be lined with a succession of terraces at different levels, each level representing an abandoned floodplain. Meanders. Valleys aggraded with fine waste from well-nigh level plains over which streams wind from side to side of a direct course in symmetric bends, known as meanders. from the name of a winding river of Asia Minor. The giant Mississippi has developed meanders with a radius of 1½ miles, but a little creek may display on its meadow as perfect curves only a rod or so in radius. On the floodplain of either river or creek we may find examples of the successive stages in the development of the meander, from its beginning in a slight initial bend sufficient to deflect the current against the other side. Eroding here and depositing on the inner side of the bend, it gradually reaches first the open bend, whose width and length are not far from equal, and later that of the horseshoe meander, whose diameter, transverse to the course of the stream, is much greater than that parallel with it. Little by little the neck of land projecting into the bend is narrowed, until at last it is cut through, and a cut-off is established. The old channel is now silted up at both ends, and becomes a crescentic lagoon, or oxbow lake, which fills gradually to an arc-shaped shallow depression. Floodplains characteristic of mature rivers. On reaching grade, a stream plains a flat floor for its continually widening valley. Ever cutting on the outer bank of its curves, it deposits on the inner bank scroll-like floodplain patches. For a while the valley bluffs do not give its growing meanders room to develop to their normal size, but as planation goes on, the bluffs are driven back to the full width of the meander belt, and still later to a width which gives room for broad stretches of floodplain on either side. Usually a river first attains grade near its mouth, and here first sinks its bed to near base level. Extending its graded course upstream by cutting away barrier after barrier, it comes to have a widened and mature valley over its lower course, while its young headwaters are still busily eroding their beds. Its ungraded branches may thus bring down to its lower course more waste than it is competent to carry on to the sea, and here it aggrades its bed and builds a floodplain in order to gain a steeper gradient and velocity enough to transport its load. As maturity is passed and the relief of the land is lessened, a smaller and smaller load of waste is delivered to the river. It now has energy to spare, and again degrades its valley, excavating its former floodplains and leaving them in terraces on either side, and at last, in its old age, sweeping them away. Alluvial cones and fans. In hilly mountainous countries one often sees on a valley side a conical or fan-shaped deposit of waste at the mouth of a lateral stream. The cause is obvious. The young branch has not been able as yet to wear its bed to accordant level with the already deepened valley of the master stream. It therefore builds its bed to grade at the point of juncture by depositing here its load of waste, a load too heavy to be carried along the more gentile profile of the trunk valley. Where rivers descend from a mountainous region upon the plain, they may build alluvial fans of exceedingly gentle slope. Thus the rivers of the western side of the Sierra Nevada mountains have spread fans with a radius of as much as 40 miles and a slope too slight to be detected without instruments, where they leave the rock-cut canyons in the mountains and descend upon the broad central valley of California. As a river flows over its fan, it commonly divides into a branchwork of shifting channels called distributaries, since they lead off the water from the main stream. In this way each part of the fan is graded and its symmetric form is preserved. Piedmont Plains. Mountain streams may build their confluent fans into widespread Piedmont (foot of the mountain) alluvial plains. These are especially characteristic of arid lands, where the streams wither as they flow out upon the thirsty lowlands, and are therefore compelled to lay down a large portion of their load. In humid climates, mountain-borne streams are usually competent to carry their loads of waste on to the sea, and have energy to spare to cut the lower mountain slopes into foothills. In arid regions, foothills are commonly absent, and the ranges rise, as from pedestals, above broad sloping plains of stream-laid waste. The High Plains. The rivers which flow eastward from the Rocky Mountains have united their fans in a continuous sheet of waste which stretches forward from the base of the mountains for hundreds of miles, and in places is 500 feet thick. That the deposit was made in ancient times on land and not in the sea is proved by the remains which it contains of land animals and plants of species now extinct. That it was laid by rivers and not by freshwater lakes is shown by its structure. Wide stretches of flat-lying clays and sands are interrupted by long, narrow belts of gravel which mark the channels of the ancient streams. Gravels and sands are often cross-bedded, and their well-worn pebbles may be identified with the rocks of the mountains. After building this sheet of waste, the streams ceased to aggregate and began the work of destruction. Large uneroded remnants, their surfaces flat as a floor, remain as the high plains of western Kansas and Nebraska. River deposits in subsiding troughs. To a geologist the most important river deposits are those which gather in areas of gradual subsidence. They are often of vast extent and immense thicknesses, and such deposits of past geological ages have not infrequently been preserved, with all their records of the times in which they were built, by being carried below the level of the sea to be brought to light by a later uplift. On the other hand, river deposits which remain above base levels of erosion are swept away comparatively soon. The Great Valley of California is a monotonously level plain of great fertility, 400 miles in length and 50 miles in average width, built of waste swept down by streams from the mountain ranges which enclose it, the Sierra Nevada on the east and the Coast Range on the west. On the waste slopes at the foot of the bordering hills, coarse gravels and even boulders are left, while over the interior the slow-flowing streams at times of flood spread wide sheets of silt. Organic deposits are now forming by the decay of vegetation in swampy tuile, reed lands and in shallow lakes which occupy depressions left by the aggrading streams. Deep borings show that this great trough is filled to a depth of at least 2,000 feet below sea level with recent unconsolidated sands and silts containing logs of wood and freshwater shells. These are land deposits, and the absence of any marine deposits among them proves that the region has not been invaded by the sea since the accumulation began. It has therefore been slowly subsiding, and its streams, although continually carried below grade, have yet been able to aggregate the surface as rapidly as the region sank, and have maintained it, as at present, slightly above sea level. The Indo-Gangetic Plain, spread by the Brahmaputra, the Ganges, and the Indus river systems, stretches for 1,600 miles along the southern base of the Himalaya Mountains and occupies an area of 300,000 square miles. It consists of the floodplains of the master streams and the confluent fans of the tributaries which issue from the mountains on the north. Large areas are subject to overflow each season of flood, and still larger tracts mark abandoned floodplains below which the rivers have now cut their beds. The plain is built of far-stretching beds of clay, penetrated by streaks of sand, and also of gravel near the mountains. Beds of impure peat occur in it, and contain freshwater shells and the bones of land animals of species now living in northern India. At Lucknow an artesian well was sunk to 1,000 feet below sea level without reaching the bottom of these river-laid sands and silts, proving a slow subsidence with which the aggrading rivers have kept pace. Warped valleys. It is not necessary that an area should sink below sea level in order to be filled with stream-swept waste. High valleys among growing mountain ranges may suffer warping, or may be blockaded by rising mountain folds athwart them. Where the deformation is rapid enough, the river may be ponded and the valley filled with lake-laid sediments. Even when the river is able to maintain its right of way, it may yet have its declivity so lessened that it is compelled to aggravate its course continually, filling the valley with river deposits which may grow to an enormous thickness. Behind the outer ranges of the Himalaya Mountains lie several waste-filled valleys, the largest of which are Kashmir and Nepal, the former being an alluvial plain about as large as the state of Delaware. The rivers which drain these plains have already cut down their outlet gorges sufficiently to begin the task of the removal of the broad accumulations which they have brought in from the surrounding mountains. Their present flood plains lie as much as some hundreds of feet below wide alluvial terraces which mark their former levels. Indeed, the horizontal beds of the Hundi's Valley have been trenched to the depth of nearly 3,000 feet by the Sutlej River. These deposits are recent or sub-recent, for there have been found at various levels the remains of land plants and land and freshwater shells, and in some the bones of such animals as the hyena and the goat, of species or genera now living. Such soft deposits cannot be expected to endure through any considerable length of future time the rapid erosion to which their great height above the level of the sea will subject them. Characteristics of river deposits. The examples just cited teach clearly the characteristic features of extensive river deposits. These deposits consist of broad, flat-lying sheets of clay and fine sand left by the overflow at time of flood, and traversed here and there by long, narrow strips of coarse, cross-bedded sands and gravels thrown down by the swifter currents of the shifting channels. Occasional beds of muck mark the sites of shallow lakelets or freshwater swamps. The various strata also contain some remains of the countless myriads of animals and plants which live upon the surface of the plain, as it is in process of building. River shells such as the mussel, land shells such as those of snails, the bones of fishes and of such land animals as suffer drowning at times of flood, or are mired in swampy places, logs of wood, and the stems and leaves of plants, are examples of the variety of the remains of land and freshwater organisms which are entombed in river deposits and sealed away as a record of the life of the time, and as proof that the deposits were laid by streams and not beneath the sea. Basin deposits. Deposits in dry basins. On desert areas without outlet to the sea, as on the Great Basin of the United States and the deserts of Central Asia, stream-swept waste accumulates indefinitely. The rivers of the surrounding mountains, fed by the rains and melting snows of these comparatively moist elevations, dry and soak away as they come down upon the arid plains. They are compelled to lay aside their entire load of waste, eroded from the mountain valleys, in fans which grow to enormous size, reaching in some instances thousands of feet in thickness. The monotonous levels of Turkestan include vast alluvial tracts now in process of building by the floods of the frequently shifting channels of the Oxus and other rivers of the region. For about 700 miles from its mouth in Aral Lake, the Oxus receives no tributaries, since even the larger branches of its system are lost in a network of distributaries and choked with desert sands before they reach their master stream. These aggrading rivers, which have channels but no valleys, spread their muddy floods, which, in the case of the Oxus, sometimes equal the average volume of the Mississippi, far and wide over the plain, washing the bases of the desert dunes. Playas. In arid interior basins the central depressions may be occupied by playas, plains of fine mud washed forward from the margins. In the wet season the playa is covered with a thin sheet of muddy water, a playa lake supplied usually by some stream at flood. In the wet season the playa is covered with a thin sheet of muddy water, a playa lake, supplied usually by some stream at flood. In the dry season the lake evaporates, the river which fed it retreats, and there is left to view a hard, smooth, level floor of sun-baked and sun-cracked yellow clay, utterly devoid of vegetation. In the Black Rock Desert of Nevada, a playa lake spreads over an area 50 miles long and 20 miles wide. In summer it disappears. The Quinn River, which feeds it, shrinks back 100 miles towards its source, leaving an absolutely barren floor of clay, level as the sea. Lake deposits. Regarding lakes as parts of river systems, we may now notice the characteristic features of the deposits in lake basins. Soundings in lakes of considerable size and depth show that their bottoms are being covered with fine clays. Sand and gravel are found along their margins, being brought in by streams and worn by waves from the shore, but there are no tidal or other strong currents to sweep coarse waste out from the shore to any considerable distance. Where fine clays are now found on the land in even horizontal layers containing the remains of freshwater animals and plants, uncut by channels tilled with cross-bedded gravels and sands, and bordered by beach deposits of coarse waste, we may safely infer the existence of ancient lakes. Marl. Marl is a soft, whitish deposit of carbonate of lime, mingled often with more or less of clay, accumulated in small lakes whose feeding springs are charged with carbonate of lime, and into which little waste is washed from the land. Such lakelets are not infrequent on the surface of the younger drift sheets of Michigan and northern Indiana, where their beds of marl, sometimes as much as 40 feet thick, are utilized in the manufacture of Portland cement. The deposit, resulting from the decay of certain aquatic plants, which secrete lime carbonate from the water, from the decomposition of the calcareous shells of tiny mollusks, which live in countless numbers on the lake floor, and in some cases apparently from chemical precipitation. Peat. We have seen how lakelets are extinguished by the decaying remains of the vegetation which they support. A section of such a fossil lake shows that below the growing mosses and other plants of the surface of the bog lies a spongy mass composed of dead vegetable tissue, which passes downward gradually into peat, a dense, dark brown, carbonaceous deposit in which, to the unaided eye, little or no trace of vegetable structure remains. When dried, peat forms a fuel of some value, and is used either cut into slabs and dried, or pressed into bricks by machinery. When vegetation decays in open air, the carbon of its tissues, taken from the atmosphere by the leaves, is oxidized and returned to it in its original form of carbon dioxide. But decomposing in the presence of water, as in a bog, where the oxygen of the air is excluded, the carbonaceous matter of plants accumulates in deposits of peat. Peat bogs are numerous in regions lately abandoned by glacier ice, where river systems are so immature that the initial depressions left in the sheet of drift spread over the country have not yet been drained. 1/10 of the surface of Ireland is said to be covered with peat, and small bogs abound in the drift-covered area of New England and the States lying as far west as the Missouri River. In Massachusetts alone it has been reckoned that there are 15 billion cubic feet of peat, the largest bog occupying several thousand acres. Much larger swamps occur on the young coastal plain of the Atlantic from New Jersey to Florida. The Dismal Swamp, for example, in Virginia and North Carolina, is 40 miles across. It is covered with a dense growth of water-loving trees, such as the cypress and black gum. The center of the swamp is occupied by Lake Drummond, a shallow lake several miles in diameter, with banks of pure peat, and still narrowing from the encroachment of vegetation along its borders. Salt lakes. In arid climates a lake rarely receives sufficient inflow to enable it to rise to the basin rim and find an outlet. Before this height is reached, its surface becomes large enough to discharge by evaporation into the dry air the amount of water that is supplied by streams. As such a lake has no outlet, the minerals in solution brought into it by its streams cannot escape from the basin. The lake water becomes more and more heavily charged with such substances as common salt, and the sulphates and carbonates of lime, of soda, and of potash, and these are thrown down from solution one after another as the point of saturation for each mineral is reached. Carbonate of lime, the least soluble and often the most abundant mineral brought in, is the first to be precipitated. As concentration goes on, gypsum, which is insoluble in a strong brine, is deposited, and afterwards common salt. As the saltiness of the lake varies with the seasons and with climatic change, gypsum and salt are laid in alternate beds and are interleaved with sedimentary clays spread from the waste brought in by streams at times of flood. Few forms of life can live in bodies of salt water so concentrated that chemical deposits take place, and hence the beds of salt, gypsum, and silt of such lakes are quite barren of the remains of life. Similar deposits are precipitated by the concentration of sea water in lagoons and arms of the sea cut off from the ocean. Lakes Bonneville and Lahontan. These names are given to extinct lakes which once occupied large areas in the Great Basin, the former in Utah, the latter in northwestern Nevada. Their records remain in old horizontal beach lines which they drew along their mountainous shores at the different levels at which they stood, and in the deposits of their beds. At its highest stage, Lake Bonneville, then 1,000 feet deep, overflowed to the north and was a freshwater lake. As it shrank below the outlet, it became more and more salty, and the Great Salt Lake, its withered residue, is now depositing salt along its shores. In its strong brine, lime carbonate is insoluble, and that brought in by streams is thrown down at once in the form of travertine. Lake Lahontan never had an outlet. The first chemical deposits to be made along its shores were deposits of travertine, in places 80 feet thick. Its floor is spread with fine clays, which must have been laid in deep, still water, and which are charged with the salts absorbed by them, as the briny water of the lake dried away. These sedimentary clays are in two divisions, the upper and lower, each being about 100 feet thick. They are separated by heavy deposits of well-rounded, cross-bedded gravels and sands, similar to those spread at the present time by intermittent streams of arid regions. A similar record is shown in the old floors of Lake Bonneville. What conclusions do you draw from these facts as to the history of these ancient lakes? Deltas. In the river deposits which are left above sea level, particles of waste are allowed to linger only for a time. From alluvial fans and flood plains they are constantly being taken up and swept further on downstream. Although these landforms may long persist, the particles which compose them are ever changing. We may therefore think of the alluvial deposits of a valley as a stream of waste fed by the waste mantle as it creeps and washes down the valley sides, and slowly moving onwards to the sea. In basins, waste finds a longer rest, but sooner or later lakes and dry basins are drained or filled, and their deposits, if above sea level, resume their journey to their final goal. It is only when carried below the level of the sea that they are indefinitely preserved. On reaching this terminus, rivers deliver their load to the ocean. In some cases the ocean is able to take it up by means of strong tidal and other currents, and to dispose of it in ways in which we shall study later. But often the load is so large, or the tides are so weak, that much of the waste which the river brings in settles at its mouth, there building up a deposit called the delta, from the Greek letter of that name, whose shape it sometimes resembles. Deltas and alluvial fans have many common characteristics. Both owe their origin to a sudden check in the velocity of the river, compelling a deposit of the lode. Both are triangular in outline, the apex pointing upstream, and both are traversed by distributaries which build up all parts in turn. In a delta we may distinguish deposits of two distinct kinds, the submarine and the subaerial. In part a delta is built of waste brought down by the river and redistributed and spread by waves and tides over the sea bottom adjacent to the river's mouth. The origin of these deposits is recorded in the remains of marine animals and plants which they contain. As the submarine delta grows near to the level of the sea, the distributaries of the river cover it with subaerial deposits altogether similar to those of the floodplain, of which indeed the subaerial delta is the prolongation. Here extended deposits of peat may accumulate in swamps, and the remains of land and freshwater animals and plants swept down by the stream are embedded in the silts laid at times of flood. Borings made in the deltas of great rivers such as the Mississippi, the Ganges, and the Nile show that the subaerial portion often reaches a surprising thickness. Layers of peat, old soils, and forest grounds with the stumps of trees are discovered hundreds of feet below sea level. In the Nile delta some 8 layers of coarse gravel were found interbedded with river silts, and in the Ganges delta at Calcutta a boring nearly 500 feet in depth stopped in such a layer. The Mississippi has built a delta of 12,300 square miles, and is pushing the natural embankments of its chief distributaries into the Gulf at a maximum rate of a mile in 16 years. Muddy shoals surround its front. Shallow lakes, example, Lakes Pontchartrain and Bourne, are formed between the growing delta and the old shoreline, and elongate lakes and swamps are enclosed between the natural embankments of the distributaries. The delta of the Indus River, India, lies so low along the shore that a broad tract of country is overflowed by the highest tides. The submarine portion of the delta has been built to near sea level over so wide a belt offshore that in many places large vessels cannot come within sight of land because of the shallow water. A former arm of the sea, the Rann of Kutch, adjoining the delta on the east, has been silted up, and is now an immense barren flat of sandy mud 200 miles in length and 100 miles in greatest breadth. Each summer it is flooded with salt water, when the sea is brought in by strong southwesterly monsoon winds, and the climate during the remainder of the year is hot and dry. By the evaporation of sea water the soil is thus left so salty that no vegetation can grow upon it, and in places beds of salt several feet in thickness have accumulated. Under like conditions, salt beds of great thickness have been formed in the past, and are now found buried among the deposits of ancient deltas. Subsidence of great deltas. As a rule, great deltas are slowly sinking. In some instances, upbuilding by river deposits has gone on so rapidly as the region has subsided. The entire thickness of the Ganges delta, for example, so far as it has been sounded, consists of deposits laid in open air. In other cases, interbedded limestones and other sedimentary rocks containing marine fossils prove that at times subsidence has gained on the upbuilding, and the delta has been covered with the sea. It is by gradual depression that delta deposits attain enormous thickness, and, being lowered beneath the level of the sea, are safely preserved from erosion until a movement of the earth's crust in the opposite direction lifts them to form part of the land. We shall read later, in the hard rocks of our continent, the records of such ancient deltas, and we shall not be surprised to find them as thick as those now building at the mouths of the great rivers. Lake deltas. Deltas are also formed where streams lose their velocity on entering the still waters of lakes. The shorelines of extinct lakes, such as Lake Agassiz and Lakes Bonneville and Lahontan, may be traced by the heavy deposits at the mouths of their tributary streams. We have seen that the work of streams is to drain the lands of the water poured upon them by the rainfall, to wear them down, and to carry their wastes away to the sea, there to be rebuilt by other agents into sedimentary rocks. The ancient strata of which the continents are largely made are composed chiefly of material thus worn from still more ancient lands with their hills and valleys like those of today, and carried by their rivers to the ocean. In all geological times, as at the present, the work of streams has been to destroy the lands, and in so doing to furnish the ocean the materials from which the lands of future ages were to be made. Before we consider how the waste of the land brought in by streams is rebuilt upon the ocean floor, we must now proceed to study the work of two agents, glacier ice and the wind, which co-operate with rivers in the denudation of the land. End of section 8.
Section 9 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avahi in September 2010. The Elements of Geology by William Harmon Norton. Chapter 5, Part 1. The work of glaciers. The drift. The surface of northeastern North America, as far south as the Ohio and Missouri rivers, is generally covered by the drift, a formation which is quite unlike any which we have so far studied. A section of it, such as that illustrated in Figure 87, shows that for the most part it is unstratified, consisting of clay, sand, pebbles, and even large boulders, all mingled pell-mell together. The agent which laid the drift is one which can carry a load of material of all sizes, from the largest boulder to the finest clay, and deposit it without sorting. The stones of the drift are of many kinds. The region from which it was gathered may well have been large in order to supply these many different varieties of rocks. Pebbles and boulders have been left far from their original homes, as may be seen in southern Iowa, where the drift contains nuggets of copper brought from the region about Lake Superior. The agent which laid the drift is one able to gather its load over a large area and carry it a long way. The pebbles of the drift are unlike those rounded by running water or by waves. They are marked with scratches. Some are angular, many have had their edges blunted, while others have been ground flat and smooth on one or more sides, like gems which have been faceted by being held firmly against the lapidary's wheel. In many places the upper surface of the country rock beneath the drift has been swept clean of residual clays and other waste. All rock rotten has been planed away, and the ledges of sound rock to which the surface has been cut down have been rubbed smooth and scratched with long, straight, parallel lines. The agent which laid the drift can hold sand and pebbles firmly in its grasp, and can grind them against the rock beneath, thus planing it down and scoring it, while faceting the pebbles also. Neither water nor wind can do these things. Indeed, nothing like the drift is being formed by any process now at work anywhere in the eastern United States. To find the agent which has laid this extensive formation, we must go to a region of different climatic conditions. The inland ice of Greenland. Greenland is about 1,500 miles long and nearly 700 miles in greatest width. With the exception of a narrow fringe of mountainous coastland, it is completely buried beneath a sheet of ice, in shape like a vast white shield, whose convex surface rises to a height of 9,000 feet above the sea. The few explorers who have crossed the ice cap found it a trackless desert, destitute of all life save such lowly forms as the microscopic plant which produces the so-called red snow. On the smooth plain of the interior no rock waste relieves the snow's dazzling whiteness, no streams of running water are seen. The silence is broken only by howling storm winds and the rustle of the surface snow which they drive before them. Sounding with long poles, explorers find that below the powdery snow of the latest snowfall lie successive layers of earlier snows, which grow more and more compact downward, and at last have altered to impenetrable ice. The ice cap formed by the accumulated snows of uncounted centuries may well be more than a mile in depth. Ice thus formed by the compacting of snow is distinguished when in motion as glacier ice. The inland ice of Greenland moves. It flows with imperceptible slowness under its own weight, like a mass of some viscous or plastic substance, such as pitch or molasses candy, in all directions outward toward the sea. Near the edge it has so thinned that mountain peaks are laid bare, these islands in the sea of ice being known as nunataks. Down the valley of the coastal belt it drains in separate streams of ice, or glaciers. The largest of these reach the sea at the head of inlets, and are therefore called tide glaciers. Their fronts stand so deep in sea water that there is visible seldom more than 300 feet of the wall of ice, which in many glaciers must be 2,000 and more feet high. From the sea walls of tide glaciers great fragments break off and float away as icebergs. Thus, snows which fell in the interior of this northern land, perhaps many thousands of years ago, are carried in the form of icebergs to melt at last in the North Atlantic. Greenland, then, is being modeled over the vast extent of its interior, not by streams of running water, as are regions in warm and humid climates, nor by currents of air, as are deserts to a large extent, but by a sheet of flowing ice. What the ice sheet is doing in the interior we may infer from a study of the separate glaciers into which it breaks at its edge. The smaller Greenland glaciers. Many of the smaller glaciers of Greenland do not reach the sea, but deploy on plains of sand and gravel. The edges of these ice tongues are often as abrupt as if sliced away with a knife, and their structure is thus readily seen. They are stratified, their layers representing in part the successive snowfalls of the interior of the country. The upper layers are commonly white and free from stones, but the lower layers, to the height of 100 feet or more, are dark with debris which is being slowly carried on. So thickly studded with stones is the base of the ice that it is sometimes difficult to distinguish it from the rock waste which has been slowly dragged beneath the glacier or left about its edges. The waste beneath and about the glacier is unsorted. The stones are of many kinds, and numbers of them have been ground to flat faces. Where the front of the ice has retreated, the rock surface is seen to be planed and scored in places by the stones frozen fast in the soul of the glacier. We have now found in glacier ice an agent able to produce the drift of North America. The ice sheet of Greenland is now doing what we have seen was done in the recent past in our own land. It is carrying for long distances rocks of many kinds, gathered, we may infer, over a large extent of country. It is laying down its load without assortment in unstratified deposits. It grinds down and scores the rock over which it moves, and in the process many of the pebbles of its load are themselves also ground smooth and scratched. Since this work can be done by no other agent, we must conclude that the northeastern part of our own continent was covered in the recent past by glacier ice, as Greenland is today. Valley glaciers. The work of glacier ice can be most conveniently studied in the separate ice streams which creep down mountain valleys in many regions such as Alaska, the western mountains of the United States and Canada, the Himalayas, and the Alps. As the glaciers of the Alps have been studied longer and more thoroughly than any others, we shall describe them in some detail as examples of valley glaciers in all parts of the world. Conditions of glacier formation. The condition of the great accumulation of snow to which glaciers are due, that more or less of each winter's snow should be left over unmelted and unevaporated to the next, is fully met in the Alps. There is abundant moisture brought by the winds from neighboring seas. The currents of moist air driven up the mountain slopes are cooled by their own expansion as they rise, and the moisture which they contain is condensed at a temperature at or below 32 degrees Fahrenheit, and therefore is precipitated in the form of snow. The summers are cool, and their heat does not suffice to completely melt the heavy snow of the preceding winter. On the Alps, the snow line, the lower limit of permanent snow, is drawn at about 8,500 feet above sea level. Above the snow line on the slopes and crests, where these are not too steep, the snow lies the year round and gathers in valley heads to a depth of hundreds of feet. This is but a small fraction of the thickness to which snow would be piled on the Alps were it not constantly being drained away. Below the snow fields which mantle the heights, the mountain valleys are occupied by glaciers which extend as much as a vertical mile below the snow line. The presence in the midst of forests and meadows and cultivated fields of these tongues of ice, ever melting and yet from year to year losing none of their bulk, proves that their loss is made good in the only possible way. They are fed by snow fields above, whose surplus of snow they drain away in the form of ice. The presence of glaciers below the snow line is a clear proof that, rigid and motionless as they appear, glaciers really are in constant motion down valley. The névé field. The head of an alpine valley occupied by a glacier is commonly a broad amphitheater deeply filled with snow. Great peaks tower above it, and snowy slopes rise on either side of the flanks of mountain spurs. From these heights fierce winds drift the snows into the amphitheater, and avalanches pour in their torrents of snow and waste. The snow of the amphitheater is like that of drifts in late winter after many successive thaws and freezings. It is made of hard grains and pellets and is called névé. Beneath the surface of the névé field and at its outlet, the granular névé has been compacted to a mass of porous crystalline ice. Snow has been changed to névé and névé to glacial ice, both by pressure, which drives the air from the interspaces of the snowflakes, and also by successive meltings and freezings, much as a snowball is packed in the warm hand and becomes frozen to a ball of ice. The Bergschrund. The névé is in slow motion. It breaks itself loose from the thinner snows about it, too shallow to share its motion, and from the rock rim which surrounds it, forming a deep fissure called the Bergschrund, sometimes a score and more feet wide. Size of glaciers. The ice streams of the Alps vary in size according to the amount of precipitation and the area of the névé fields which they drain. The largest of alpine glaciers, the Aletsch, is nearly 10 miles long and has an average width of about a mile. The thickness of some of the glaciers of the Alps is as much as 1,000 feet. Giant glaciers more than twice the length of the longest in the Alps occur on the south slope of the Himalaya mountains, which receive frequent precipitations of snow from moist winds from the Indian Ocean. The best known of the many immense glaciers of Alaska, the Muir, has an area of about 800 square miles. Glacier motion. The motion of the glaciers of the Alps seldom exceeds 1 or 2 feet a day. Large glaciers, because of the enormous pressure of their weight and because of less marginal resistance, move faster than small ones. The Muir advances at a rate of 7 feet a day, and some of the larger tide glaciers of Greenland are reported to move at the exceptional rate of 50 feet and more in the same time. Glaciers move faster by day than by night, and in summer than in winter. Other laws of glacier motion may be discovered by a study of figures 96 and 97. It is important to remember that glaciers do not slide bodily over their beds, but urged by gravity more slowly down valley in somewhat the same way as would a stream of thick mud. Although small pieces of ice are brittle, the large mass of granular ice which composes a glacier acts as a viscous substance. Crevasses. Slight changes of slope in the glacier bed and the different rates of motion in different parts produce tensions under which the ice cracks and opens in great fissures called crevasses. At an abrupt descent in the bed, the ice is shattered into great fragments, which unite again below the icefall. Crevasses are opened on lines at right angles to the direction of the tension. Transverse crevasses are due to a convexity in the bed which stretches the ice lengthwise. Marginal crevasses are directed upstream and inwards. Radial crevasses are found where the ice stream deploys from some narrow valley and spreads upon some more open space. What is the direction of the tension which causes each, and to what is it due? Lateral and medial moraines. The surface of a glacier is striped lengthwise by long dark bands of rock debris. Those in the center are called the medial moraines. The one on either margin is a lateral moraine, and is clearly formed of waste which has fallen on the edge of the ice from the valley slopes. A medial moraine cannot be formed in this way, since no rock fragments can fall so far out from the sides. But following it up the glacial stream, one finds that a medial moraine takes its beginning at the junction of the glacier and some tributary, and is formed by the union of their two adjacent lateral moraines. Each branch thus adds a medial moraine, and by counting the number of medial moraines of a trunk stream, one may learn of how many branches it is composed. Surface moraines appear in the lower course of the glacier as ridges, which may reach the exceptional height of 100 feet. The bulk of such a ridge is ice. It has been protected from the sun by the veneer of moraine stuff, while the glacier surface on either side has melted down at least the distance of the height of the ridge. In summer, the lowering of the glacial surface by melting goes on rapidly. In Swiss glaciers it has been estimated that the average lowering of the surface by melting and evaporation amounts to 10 feet a year. As a moraine ridge grows higher and more steep by the lowering of the surface of the surrounding ice, the stones of its cover tend to slip down its sides. Thus moraines broaden until near the terminus of a glacier they may coalesce in a wide field of stony waste. Inglacial drift. This name is applied to whatever debris is carried within the glacier. It consists of rock waste fallen on the névé and there buried by accumulations of snow, and of that engulfed in the glacier where crevasses have opened beneath the surface moraine. As the surface of the glacier is lowered by melting, more or less inglacial drift is brought again to open air, and near the terminus it may help to bury the ice from view between a sheet of debris. The ground moraine. The drift dragged along at the glacier's base and lodged beneath it is known as the ground moraine. Part of the material of it has fallen down deep crevasses, and part has been torn and worn from the glacier's bed and banks. While the stones of the surface moraines remain as angular as when they lodged on the ice, many of those of the ground moraine have been blunted on the edges and faceted and scratched by being ground against one another and the rocky bed. In glaciers such as those of Greenland, whose basal layers are well loaded with drift and whose surface layers are nearly clean, different layers have different rates of motion, according to the amount of drift with which they are clogged. One layer glides over another, and the stones inset in each are ground and smoothed and scratched. Usually the sides of glacial pebbles are more worn than the ends, and the scratches upon them run with the longer axis of the stone. Why? The terminal moraine. As a glacier is in constant motion, it brings to its end all of its load except such parts of the ground moraine as may find permanent lodgment beneath the ice. Where the glacier front remains for some time at one place, there is formed an accumulation of drift known as the terminal moraine. In valley glaciers it is shaped by the ice front to a crescent whose convex side is downstream. Some of the pebbles of the terminal moraine are angular, and some are faceted and scored, the latter having come by the hard road of the ground moraine. The material of the dump is for the most part unsorted, though the water of the melting ice may find opportunity to leave patches of stratified sands and gravels in the midst of the unstratified mass of drift, and the finer material is in places washed away. Glacier drainage. The terminal moraine is commonly breached by a considerable stream which issues from beneath the ice by a tunnel whose portal has been enlarged to a beautiful archway by melting in the sun and the warm air. The stream is gray with silt and loaded with sand and gravel washed from the ground moraine. Glacier milk, the Swiss call this muddy water, the gray color of whose silt proves it rock flour freshly ground by the ice from the unoxidized sound rock of its bed, the mud of streams being yellowish when it is washed from the oxidized mantle of waste. Since glacial streams are well loaded with waste due to vigorous ice erosion, the valley in front of the glacier is commonly aggraded to a broad, flat floor. These outwash deposits are known as valley drift. The sand brought out by streams from beneath a glacier differs from river sand in that it consists of freshly broken angular grains. Why? The stream derives its water chiefly from the surface melting of the glacier. As the ice is touched by the rays of the morning sun in summer, water gathers in pools, and rills trickle and unite in brooklets, which melt and cut shallow channels in the blue ice. The course of these streams is short. Soon they plunge into deep wells cut by their whirling waters, where some crevice has begun to open across their path. These wells lead into chambers and tunnels, by which sooner or later their waters find way to the rock floor of the valley, and there unite in a subglacial stream. The lower limit of glaciers. The glaciers of a region do not by any means end at uniform height above sea level. Each terminates where its supply is balanced by melting. Those, therefore, which are fed by the largest and deepest néves, and those also which are the best protected from the sun by a northward exposure, or by the depth of their enclosing valleys, flow to lower levels than those whose supply is less and whose exposure to the sun is greater. A series of cold, moist years with an abundant snowfall causes glaciers to thicken and advance. A series of warm, dry years causes them to wither and melt back. The variation in glaciers is now carefully observed in many parts of the world. The Muir Glacier has retreated 2 miles in 20 years. The glaciers of the Swiss Alps are now for the most part melting back, although a well-known glacier of the Eastern Alps, the Vernackt, advanced 500 feet in the year 1900, and was then ploughing up its terminal moraine. How soon would you expect a glacier to advance after its névé fields have been swollen with unusually heavy snows, as compared with the time needed for the flood of a large river to reach its mouth after heavy rains upon its headwaters? On the surface of glaciers in summertime, one may often see large stones supported by pillars of ice several feet in height. These glacier tables commonly slope more or less strongly to the south, and thus may be used to indicate roughly the points of the compass. Can you explain their formation and the direction of their slope? On the other hand, a small and thin stone or a patch of dust lying on the ice tends to sink a few inches into it. Why? In what respects is a valley glacier like a mountain stream which flows out upon desert plains? Two confluent glaciers do not mingle their currents as do confluent rivers. What characteristics of surface moraines prove this fact? What effect would you expect the laws of glacier motion to have on the slant of the sides of transverse crevasses? A trunk glacier has 4 medial moraines. Of how many tributaries is it composed? Illustrate by diagram. State all the evidences which you have found that glaciers move. If a glacier melts back with occasional pauses up a valley, what records are left of its retreat? Piedmont glaciers. The Malaspina Glacier. Piedmont, foot of the mountain, glaciers are, as the name implies, ice fields formed at the foot of mountains by the confluence of valley glaciers. The Malaspina Glacier of Alaska, the typical glacier of this kind, is 70 miles wide and stretches for 30 miles from the foot of the Mount St. Elias range to the shore of the Pacific Ocean. The valley glaciers which unite and spread to form this lake of ice lie above the snow line, and their moraines are concealed between névé. The central area of the Malaspina is also free from debris, but on the outer edge large quantities of inglacial drift are exposed by surface melting, and form a belt of morainic waste a few feet thick and several miles wide, covered in part with a luxuriant forest, beneath which the ice is in places 1,000 feet in depth. The glacier here is practically stagnant, and lakes a few hundred yards across, which could not exist were the ice in motion and broken with crevices, gather on their beds sorted waste from the moraine. The streams which drain the glacier have cut their courses in inglacial and subglacial tunnels. None flow for any distance on the surface. The largest, the Yahtse River, issues from a high archway in the ice, a muddy torrent 100 feet wide and 20 feet deep, loaded with sand and stones which it deposits in a broad outwash plain. Where the ice has retreated from the sea, there is left a hummocky drift sheet with hollows filled with lakelets. These deposits help to explain similar hummocky regions of drift and similar plains of coarse, water-laid material often found in the drift-covered area of the northeastern United States. End of section 9. Section 10 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avahi in September 2010. The Elements of Geology by William Harmon Norton. Chapter 5, Part 2. The geological work of glacier ice. The sluggish glacier must do its work in a different way from the agile river. The mountain stream is swift and small, and its channel occupies but a small portion of the valley. The glacier is slow and big. Its rate of motion may be less than a millionth of that of running water over the same declivity, and its bulk is proportionately large and fills the valley to great depth. Moreover, glacier ice is a solid body, plastic under slowly applied stresses, while the water of rivers is a nimble fluid. Transportation. Valley glaciers differ from rivers as carriers in that they float the major part of their load upon their surface, transporting the heaviest boulder as easily as a grain of sand, while streams push and roll much of their load along their beds, and their power of transporting waste depends solely upon their velocity. The amount of the surface load of glaciers is limited only by the amount of waste received from the mountain slopes above them. The moving floor of ice stretched high across a valley sweeps along as lateral moraines much of the waste which a mountain stream would let accumulate in talus and alluvial cones. While a valley glacier carries much of its load on top, an ice sheet, such as that of Greenland, is free from surface debris, except where moraines trail away from some nunatak. If at its edge it breaks into separate glaciers which drain down mountain valleys, these tongues of ice will carry the salvages of waste common to valley glaciers. Both ice sheets and valley glaciers drag on large quantities of rock waste in their ground moraines. Stones transported by glaciers are sometimes called erratics. Such are the boulders of the drift of our northern states. Erratics may be set down in an insecure position on the melting of the ice. Deposit. Little need be added here to what has already been said of ground and terminal moraines. All strictly glacial deposits are unstratified. The load laid down at the end of a glacier in the terminal moraine is loose in texture, while the drift lodged beneath the glacier as ground moraine is often an extremely dense, stony clay, having been compacted under the pressure of the overriding ice. Erosion. A glacier erodes its bed and banks in two ways, by abrasion and by plucking. The rock bed over which a glacier has moved is seen in places to have been abraded, or ground away, to smooth surfaces which are marked by long, straight, parallel scorings aligned with the line of movement of the ice and varying in size from hairlines and coarse scratches to exceptional furrows several feet deep. Clearly, this work has been accomplished by means of the sharp sand, the pebbles, and the larger stones with which the base of the glacier is inset, and which it holds in a firm grasp as running water cannot. Hard and fine-grained rocks, such as granite and quartzite, are often not only ground down to a smooth surface, but are also highly polished by means of fine rock flour worn from the glacier bed. In other places the bed of the glacier is rough and torn. The rocks have been disrupted and their fragments have been carried away, a process known as plucking. Moving under immense pressure, the ice shatters the rock, breaks off projections, presses into crevices, and wedges the rock apart, dislodges the block into which the rock is divided by joints and bedding planes, and freezing fast to the fragments, drags them on. In this work, the freezing and thawing of subglacial waters in any cracks and crevices of the rock no doubt play an important part. Plucking occurs especially where the bedrock is weak because of close jointing. The product of plucking is boulders, while the product of abrasion is fine rock flour and sand. Roches moutonnées and rounded hills. The prominences left between the hollows due to plucking are commonly ground down and rounded on the Stoß side, the side from which the ice advances, and sometimes on the opposite, the lee side, as well. In this way the bedrock often comes to have a billowy surface known as roches moutonnées, sheep rocks. Hills overridden by an ice sheet often have similarly rounded contours on the Stoß side, while on the lee side they may be craggy, either because of plucking or because here they have been less worn from their initial profile. The direction of glacier movement. The direction of the flow of vanished glaciers and ice sheets is recorded both in the differences just mentioned in the profiles of overridden hills and also in the minute details of the glacier trail. Flint nodules or other small prominences in the bedrock are found more worn on the Stoß than on the lee side, where indeed they may have a low cone of rock protected by them from abrasion. Cavities, on the other hand, have their edges worn on the lee side and left sharp upon the Stoß. Surfaces worn and torn in the ways which we have mentioned are said to be glaciated. But it must not be supposed that a glacier everywhere glaciates its bed. although in places it acts as a rasp or as a pick, in others, and especially where its pressure is least, as near the terminus, it moves over its bed in the manner of a sled. Instances are known where glaciers have advanced over deposits of sand and gravel without disturbing them to any notable degree. Like a river, a glacier does not everywhere erode. In places it leaves its bed undisturbed, and in places aggrades it by deposits of the ground moraine. Cirques. Valley glaciers commonly head, as we have seen, in broad amphitheaters deeply filled with snow and ice. On mountains now destitute of glaciers, but whose glaciation shows that they have supported glaciers in the past, there are found similar crescentic hollows with high, precipitous walls and glaciated floors. Their floors are often basined and hold lakelets whose deep and quiet waters reflect the sheltering ramparts of rugged rock which tower far above them. Such mountain hollows are termed cirques. As a powerful spring wears back a recess in the valley side where it discharges, so the fountainhead of a glacier gradually wears back a cirque. In its slow movement the névé field broadly scours its bed to a flat or basined floor. Meanwhile the sides of the valley head are steepened and driven back to precipitous walls. For in winter the crevasse of the Bergschrund which surrounds the névé field is filled with snow, and the névé is frozen fast to the rocky sides of the valley. In early summer the névé tears itself free, dislodging and removing any loosened blocks, and the open fissure of the Bergschrund allows frost and other agencies of weathering to attack the unprotected rock. As cirques are thus formed and enlarged, the peaks beneath which they lie are sharpened, and the mountain crests are scalloped and cut back from either side to knife-edged ridges. In the western mountains of the United States, many cirques, now empty of névé and glacier ice, and known locally as basins, testify to the fact that in recent times the snow line stood beneath the levels of their floors, and thus far below its present altitude. Glacier troughs. The channel worn to accommodate the big and clumsy glacier differs markedly from the river valley cut as with a saw by the narrow and flexible stream, and widened by the weather and the wash of rains. The valley glacier may easily be from 1,000 to 3,000 feet deep, and from 1 to 3 miles wide. Such a ponderous bulk of slowly moving ice does not readily adapt itself to sharp turns and a narrow bed. By scoring and plucking all resisting edges, it develops a fitting channel with a wide, flat floor and steep, smooth sides, above which are seen the weathered slopes of stream-worn mountain valleys. Since the trunk glacier requires a deeper channel than do its branches, the bed of a branch glacier enters the main trough at some distance above the floor for the latter, although the surface of the two ice streams may be accordant. Glacier troughs can be studied best where large glaciers have recently melted completely away, as is the case in many valleys of the mountains of the western United States and of Central and Northern Europe. The typical glacier trough, as shown in such examples, is U-shaped, with a broad, flat floor and high, steep walls. Its walls are little broken by projecting spurs and lateral ravines. It is as if a V-valley cut by a river had afterwards been gouged deeper with a gigantic chisel, widening the floor to the width of the chisel blade, cutting back the spurs, and smoothing and steepening the sides. A river valley could only be as wide-floored as this after it had long been worn down to grade. The floor of a glacier trough may not be graded. It is often interrupted by irregular steps, perhaps hundreds and even 1,000 feet in height, over which the stream that now drains the valley tumbles in waterfalls. Reaches between the steps are often basined. Lakelets may occupy hollows excavated in solid rock, and other lakes may be held behind terminal moraines left as dams across the valley at pauses in the retreat of the glacier. Fjords are glacier troghs now occupied in part or wholly by the sea, either because they were excavated by a tide glacier to their present depth below sea level, or because of a submergence of the land. Their characteristic form is that of a long, deep, narrow bay, with steep rock walls and basement floor. Fjords are found only in regions which have suffered glaciation, such as Norway and Alaska. Hanging valleys. These are lateral valleys which open on their main valley some distance above its floor. They are conspicuous features of glacier troughs from which the ice has vanished, for the trunk glacier, in widening and deepening its channel, cut its bed below the bottoms of the lateral valleys. Since the mouths of hanging valleys are suspended on the walls of the glacier trough, their streams are compelled to plunge down its steep, high sides in waterfalls. Some of the loftiest and most beautiful waterfalls of the world leap from hanging valleys, among them the celebrated Staubach of the Lauterbrunnen Valley of Switzerland, and those of the fjords of Norway and Alaska. Hanging valleys are found also in river gorges where the smaller tributaries have not been able to keep pace with a strong master stream in cutting down their beds. In this case, however, they are a mark of extreme youth, for, as the trunk stream approaches grade, and its velocity and power to erode its bed decrease, the side streams soon cut back their falls and wear their beds at their mouths to a common level with that of the main river. The Grand Canyon of the Colorado must be reckoned a young valley. At its base it narrows to scarcely more than the width of the river, and yet its tributaries, except the very smallest, enter it at a common level. Why could not a wide-floored valley, such as a glacier trough, with hanging valleys opening upon it, be produced in the normal development of a river valley? The troughs of young and of mature glaciers. The features of a glacier trough depend much on the length of time the pre-existing valley was occupied with ice. During the infancy of a glacier, we may believe, the spurs of the valley which it fills are but little blunted, and its bed is but little broken by steps. In youth the glacier develops ice falls, as a river in youth develops waterfalls, and its bed becomes terraced with great stairs. The mature glacier, like the mature river, has effaced its falls and smoothed its bed to grade. It has also worn back the projecting spurs of its valley, making itself a wide channel with smooth sides. The bed of a mature glacier may form a long basin, since it abrades most in its upper and middle course, where its weight and motion are the greatest. Near the terminus, where weight and motion are the least, it erodes least, and may instead deposit a sheet of ground moraine, much as a river builds a flood-plain in the same part of its course as it approaches maturity. The bed of a mature glacier thus tends to take the form of a long, relatively narrow basin, across whose lower end may be stretched the dam of the terminal moraine. On the disappearance of the ice, the basin is rilled with a long, narrow lake, such as Lake Chelan in Washington and many of the lakes in the Highlands of Scotland. Piedmont glaciers apparently erode but little. Beneath their lake-like expanse of sluggish or stagnant ice, a broad sheet of ground moraine is probably being deposited. Cirques and glaciated valleys rapidly lose their characteristic forms after the ice has withdrawn. The weather destroys all smoothed, polished, and scored surfaces which are not protected beneath glacial deposits. The over-steepened sides of the trough are graded by landslips, by talus slopes, and by alluvial cones. Morainic heaps of drift are dissected and carried away. Hanging valleys in the irregular bed of the trough are both worn down to grade by the streams which now occupy them. The length of time since the retreat of the ice from a mountain valley may thus be estimated by the degree to which the destruction of the characteristic feature of the glacier trough has been carried. Name all the evidences you would expect to find to prove the fact that in the recent geological past the valleys of the Alps contained far larger glaciers than at present, and that on the north of the Alps the ice streams united in a Piedmont glacier which extended across the plains of Switzerland to the sides of the Jura mountains. The relative importance of glaciers and of rivers. Powerful as glaciers are, and marked as are the landforms which they produce, it is easy to exaggerate their geological importance as compared with rivers. Under present climatic conditions they are confined to lofty mountains or polar lands. Polar ice sheets are permanent only so long as the lands remain on which they rest. Mountain glaciers can stay only the brief time during which the ranges continue young and high. As lofty mountains, such as the Selkirks and the Alps, are lowered by frost and glacier ice, the snowfall will decrease, the line of permanent snow will rise, and as the mountain hollows in which snow may gather are worn beneath the snow line, the glaciers must disappear. Under present climatic conditions, the work of glaciers is therefore both local and of short duration. Even the glacial epoch, during which vast ice sheets deposited drift over northeastern North America, must have been brief as well as recent, for many lofty mountains, such as the Rockies and the Alps, still bear the marks of great glaciers which then filled their valleys. Had the glacial epoch been long, as the earth counts time, these mountains would have been worn low by ice. Had the epoch been remote, the marks of glaciation would already have been largely destroyed by other agencies. On the other hand, rivers are well nigh universally at work over the land surfaces of the globe, and ever since the dry land appeared they have been constantly engaged in leveling the continents and in delivering to the seas the waste which there is built into the stratified rocks. Icebergs. Tide glaciers, such as those of Greenland and Alaska, are able to excavate their beds to a considerable distance below sea level. From their fronts, the buoyancy of seawater raises and breaks away great masses of ice which float out to sea as icebergs. Only about 1/7 of a mass of a glacier ice floats above the surface, and a berg 300 feet high may be estimated to have been detached from a glacier not less than 2,000 feet thick where it met the sea. Icebergs transport on their long journeys whatever drift they may have carried when part of the glacier, and scatter it as they melt over the ocean floor. In this way, pebbles torn by the inland ice from the rocks of the interior of Greenland and glaciated during their carriage in the ground moraine are dropped at last among the oozes of the bottom of the North Atlantic. End of section 10.
Section 11 of The Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Bologna Times. The Elements of Geology by William Harmon Norton. Chapter 6. The Work of the Wind. We are now to study the geological work of the currents of the atmosphere, and to learn how they erode and transport and deposit waste as they sweep over the land. Illustrations of the wind's work are at hand in dry weather on any windy day. Clouds of dust are raised from the street and driven along by the gale. Here the roadway is swept bare, and there, in sheltered places, the dust settles in little windrows. The erosive power of the waste-laden currents of air is suggested as the sharp grains of flying sand sting one's face or clatter against the window. In the country one sometimes sees the dust whirled in clouds from dry, plowed fields in spring, and left in the lee of fences in small drifts, resembling in form those of snow in winter. The essential conditions for the wind's conspicuous work are illustrated in these simple examples. They are aridity and the absence of vegetation. In humid climates these conditions are only rarely and locally met; for the most part a thick growth of vegetation protects the moist soil from the wind with a cover of leaves and stems and a mattress of interlacing roots. But in arid regions either vegetation is wholly lacking, or scant growths are found huddled in detached clumps, leaving interspaces of unprotected ground. Here, too, the mantle of waste, which is formed chiefly under the action of temperature changes, remains dry and loose for long periods. Little or no moisture is present to cause its particles to cohere, and they are therefore readily lifted and drifted by the wind. Transportation by the wind. In the desert, the finer waste is continually swept to and fro by the ever shifting wind. Even in quiet weather, the air heated by contact with the hot sands rises in whirls, and the dust is lifted in stately columns, sometimes as much as 1,000 feet in height, which march slowly across the plain. In storms the sand is driven along the ground in a continuous sheet, while the air is tilled with dust. Explorers tell of sandstorms in the deserts of Central Asia and Africa, in which the air grows murky and suffocating. Even at midday it may become dark as night, and nothing can be heard except the roar of the blast and the whir of myriads of grains of sand as they fly past the ear. Sandstorms are by no means uncommon in the arid regions of the western United States. In a recent year 6 were reported from Yuma, Arizona. Trains on transcontinental railways are occasionally blockaded by drifting sand, and the dust sifts into closed passenger coaches, covering the seats and floors. After such a storm 13 carloads of sand were removed from the platform of a station on a western railway. Dust falls. Dust launched by upward whirling winds on the swift currents of the upper air is often blown for hundreds of miles beyond the arid region from which it was taken. Dust falls from western storms are not unknown even as far east as the Great Lakes. In 1896 a black snow fell in Chicago, and in another dust storm in the same decade the amount of dust carried in the air over Rock Island, Illinois, was estimated at more than 1,000 tons to the cubic mile. In March 1901 a cyclonic storm carried vast quantities of dust from the Sahara northward across the Mediterranean to fall over southern and central Europe. On March 8th dust storms raged in southern Algeria. 2 days later the dust fell in Italy, and on the 11th it had reached central Germany and Denmark. It is estimated that in these few days 1,800,000 tons of waste were carried from northern Africa and deposited on European soil. We may see from these examples the importance of the wind as an agent of transportation, and how vast in the aggregate are the loads which it carries. There are striking differences between air and water as carriers of waste. Rivers flow in fixed and narrow channels to definite goals. The channelless streams of the air sweep across broad areas, and, shifting about continually, carry their loads back and forth, now in one direction and now in another. Wind deposits. The mantle of waste of deserts is rapidly sorted by the wind. The coarser rubbish, too heavy to be lifted into the air, is left to strew wide tracks with residual gravels. The sand derived from the disintegration of desert rocks gathers in vast fields. About 1/8 of the surface of the Sahara is said to be thus covered with drifting sand. In desert mountains, as those of Sinai, it lies like fields of snow in the high valleys below the sharp peaks. On more level tracts it accumulates in seas of sand, sometimes, as in the deserts of Arabia, 200 and more feet deep. Dunes. The sand thus accumulated by the wind is heaped in wave-like hills called dunes. In the desert of northwestern India, where the prevalent wind is of great strength. The sand is laid in longitudinal dunes, i.e. in stripes running parallel with the direction of the wind, but commonly dunes lie, like ripple marks, transverse to the wind current. On the windward side they show a long, gentle slope, up which grains of sand can readily be moved, while to the lee their slope is frequently as great as the angle of repose. Dunes whose sands are not fixed by vegetation travel slowly with the wind, for their material is ever shifted forward, as the grains are driven up the windward slope and, falling over the crest, are deposited in slanting layers in the quiet of the lee. Like river deposits, wind-blown sands are stratified, since they are laid by currents of air varying in intensity, and therefore in transporting power, which carry now finer and now coarser materials, and lay them down where their velocity is checked. Since the wind varies in direction, the strata dip in various directions. They also dip at various angles, according to the inclination of the surface on which they were laid. Dunes occur not only in arid regions, but also wherever loose sand lies unprotected by vegetation from the wind. From the beaches of sea and lake shores the wind drives inland the surface sand left dry between tides and after storms, piling it in dunes, which may invade forests and fields and bury villages beneath their slowly advancing waves. On flood plains, during summer droughts, river deposits are often worked over by the wind, the sand is heaped in hummocks, and much of the fine silt is caught and held by the forests and grassy fields of the bordering hills. The sand of shore dunes differs little in composition and the shape of its grains from that of the beach from which it was derived, but in deserts, by the long wear of grain on grain as they are blown hither and thither by the wind, all soft minerals are ground to powder, and the sand comes to consist almost wholly of smooth round grams of hard quartz. Some marine sandstones, such as the St. Peter sandstone of the upper Mississippi Valley, are composed so entirely of polished spherules of quartz that it has been believed by some that their grains were long blown about in ancient deserts before they were deposited in the sea. Dust deposits. As desert sands are composed almost wholly of quartz, we may ask what has become of the softer minerals of which the rocks whose disintegration has supplied the sand were in part, and often in large part, composed. The softer minerals have been ground to powder, and little by little the quartz sand also is worn by attrition to fine dust. Yet dust deposits are scant and few in great deserts such as the Sahara. The finer waste is blown beyond its limits and laid in adjacent oceans, where it adds to the muds and oozes of their floors, and on bordering steppes and forest lands, where it is bound fast by vegetation, and slowly accumulates in deposits of unstratified loose yellow earth. The fine waste of the Sahara has been identified in dredgings from the bottom of the Atlantic Ocean, taken hundreds of miles from the coast of Africa. Loess. In northern China, an area as large as France is deeply covered with a yellow, pulverulent earth called loess (German, Luss), which many consider a dust deposit blown from the great Mongolian desert lying to the west. Loess mantles the recently uplifted mountains to the height of 8,000 feet, and descends on the plains nearly to sea level. Its texture and lack of stratification give it a vertical cleavage, hence it stands in steep cliffs on the sides of the deep and narrow trenches which have been cut in it by streams. On Loess hillsides in China are thousands of villages whose eave-like dwellings have been excavated in this soft yet firm dry loam. While dust falls are common at the present time in this region, the loess is now being rapidly denuded by streams, and its yellow silt gives name to the muddy Hoang Ho (Yellow River) and to the Yellow Sea, whose waters it discolors for scores of miles from shore. When deposits, both of dust and of sand, may be expected to contain the remains of land shells, bits of wood, and bones of land animals, testifying to the fact that they were accumulated in open air and not in the sea or in bodies of fresh water. Wind erosion. Sand laden currents of air abrade and smooth and polish exposed rock surfaces, acting in much the same way as does the jet of steam fed with sharp sand, which is used in the manufacture of ground glass. Indeed, in a single storm at Cape Cod a plate glass of a lighthouse was so ground by flying sand that its transparency was destroyed and its removal made necessary. Telegraph poles and wires wetted by wind blown sands are destroyed within a few years. In rocks of unequal resistance the harder parts are left in relief, while the softer are etched away. Thus in the pass of San Bernardino, California, through which strong winds stream from the west, crystals of garnet are left projecting on delicate rock fingers from the softer rock in which they were embedded. When carved pebbles are characteristically planed, the facets meeting along a summit ridge, or at a point like that of a pyramid. We may suppose that these facets were ground by prevalent winds from certain directions, or that from time to time the stone was undermined and rolled over as the sand beneath it was blown away on the windward side, thus exposing fresh surfaces to the driving sand. Such wind carved pebbles are sometimes found in ancient rocks, and may be accepted as evidence that the sands of which the rocks are composed were blown about by the wind. Deflation. In the denudation of an arid region, wind erosion is comparatively ineffective as compared with deflation. Latin, de, from, flare, to blow. A term by which is meant the constant removal of waste by the wind, leaving the rocks bare to the continuous attack of the weather. In moist climates, denudation is continually impeded by the mantle of waste and its cover of vegetation, and the land surface can be lowered no faster than the waste is removed by running water. Deep residual soils come to protect all regions of moderate slope, concealing from view the rock structure, and the various forms of the land are due more to the agencies of erosion and transportation than to differences in the resistance of the underlying rocks. But in arid regions the mantle is rapidly removed, even from well nigh level plains and plateaus, by the sweep of the wind and the wash of occasional rains. The geological structure of these regions of naked rock can be read as far as the eye can see, and it is to this structure that the forms of the land are there largely due. In a landmass of horizontal strata, for example, any softer surface rocks wear down to some underlying resistant stratum, and this for a while forms the surface of a level plateau. The edges of the capping layer, together with those of any softer layers beneath it, wear back in steep cliffs, dissected by the valleys of wet weather streams and often swept bare to the base by the wind. As they are little protected by talus, which commonly is removed about as fast as formed, these escarpments and the walls of the valleys retreat indefinitely, exposing some hard stratum beneath which forms the floor of a widening terrace. The high plateaus of northern Arizona and southern Utah, north of the Grand Cañon of the Colorado River, are composed of stratified rocks more than 10,000 feet thick and of very gentle inclination northward. From the broad platform in which the cañon has been cut rises a series of gigantic stairs, which are often more than 1,000 feet high and a score or more of miles in breadth. the retreating escarpments, the cliffs of the mesas and buttes which they have left behind as outliers, and the walls of the ravines are carved into noble architectural forms, into cathedrals, pyramids, amphitheaters, towers, arches, and colonnades, by the processes of weathering aided by deflation. It is thus by the help of the action of the wind that great plateaus in arid regions are dissected, and at last are smoothed away to waterless plains, either composed of naked rock or strewed with residual gravels, or covered with drifting residual sand. The specific gravity of air is 1/823 that of water. How does this fact affect the weight of the material which each can carry at the same velocity? If the rainfall should lessen in your own State to from 5 to 10 inches a year, what changes would take place in the vegetation of the country, in the soil, in the streams, in the erosion of valleys, in the agencies chiefly at work in denuding the land? In what way can a wind-carved pebble be distinguished from a river-worn pebble, from a glaciated pebble? End of Section 11, Chapter 6, The Work of the Wind.
Section 12 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Maggie Russell. The Elements of Geology by William Harmon Norton. Section 12. Chapter 7. The Sea and its Shores. We have already seen that the ocean is the goal at which the waste of the land arrives. The mantle of rock waste, creeping down slopes, is washed to the sea by streams, together with the material which the streams have worn from their beds and that dissolved by underground waters. In arid regions, the winds sweep waste either into bordering oceans or into more humid regions where rivers take it up and carry it on to the sea. Glaciers deliver the load of their moraines either directly to the sea or leave it for streams to transport to the same goal. All deposits made on the land, such as the floodplains of rivers, the silts of lake beds, dune sands, and sheets of glacial drift, mark but pauses in the process which is to bring all the materials of the land now above sea level to rest upon the ocean bed. But the sea is also at work along its shores as an agent of destruction, and we must first take up its work in erosion before we consider how it transports and deposits the waste of the land. Sea erosion. The sea cliff and the rock bench. On many coasts, the land fronts the ocean in a line of cliffs. To the edge of the cliffs, there lead down valleys and ridges carved by running water, which, if extended, would meet the water surface some way out from shore. Evidently, they are now abruptly cut short at the present shoreline because the land has been cut back. Along the foot of the cliff lies a gently shelving bench of rock, more or less thickly veneered with sand and shingle. At low tide its inner margin is laid bare, but at high tide it is covered wholly, and the sea washes the base of the cliffs. A notch, of which the sea cliff and the rock bench are the two sides, has been cut along the shore. Waves. The position of the rock bench, with its inner margin slightly above low tide, shows that it has been cut by some agent which acts like a horizontal saw, set at about sea level. This agent is clearly the surface agitation of the water. It is the wind-raised wave. As a wave comes up the shelving bench, the crest topples forward and the wave breaks, striking a blow whose force is measured by the momentum of all its tons of falling water. On the coast of Scotland, the force of the blows struck by the waves of the heaviest storms has sometimes exceeded 3 tons to the square foot. But even a calm sea constantly chafes the shore. It heaves in gentle undulations known as the ground swell, the result of storms perhaps 1,000 miles distant, and breaks on the shore in surf. The blows of the waves are not struck with clear water only, else they would have little effect on cliffs of solid rock. Storm waves arm themselves with the sand and gravel, the cobbles, and even the large boulders which lie at the base of the cliff, and beat against it with these hammers of stone. Where a precipice descends sheer into deep water, waves swash up and down the face of the rocks, but cannot break and strike effective blows. They therefore erode but little, until the talus fallen from the cliff is gradually built up beneath the sea to the level at which the waves drag bottom upon it and break. Compare the ways in which different agents abrade. The wind lightly brushes sand and dust over exposed surfaces of rock. Running water sweeps fragments of various sizes along its channels, holding them with a loose hand. Glacial ice grinds the stones of its ground moraine against the underlying rock with the pressure of its enormous weight. The wave hurls fragments of rock against the sea cliff, bruising and battering it by the blow. It also rasps the bench as it drags sand and gravel to and fro upon it. Weathering of sea cliffs. The sea cliff furnishes the weapons for its own destruction. They are broken from it, not only by the wave, but also by the weather. Indeed, the sea cliff weathers more rapidly, as a rule, than do rock ledges inland. It is abundantly wet with spray. Along its base, the ground water of the neighboring land finds its natural outlet in springs which undermine it. Moreover, it is unprotected by any shield of talus. Fragments of rock, as they fall from its face, are battered to pieces by the waves and swept out to sea. The cliff is thus left exposed to the attack of the weather, and its retreat would be comparatively rapid for this reason alone. Sea cliffs seldom overhang, but commonly, as in Figure 134, slope seaward, showing that the upper portion has retreated at a more rapid rate than has the base. Which do you infer is on the whole the more destructive agent, weathering or the wave? Draw a section of a sea cliff cut in well-jointed rocks, whose joints dip toward the land. Draw a diagram of a sea cliff where the joints dip toward the sea. Sea caves. The wave does not merely batter the face of the cliff. Like a skillful quarryman, it inserts wedges in all natural fissures, such as joints, and uses explosive forces. As a wave flaps against a crevice, it compresses the air within with a sudden stroke. As it falls back, the air as suddenly expands. On lighthouses, heavily barred doors have been burst outward by the explosive force of the air within, as it was released from pressure when a partial vacuum was formed by the refluence of the wave. Where a crevice is filled with water, the entire force of the blow of the wave is transmitted by hydraulic pressure to the sides of the fissure. Thus, storm waves, little by little, pry and suck the rock loose, and in this way, and by the blows which they strike with the stones of the beach, they quarry out about a joint, or wherever the rock may be weak, a recess known as a sea cave, provided that the rock above is coherent enough to form a roof. Otherwise, an open chasm results. Blowholes and sea arches. As a sea cave is drilled back into the rock, it may encounter a joint or crevice opened to the surface by percolating water. The shock of the waves soon enlarges this to a blowhole, which one may find on the breezy upland, perhaps 100 yards and more back from the cliff's edge. In quiet weather, the blowhole is a deep well. In storm, it plays a fountain as the waves drive through the long tunnel below and spout their spray high in air in successive jets. As the roof of the cave thus breaks down in the rear, there may remain in front for a while a sea arch similar to the natural bridges of land caverns. stacks, and wave-cut islands. As the sea drives its tunnels and open drifts into the cliff, it breaks through behind the intervening portions and leaves them isolated as stacks, much as monuments are detached from inland escarpments by the weather, and as the sea cliff retreats, these remnant masses may be left behind as rocky islets. Thus the rock bench is often set with stacks, islets in all stages of destruction, and sunken reefs, all wrecks of the land testifying to its retreat before the incessant attack of the waves. Coves, where zones of soft or closely jointed rock outcrop along a shore, or where minor water courses conic down to the sea and aid in erosion, the shore is worn back in curved reentrants called coves, while the more resistant rocks on either hand are left projecting as headlands. Figure 139. After coves are cut back a short distance by the waves, the headlands come to protect them, as with breakwaters, and prevent their indefinite retreat. The shore takes a curve of equilibrium, along which the hard rock of the exposed headland and the weak rock of the protected cove wear back at an equal rate. Rate of recession. The rate at which a shore recedes depends on several factors. In soft or incoherent rocks exposed to violent storms, the retreat is so rapid as to be easily measured. The coast of Yorkshire, England, whose cliffs are cut in glacial drift, loses 7 feet a year on the average, and since the Norman conquest, a strip a mile wide with farmsteads and villages and historic seaports has been devoured by the sea. The sandy south shore of Martha's Vineyard wears back 3 feet a year. But hard rocks retreat so slowly that their recession has seldom been measured by the records of history. Shore drift. Boulder and pebble beaches. About as fast as formed, the waist of the sea cliff is swept both along the shore and out to sea. The road of waste along shore is the beach. We may also define the beach as the exposed edge of the sheet of sediment formed by the carriage of land waste out to sea. At the foot of sea cliffs, where the waves are pounding hardest, one commonly finds the rock bench strewn on its inner margin with large stones, dislodged by the waves and by the weather, and somewhat worn on their corners and edges. From this boulder beach the smaller fragments of waste from the cliff, and the fragments into which the boulders are at last broken, drift on to more sheltered places and there accumulate in a pebble beach, made of pebbles well rounded by the wear which they have suffered. Such beaches form a mill, whose raw material is constantly supplied by the cliff. The breakers of storms set it in motion to a depth of several feet, grinding the pebbles together with a clatter to be heard above the roar of the surf. In such a rock crusher the life of a pebble is short. Where ships have stranded on our Atlantic coast with cargoes of hard-burned brick or of coal, a year of time and a drift of 5 miles along the shore have proved enough to wear brick and coal to powder. At no great distance from their source, therefore, pebble beaches give place to beaches of sand, which occupy the more sheltered reaches of the shore. Sand beaches. The angular sand grains of various minerals into which pebbles are broken by the waves are ground together under the beating surf and rounded, and those of the softer minerals are crushed to powder. The process, however, is a slow one, and if we study these sand grains under a lens, we may be surprised to see that, though their corners and edges have been blended, they are yet far from the spherical form of the pebbles from which they were derived. The grains are small, and in water they have lost about half their weight in air. The blows which they strike one another are therefore weak. Besides, each grain of sand of the wet beach is protected by a cushion of water from the blows of its neighbors. The shape and size of these grains and the relative proportion of grains of the softer materials which still remain give a rough measure of the distance in space and time which they have traveled from their source. the sand of many beaches, derived from the rocks of adjacent cliffs, or brought in by torrential streams from neighboring highlands, is dark with grains of a number of minerals softer than quartz. The white sand of other beaches, as those of the east coast of Florida, is almost wholly composed of quartz grains, for in its long travel down the Atlantic coast the weaker minerals have been worn to powder, and the hardest alone survive. How does the absence of cleavage in quartz affect the durability of quartz sand? How shore drift migrates. It is under the action of waves and currents that shore drift migrates slowly along a coast. Where waves strike a coast obliquely, they drive the waste before them little by little along the shore. Thus, on a north-south coast, where the predominant storms are from the northeast, there will be a migration of shore drift southwards. All shores are swept also by currents produced by winds and tides. These are usually far too gentle to transport of themselves the coarse materials of which beaches are made. But while the wave stirs the grain of sand and gravel and for a moment lifts them from the bottom, the current carries them a step forward on their way. The current cannot lift and the wave cannot carry, but together the two transport the waste along the shore. The road of shore drift is therefore the zone of the breaking waves. The Bayhead Beach. As the waste derived from the wear of waves and that brought in by streams is trailed along a coast, it assumes, under varying conditions, a number of distinct forms. When swept into the head of a sheltered bay, it constitutes the Bayhead Beach. By the highest storm waves, the beach is often built higher than the ground immediately behind it, and forms a dam, enclosing a shallow pond or marsh. The Bay Bar. As the stream of shore drift reaches the mouth of a bay of some size, it often occurs that, instead of turning in, it sets directly across toward the opposite headland. The waste is carried out from shore into the deeper waters of the bay mouth, where it is no longer supported by the breaking waves and sinks to the bottom. The dump is gradually built to the surface as a stubby spur, pointing across the bay, and as it reaches the zone of wave action, current and wave can now combine to carry shore drift along it, depositing their load continually at the point of the spur. An embankment is thus constructed in much the same manner as a railway fill, which, while it is building, serves as a roadway along which the dirt from an adjacent cut is carted to be dumped at the end. When the embankment is completed, it bridges the bay with a highway along which shore drift now moves without interruption and becomes a bay bar. Incomplete bay bars. Under certain conditions, the sea cannot carry out its intention to bridge a bay. Rivers discharging in bays demand open way to the ocean. Strong tidal currents also are able to keep open channels scoured by their ebb and flow. In such cases, the most that land waste can do is to build spits and shoals, narrowing and shoaling the channel as much as possible. Incomplete bay bars sometimes have their points recurved by currents setting at right angles to the stream of shore drift, and are then classified as hooks. Figure 142. Sand reefs. On low coasts where shallow water extends some distance out, the highway of shore drift lies along a low narrow ridge, termed the sand reef, separated from the land by a narrow stretch of shallow water, called the lagoon. At intervals, the reef is held open by inlets, gaps through which the tide flows and ebbs, and by which the water of streams finds way to the sea. No finer example of this kind of shoreline is to be found in the world than the coast of Texas. From near the mouth of the Rio Grande, a continuous sand reef draws its even curve for 100 miles to Corpus Christi Pass, and the reefs are but seldom interrupted by inlets as far north as Galveston Harbor. On this coast the tides are variable and exceptionally weak, being less than 1 foot in height, while the amount of waste swept along the shore is large. The lagoon is extremely shallow, and much of it is a mud flat, too shoal for even small boats. On the coast of New Jersey, strong tides are able to keep open inlets at intervals of from 2 to 20 miles in spite of a heavy alongshore drift. Sand reefs are formed where the water is so shallow near shore that storm waves cannot run in, and therefore break some distance out from land. Where storm waves first drag bottom, they erode and deepen the seafloor, and sweep in sediment as far as the line where they break. Here, where they lose their force, they drop their load and beat up the ridge, which is known as the sand reef, when it reaches the surface. Shores of elevation and depression. Our studies have already brought to our notice 2 distinct forms of strand lines. One, the high rocky coast cut back to cliffs by the attack of the waves, and the other, the low sandy coast where the waves break, usually upon the sand reef. To understand the origin of these 2 types, we must know that the meeting place of sea and land is determined primarily by movements of the earth's crust. Where a coast land emerges, the shoreline moves seaward. Where it is being submerged, the shoreline advances on the land. Shores of elevation. The retreat of the sea, either because of a local uplift of the land or for any other reason, such as the lowering of any portion of ocean bottom, lays bare the inner margin of the seafloor. Where the seafloor has long received the waste of the land, it has been built up to a smooth subaqueous plain, gently shelving from the land. Since the new shoreline is drawn across this even surface, it is simple and regular, and is bordered on the one side by shallow water gradually deepening seaward, and on the other by low land composed of material which has not yet thoroughly consolidated to firm rock. A sand reef is soon beaten up by the waves, and for some time conditions will favor its growth. The loss of sand driven into the lagoon beyond, and of that ground to powder by the surf and carried out to sea, is more than made up by the streams of a longshore drift, and especially by the drag of sediments to the reef by the waves as they deepen the sea floor on its seaward side. Meanwhile, the lagoon gradually fills with waste from the reef and from the land. It is invaded by various grasses and reeds which have learned to grow in salt and brackish water. The marsh, laid bare only at low tide, is built above high tide by wind drift and vegetable deposits, and becomes a meadow, soldering the sand reef to the mainland. While the lagoon has been filling, the waves have been so deepening the seafloor off the sand reef that at last they are able to attack it vigorously. They now wear it back, and driving the shoreline across the lagoon or meadow, cut a line of low cliffs on the mainland. Such a shore is that of Gascony in southwestern France, a low, straight, sandy shore bordered by the dunes and unprotected by reefs from the attack of the waves of the Bay of Biscay. We may say, then, that on shores of elevation the presence of sand reefs and lagoons indicates the stage of youth, while the absence of these features and the vigorous and unimpeded attack by the sea upon the mainland indicate the stage of maturity. Where much waste is brought in by rivers, the maturity of such a coast may be long delayed. The waste from the land keeps the sea shallow offshore and constantly renews the sand reef. The energy of the waves is consumed in handling shore drift, and no energy is left for an effective attack upon the land. Indeed, with an excessive amount of waste brought down by streams, the land may be built out and encroach temporarily upon the sea, and not until long denudation has lowered the land and thus decreased the amount of waste from it. May the waves be able to cut through the sand reef, and thus the coast reach maturity. Shores of depression. Where a coastal region is undergoing submergence, the shoreline moves landward. The horizontal plane of the sea now intersects an old land surface roughened by subaerial denudation. The shoreline is irregular and indented in proportion to the relief of the land and the amount of the submergence which the land has suffered. It follows up partially submerged valleys forming bays, and bends round the divides, leaving them to project as promontories and peninsulas. The outlines of shores of depression are as varied as are the forms of the land partially submerged. We give a few typical illustrations. The characteristics of the coast of Maine are due chiefly to the fact that the mountainous region of hard rocks, once worn to a peneplain, and after a subsequent elevation deeply dissected by north-south valleys, has subsided, the depression amounting on its southern margin to as much as 600 feet below sea level. Drowned valleys penetrate the land in long narrow bays, and rugged divides project in long narrow land arms, prolonged seaward by islands representing the high portions of their extremities. Of this exceedingly ragged shore there are said to be 2,000 miles from the New Brunswick boundary as far west as Portland, a straight line distance of but 200 miles. Since the time of its greatest depression, the land is known to have risen some 300 feet, for the bays have been shortened, and the waste with which their floors were strewn is now in part laid bare, as clay plains about the bay heads and in narrow selvages about the peninsulas and islands. The coast of Dalmatia, on the Adriatic Sea, is characterized by long land arms and chains of long and narrow islands, all parallel to the trend of the coast. A region of parallel mountain ranges has been depressed, and the longitudinal valleys which lie between them are occupied by arms of the sea. Chesapeake Bay is a branching bay due to the depression of an ancient coastal plain, which, after having emerged from the sea, was channeled with broad shallow valleys. The sea has invaded the valley of the trunk stream and those of its tributaries, forming a shallow bay whose many branches are all directed towards its axis. Figure 146. Hudson Bay and the North, the Baltic, and the Yellow Seas are examples where the sinking of the land has brought the sea in over low plains of large extent, thus deeply indenting the continental outline. The rise of a few hundred feet would restore these submerged plains to the land. The cycle of shores of depression. In its infantile stage, the outline of a shore of depression depends almost wholly on the previous relief of the land, and but little on erosion by the sea. Sea cliffs and narrow benches appear where headlands and outlying islands have been nipped by the waves. As yet, little shore waste has been formed. The coast of Maine is an example of this stage. In early youth, all promontories have been strongly cliffed, and under a vigorous attack of the sea, the shore of open bays may be cut back also. Sea stacks and rocky islets, caves and coves make the shore minutely ragged. The irregularity of the coast, due to depression, is for a while increased by differential wave wear on harder and softer rocks. The rock bench is still narrow. Shore waste, though being produced in large amounts, is for the most part swept into deeper water and buried out of sight. Examples of this stage are the east coast of Scotland and the California coast near San Francisco. Later youth is characterized by a large accumulation of shore waste. The rock bench has been cut back so that it now furnishes a good roadway for shore drift. The stream of alongshore drift grows larger and larger, filling the heads of the smaller bays with beaches, building spits and hooks, and tying islands with sandbars to the mainland. It bridges the larger bays with bay bars, while their length is being reduced as their enclosing promontories are cut back by the waves. Thus there comes to be a straight, continuous, and easy road, no longer interrupted by headlands and bays, for the transportation of waste alongshore. The Baltic coast of Germany is in this stage. All the while, streams have been busy filling with delta deposits, the bays into which they empty. By these steps, a coast gradually advances to maturity, the stage when the irregularities due to depression have been effaced. When outlying islands formed by subsidence have been planed away, and when the shoreline has been driven back behind the former bayheads. The sea now attacks the land most effectively along a continuous and fairly straight line of cliffs. Although the first effective wave wear was to increase the irregularities of the shore, it sooner or later rectifies it, making it simple and smooth. Northwestern France may be cited as an upland plain, dissected and depressed, whose coast has reached maturity. In the old age of coasts, the rock bench is cut back so far that the waves can no longer exert their full effect upon the shore. Their energy is dissipated in moving shore drift hither and thither, and in abrading the bench when they drag a bottom upon it. Little by little the bench is deepened by tidal currents and the drag of waves. But this process is so slow that meanwhile the sea cliffs melt down under the weather, and the bench becomes a broad shoal, where waves and tides gradually work over the waste from the land to greater fineness and sweep it out to sea. Plains of marine abrasion. While subaerial denudation reduces the land to base level, the sea is sawing its edges to wave base, i.e., the lowest limit of the wave's effective wear. The widened rock bench forms when uplifted a plain of marine abrasion, which, like the peneplain, bevels across strata regardless of their various inclinations and various degrees of hardness. How may a plain of marine abrasion be expected to differ from a peneplain in its mantle of waste? Compared with subaerial denudation, marine abrasion is a comparatively feeble agent. At the rate of 5 feet per century, a higher rate than obtains on the youthful rocky coast of Britain, it would require more than 10 million years to pare a strip 100 miles wide from the margin of the continent, a time sufficient, at the rate at which the Mississippi Valley is now being worn away, for subaerial denudation to lower the lands of the globe to the level of the sea. Slow submergence favors the cutting of a wide rock bench. The water continually deepens upon the bench. Storm waves can therefore always ride in to the base of the cliffs and attack them with full force. Shore waste cannot impede the onset of the waves, for it is continually washed out in deeper water below wave base. Basal conglomerates. As the sea marches across the land during a slow submergence, the platform is covered with sheets of sea-laid sediments. Lowest of these is a conglomerate, the boulder and pebble beach, widened indefinitely by the retreat of the cliffs at whose base it was formed, and preserved by the finer deposits laid upon it in the constantly deepening water as the land subsides. Such basal conglomerates are not uncommon among the ancient rocks of the land, and we may know them by their rounded pebbles and larger stones, composed of the same kind of rock as that of the abraded and evened surface on which they lie. End of section 12. Chapter 7. Recording by Maggie Russell. New York, New York.
Section 13 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Esther. The Elements of Geology by William Harmon Norton. Chapter 8, Part 13. Offshore and Deep Sea Deposits. The alongshore deposits which we have now studied are the exposed edge of a vast subaqueous sheet of waste which borders the continents and extends often for as much as 200 or 300 miles from land. Soundings show that offshore deposits are laid in belts parallel to the coast, the coarsest materials lying nearest to the land and the finest furthest out. The pebbles and gravel and the clean coarse sand of beaches gives place to broad stretches of sand, which grows finer and finer until it is succeeded by sheets of mud. Clearly there is an offshore movement of waste by which it is sorted, the coarser being sooner dropped and the finer being carried further out. Offshore deposits. The debris torn by waves from rocky shores is far less in amount than the waste of the land brought down to the sea by rivers, being only 1/33 as great, according to a conservative estimate. Both mingle along shore in all the forms of beach and bar that have been described, and both are together slowly carried out to sea. On the shelving ocean floor, waste is agitated by various movements of the unquiet water, by the undertow, an outward running bottom current near the shore, by the ebb and flow of tides, by ocean currents where they approach the land, and by waves and ground swells whose effects are sometimes felt to a depth of 600 feet. By all these means the waste is slowly washed to and fro, and as it is thus ground finer and finer, and its soluble parts are more and more dissolved, it drifts farther and farther out from land. It is by no steady and rapid movement that waste is swept from the shore to its final resting place. Day after day, and century after century, the grains of sand and particles of mud are shifted to and fro, winnowed and spread in layers, which are destroyed and rebuilt again and again before they are buried safe from further disturbance. These processes, which are hidden from the eye, are among the most important of those which our science has to do, for it is they which have given shape to by far the largest part of the stratified rocks of which the land is made. The continental delta. This fitting term has been recently suggested for the sheet of waste slowly accumulating along the borders of the continents, within a narrow belt which rarely exceeds 200 or 300 miles, except near the mouths of muddy rivers such as the Amazon and Congo. Nearly all the waste of the continent, whether worn from its surface by the weather, by streams, by glaciers, or by the wind, or from its edge by the chafing of the waves, comes at last to its final resting place. The agencies which spread the material of the continental delta grow more and more feeble as they pass into deeper and more quiet water away from shore. Coarse materials are therefore soon dropped along narrow belts near land. Gravels and coarse sand lie in thick wedge-shaped masses, which thin out seaward rapidly and give place to sheets of finer sand. Sea muds. Outermost of the sediments derived from the waste of the continents is a wide belt of mud, for fine clays settle so slowly, even in sea water, whose saltiness causes them to sink much faster than they would in fresh water, that they are wafted far before they reach a bottom where they may remain undisturbed. Muds are also found near shore, carpeting the floors of estuaries, and among stretches of sandy deposits in hollows where the more quiet water has permitted the finer silt to rest. Sea muds are commonly bluish, and consolidate to bluish shales. The red colouring matter brought from land waste, iron oxide, is altered to other iron compounds by decomposing organic matter in the presence of sea water. Yellow and red muds occur where the amount of iron oxide in the silt brought down to the sea by rivers is too great to be reduced or decomposed by the organic matter present. Green muds and green sand owe their colour to certain chemical changes which take place where waste from the land accumulates on the sea floor with extreme slowness. A greenish mineral called glauconite, a silicate of iron and alumina, is then formed. Such deposits, known as greensand, are now in process of making in several patches off the Atlantic coast, and are found on the coastal plain of New Jersey, among the offshore deposits of earlier geological ages. Organic deposits. Living creatures swarm along the shore and on the shallows out from land as nowhere else in the ocean. Seaweed often mantles the rock of the sea cliff between the levels of high and low tide, protecting it to some degree from the blows of waves. On the rock bench, each little pool left by the ebbing tide is an aquarium abounding in the lowly forms of marine life. Below low tide level occur beds of molluscous shells, such as the oyster, with countless numbers of other humble organisms. Their harder parts, the shells of mollusks, the white framework of corals, the carapaces of crabs and other crustaceans, the shells of sea urchins, the bones and teeth of fishes, are gradually buried within the accumulating sheets of sediment, either whole or, far more often, broken into fragments by the waves. By means of these organic remains, each layer of beach deposits, and those of the continental delta, may contain a record of the life of the time when it was laid. Such a record has been made ever since living creatures with hard parts appeared upon the globe. We shall find it sealed away in the stratified rocks of the continents, parts of the ancient sea deposits now raised to form the dry land. Thus we have in the traces of living creatures found in the rocks, that is, fossils, a history of the progress of life upon the planet. Molluscous shell deposits. The forms of marine life of importance in rock making thrive best in clear water, where little sediment is being laid, and where at the same time the depth is not so great as to deprive them of needed light, heat, and of sufficient oxygen absorbed by sea water from the air. In such clear and comparatively shallow water there often grow countless myriads of animals, such as mollusks and corals, whose shells and skeletons of carbonate of lime gradually accumulate in beds of limestone. A shell limestone made of broken fragments cemented together is sometimes called coquina, a local term applied to such beds recently uplifted from the sea along the coast of Florida. Oolitic limestone. Un, an egg; lithos, a stone, is so named from the likeness of the tiny spherules which compose it to the roe of fish. Corals and shells have been pounded by the waves to calcareous sand, and each grain has been covered with successive concentric coatings of lime carbonate deposited about it from solution. The impalpable powder to which calcareous sand is ground by the waves settles at some distance from shore in deeper and quieter water as a limy silt, and hardens into a dense, fine-grained limestone, in which perhaps no trace of fossil is found to suggest the fact that it is of organic origin. From the Florida Keys there extends south to the trough of Florida Straits a limestone bank covered by from 540 to 800 feet of water. The rocky bottom consists of limestone, now slowly building from the accumulation of the remains of mollusks, small corals, sea urchins, worms with calcareous tubes, and lime-secreting seaweed, which live upon its surface. Where sponges and other silica-secreting organisms abound on limestone banks, silica forms part of the accumulated deposit, either in its original condition, as, for example, the spicules of sponges, or gathered into concretions and layers of flint. Where considerable mud is being deposited along with carbonate of lime, there is in process of making a clayey limestone or a limy shell; where considerable sand, a sandy limestone or a limy sandstone. Consolidation of off-shore deposits. We cannot doubt that all these loose sediments of the sea floor are being slowly consolidated to solid rock. They are soaked with water which carries in solution lime carbonate and other cementing substances. These cements are deposited between the fragments of shells and corals, the grains of sand and the particles of mud, binding them together into firm rock. Where sediments have accumulated to great thickness, the lower portions also tend to consolidate under the weight of the overlying beds. Except in the case of limestones, recent sea deposits, uplifted to form land, are seldom so well cemented as are the older strata, which have long been acted upon by underground waters deep below the surface within the zone of cementation, and have been exposed to view by great erosion. Ripple marks, sun cracks, etc. The pulse of waves and tidal currents agitates the loose material of offshore deposits, throwing it into fine, parallel ridges called ripple marks. One may see this beautiful ribbing imprinted on beach sands uncovered by the outgoing tide, and it is also produced where the water is of considerable depth. While the tide is out, the surface of shore deposits may be marked by the footprints of birds and other animals, or by the raindrops of a passing shower. The mud of flats thus exposed to the sun and dried cracks in a characteristic way. Such markings may be covered over with a thin layer of sediment at the next flood tide, and sealed away as a lasting record of the manner and place in which the strata were laid. In Figure 150 we have an illustration of a very ancient ripple marked sand consolidated to hard stone, uplifted and set on edge by movements of the earth's crust, and exposed to open air after long erosion. Stratification. For the most part the sheet of sea-laid waste is hidden from our sight. Where its edge is exposed along the shore we may see the surface markings which have just been noticed. Soundings also, and the observations made in shallow waters by divers, tell something of its surface. But to learn more of its structures we must study those ancient sediments which have been lifted from the sea and dissected by subaerial agencies. From them we ascertain that sea deposits are stratified. They lie in distinct layers, which often differ from one another in thickness, in size of particles, and perhaps in colour. They are parted by bedding planes, each of which represents either a change in material, or a pause in which deposition ceased and the material of one layer had time to settle and become somewhat consolidated before the material of the next was laid upon it. Stratification is thus due to intermittently acting forces, such as the agitation of the water during storms, the flow and ebb of the tide, and the shifting channels of tidal currents. Off the mouths of rivers, stratification is also caused by the coarser and more abundant material brought down at times of flood, being laid on the finer silt which is discharged during ordinary stages. How stratified deposits are built up is well illustrated in the flats which border estuaries, such as the Bay of Fundy. Each advance of the tide spreads a film of mud, which dries and hardens in the air during low water before another film is laid upon it by the next incoming tidal flood. In this way the flats have been covered by a clay which splits into leaves as thin as sheets of paper. It is in fine material, such as clays and shales and limestones, that the thinnest and most uniform layers, as well as those of widest extent, occur. On the other hand, coarse materials are commonly laid in thick beds, which soon thin out seaward and give place to deposits of finer stuff. In a general way, strata are laid in well nigh horizontal sheets, for the surface on which they are laid is generally of very gentle inclination. Each stratum, however, is lenticular or lens-like in form, having an area where it is thickest and thinning out thence to its edges, where it is overlapped by strata similar in shape. Cross-bedding. There is an apparent exception to this rule, where strata whose upper and lower surfaces may be about horizontal are made up of layers inclined at angles which may be as high as the angle of repose. In this case each stratum grew by the addition along its edge of successive layers of sediment, precisely as does a sandbar in a river, the sand being pushed continuously over the edge and coming to rest on a sloping surface. Shoals built by strong and shifting tidal currents often show successive strata in which the cross bedding is inclined in different directions. Thickness of sea deposits. Remembering the vast amounts of material denuded from the land and deposited offshore, we should expect that with the lapse of time sea deposits would have grown to an enormous thickness. It is a suggestive fact that, as a rule, the profile of the ocean bed is that of a soup plate, a basin surrounded by a flaring rim. On the continental shelf, as the rim is called, the water is seldom more than 600 feet in depth at the outer edge, and shallows gradually towards shore. Along the eastern coast of the United States, the continental shelf is from 50 to 100 and more miles in width. On the Pacific coast it is much narrower. So far as it is due to upbuilding, a wide continental shelf, such as that of the Atlantic coast, implies a massive continental delta thousands of feet in thickness. The coastal plain of the Atlantic States may be regarded as the emerged inner margin of this shelf, and borings made along the coast probe it to the depth of as much as 3,000 feet without finding the bottom of ancient offshore deposits. Continental shelves may also be due in part to a submergence of the outer margin of a continental plateau, and to marine abrasion. Deposition of sediments and subsidence. The stratified rock of the land show in many places ancient sediments which reach a thickness which is measured in miles, and which are yet the product of well-nigh continuous deposition. Such strata may prove by their fossils and by the composition and structure that they were all laid offshore in shallow water. We must infer that, during the vast length of time recorded by the enormous pile, the floor of the sea along the coast was slowly sinking, and that the trough was constantly being filled, foot by foot, as fast as it was depressed. Such gradual, quiet movements of the earth's crust not only modify the outline of coasts, as we have seen, but are of far greater geological importance in that they permit the making of immense deposits of stratified rock. A slow subsidence, continued during long time, is recorded also in the succession of the various kinds of rock that come to be deposited in the same area. As the sea transgresses the land, that is, encroaches upon it, any given part of the sea bottom is brought further and further from the shore. The basal conglomerate, formed by boulder and pebble beaches, comes to be covered with sheets of sand, and these with layers of mud as the sea becomes deeper and the shore more remote, while deposits of limestone are made when at last no waste is brought to the place from the now distant land, and the water is left clear for the growth of mollusks and other lime-secreting organisms. Rate of deposition. As deposition in the sea corresponds to denudation on the land, we are able to make a general estimate of the rate at which the former process is going on. Leaving out of account the soluble matter removed, the Mississippi is lowering its basin at the rate of 1 foot in 5,000 years, and we may assume this as the average rate at which the earth's land surface of 57,000,000 square miles is now being denuded by the removal of its mechanical waste. But sediments from the land are spread within a zone but 200 or 300 miles in width along the margin of the continents, a line 100,000 miles long. As the area of deposition, about 25,000,000 square miles, is about one half the area of denudation, the average rate of deposition must be twice the average rate of denudation, that is, about 1 foot in 2,500 years. If some deposits are made much more rapidly than this, others are made much more slowly. If they were laid no faster than the present average rate, the strata of ancient sea deposits exposed in a quarry 50 feet deep represents a lapse of at least 125,000 years, and those of a formation 500 feet thick required for their accumulation 1,250,000 years. The sedimentary record and the denudation cycle. We have seen that the successive stages in a cycle of denudation, such as that by which a land mass of lofty mountains is worn to low plains, are marked each by its own peculiar land forms, and that the forms of the earlier stages are more or less completely effaced as the cycle draws toward an end. Far more lasting records of each stage are left in the sedimentary deposits of the continental delta. Thus, in the youth of such a land mass as we have mentioned, torrential streams flowing down the steep mountain sides deliver to the adjacent sea their heavy loads of coarse waste, and thick off-shore deposits of sand and gravel record the high elevation of the bordering land. As the land is worn to lower levels, the amount and coarseness of the waste brought to the sea diminishes, until the sluggish streams carry only a fine silt which settles on the ocean floor, near to land in wide sheets of mud which harden into shale. At last, in the old stage of the region, its low plains contribute little to the sea except the soluble elements of the rocks, and in the clear waters near the land, lime-secreting organisms flourish, and their remains accumulate in beds of limestone. When long-weathered lands, mantled with deep, well-oxidized waste, are uplifted by a gradual movement of the earth's crust, and the mantle is rapidly stripped off by the revived streams, the uprise is recorded in wide deposits of red and yellow clays and sands upon the adjacent ocean floor. Where the waste brought in is more than the waves can easily distribute, as off the mouths of turbid rivers which drain highlands near the sea, deposits are little winnowed, and are laid in rapidly alternating shaly sandstones and sandy shales. Where the highlands are of igneous rock, such as granite, and mechanical disintegration is going on more rapidly than chemical decay, these conditions are recorded in the nature of the deposits laid off-shore. The waste swept in by streams contained much feldspar and other minerals softer and more soluble than quartz, and where the waves have little opportunity to wear and winnow it, it comes to rest in beds of sandstone, in which grains of feldspar and other soft minerals are abundant. Such feldspathic sandstones are known as arkose. On the other hand, where the waste supplied to the sea comes chiefly from wide, sandy, coastal plains, there are deposited, off-shore, clean sandstones of well-worn grains of quartz alone. In such coastal plains the waste of the land is stored for ages. Again and again they are abandoned and invaded by the sea, as from time to time the land slowly emerges and is again submerged. Their deposits are long exposed to the weather, and sorted over by the streams, and winnowed and worked over again and again by the waves. In the course of long ages such deposits thus become thoroughly sorted, and the grains of all minerals softer than quartz are ground to mud. Deep-sea oozes and clays. Globigerina ooze. Beyond the reach of waste from the land, the bottom of the deep sea is carpeted for the most part with either chalky ooze or a fine red clay. The surface waters of the warm seas swarm with minute and lowly animals belonging to the order of the foraminifera, which secrete shells of carbonate of lime. At death these tiny white shells fall through the sea water like snowflakes in the air, and slowly dissolving, seem to melt quite away before they can reach depths greater than about 3 miles. Near shore they reach bottom, but are masked by the rapid deposit of waste derived from the land. At intermediate depths they mantle the ocean floor with a white, soft lime deposit, known as Globigerina ooze, from a genus of the foraminifera, which contributes largely to its formation. Red clay. Below depths of from 15 to 18,000 feet, the ocean bottom is sheeted with red or chocolate-coloured clay. It is the insoluble residue of sea shells, of the debris of submarine volcanic eruptions, of volcanic dust wafted by the winds, and of pieces of pumice drifted by ocean currents far from the volcanoes from which they were hurled. The red clay builds up with such inconceivable slowness that the teeth of sharks and the hard ear bones of whales may be dredged in large numbers from the deep ocean bed, where they have lain unburied for thousands of years, and an appreciable part of the clay is also formed by the dust of meteorites consumed in the atmosphere, a dust which falls everywhere on sea and land, but which elsewhere is wholly masked by other deposits. The dark, cold abyss of the ocean are far less affected by change than any other portion of the surface of the lithosphere. These vast, silent plains of ooze lie far below the reach of storms. They know no succession of summer and winter, or of night and day. A mantle of deep and quiet water protects them from the agents of erosion which continually attack, furrow, and destroy the surface of the land. While the land is the area of erosion, the sea is the area of deposition. The sheets of sediments which are slowly spread there tend to efface any inequalities, and to form a smooth and featureless subaqueous plain. With few exceptions, the stratified rocks of the land are proved by their fossils and composition to have been laid in the sea; but in the same way they are proved to be off-shore, shallow water deposits, akin to those now making on the continental shelves. Deep-sea deposits are absent from rocks of the land, and we may therefore infer that the deep sea has never held sway where continents now are; that the continents have ever been, as now, the elevated portions of the lithosphere, and that the deep seas of the present have ever been its most depressed portions. The reef-building corals. In warm seas the most conspicuous of rock-making organisms are the corals, known as the reef-builders. Floating in a boat over a coral reef, as, for example, off the south coast of Florida, or among the Bahamas, one looks down through clear water on thickets of branching coral shrubs perhaps as much as 8 feet high, and hemispherical masses 3 or 4 feet thick, all abloom with countless minute flower-like coral polyps, gorgeous in their colours of yellow, orange, green, and red. In structure, each tiny polyp is little more than a fleshy sac, whose mouth is surrounded with petal-like tentacles, or feelers. From the sea water the polyps secrete calcium carbonate, and build it up into the stony framework which supports their colonies. Boring mollusks, worms, and sponges perforate and honeycomb this framework, even while its surface is covered with myriads of living polyps. It is thus easily broken by the waves, and white fragments of coral trees strew the ground beneath. Brilliantly coloured fishes live in these coral groves, and countless mollusks, sea urchins, and other forms of marine life make here their home. With the debris from all these sources, the reef is constantly built up until it rises to low tide level. Higher than this the corals cannot grow, since they are killed by a few hours' exposure to the air. When the reef has risen to wave base, the waves abrade it on the windward side, and pile to leeward coral blocks torn from their foundation, filling the interstices with finer fragments. Thus they heap up along the reef low narrow islands. Reef building is a comparatively rapid progress. It has been estimated that off Florida a reef could be built up to the surface from a depth of 50 feet in about 1,500 years. Coral limestones. Limestones of various kinds are due to the reef builders. The reef rock is made of corals, in place, and broken fragments of all sizes, cemented together with calcium carbonate, from solution by infiltrating waters. On the island beaches, coral sand is forming oolitic limestone, and the white coral mud, with which the sea is milky for miles about the reef in times of storm, settles, and concretes into a compact limestone of finest grain. Corals have been among the most important limestone builders of the sea ever since they made their appearance in the early geological ages. The areas on which coral limestone is now forming are large. The Great Barrier Reef of Australia, which lies off the northeastern coast, is 1,250 miles long and has a width of from 10 to 90 miles. Most of the islands of the tropics are either skirted with coral reefs or are themselves of coral formation. Conditions of coral growth. Reef-building corals cannot live except in clear salt water less, as a rule, than 150 feet in depth, with a winter temperature not lower than 68° Fahrenheit. An important condition, also, is an abundant food supply, and this is best secured in the path of the warm oceanic currents. Coral reefs may be grouped in three classes: fringing reefs, barrier reefs, and atolls. Fringing reefs. These take their name from the fact that they are attached as narrow fringes to the shore. An example is the reef which forms a selvage about a mile wide along the northeastern coast of Cuba. The outer margin, indicated by the line of white surf, where the corals are in vigorous growth, rises from about 40 feet of water. Between this and the shore lies a stretch of shoal, across which one can wade at low water, composed of coral sand, with here and there a clump of growing coral. Barrier reefs. Reefs separated from the shore by a ship channel of quiet water, often several miles in width and sometimes as much as 300 feet in depth, are known as barrier reefs. The seaward face rises abruptly from water too deep for coral growth. Low islands are cast up by the waves upon the reef, and inlets give place for the ebb and flow of the tides. Along the west coast of the island of New Caledonia a barrier reef extends for 400 miles, and for a length of many leagues seldom approaches within 8 miles of the shore. Atolls. These are ring-shaped or irregular coral islands, or island-studded reefs, enclosing a central lagoon. The narrow zone of land, like the rim of a great bowl sunken to the water's edge, rises hardly more than 20 feet at most above the sea, and is covered with a forest of trees, as the cocoanut, whose seeds can be drifted to it uninjured from long distances. The white beach of coral sand leads down to the growing reef, on whose outer margin the surf is constantly breaking. The sea face of the reef falls off abruptly, often to depths of thousands of feet, while the lagoon varies in depth from a few feet to 150 or 200, and exceptionally measures as much as 350 feet. Theories of coral reefs. Fringing reefs require no explanation, since the depth of water about them is not greater than that at which coral can grow. But barrier reefs and atolls, which may rise from depths too great for coral growth, demand a theory of their origin. Darwin's theory holds that barrier reefs and atolls are formed from fringing reefs by subsidence. The rate of sinking cannot be greater than that of the uplifting of the reef, since otherwise the corals would be carried below their depth and drowned. The process is illustrated in Figure 161, where V represents a volcanic island in mid-ocean undergoing slow depression, and SS the sea level before the sinking began, when the island was surrounded by a fringing reef. As the island slowly sinks, the reef builds up with equal pace. It rears its seaward face more steep than the island slope, and thus the intervening space between the sinking, narrowing land and the outer margin of the reef constantly widens. In this intervening space the corals are more or less smothered with silt from the outer reef and from the land, and are also deprived in large measures of the needful supply of food and oxygen by the vigorous growth of the corals on the outer rim. The outer rim thus becomes a barrier reef, and the inner belt of retarded growth is deepened by subsidence to a ship channel, SS representing sea level at this time. The final stage, where the island has been carried completely beneath the sea and overgrown by the contracting reef, whose outer ring now forms an atoll, is represented by SS. In very many instances, however, atolls and barrier reefs may be explained without subsidence. Thus a barrier reef may be formed by the seaward growth of a fringing reef upon the talus of its sea face. In Fig. 162, F is a fringing reef whose outer wall rises from about 150 feet, the lower limit of the reef building species. At the foot of this submarine cliff a talus of fallen blocks T accumulates, and as it reaches the zone of coral growth becomes the foundation on which the reef is steadily extended seaward. As the reef widens, the polyps of the circumference flourish, while those of the inner belt are retarded in their growth and at last perish. The coral rock of the inner belt is now dissolved by sea water and scoured out by tidal currents until it gives place to a gradual deepening ship channel, while the outer margin is left as a barrier reef. In much the same way, atolls may be built on any shoal which lies within the zone of coral growth. Such shoals may be produced when volcanic islands are levelled by waves and ocean currents, and when submarine plateaus, ridges, and peaks are built up by various organic agencies, such as molluscous and foraminiferal shell deposits. The reef-building corals, whose eggs are drifted widely over the tropic seas by ocean currents, colonize such submarine foundations wherever the conditions are favourable for their growth. As the reef approaches the surface, the corals of the inner area are smothered by silt and starved, and their submarine volcanic peak hard parts are dissolved and scoured away, while those of the circumference, with abundant food supply, nourish and build the ring of the atoll. Atolls may be produced also by the backward drift of sand from either end of a crescentic coral reef or island, the spits uniting in the quiet water of the Lee to enclose a lagoon. In the Maldive archipelago all gradations between crescent-shaped islets and complete atoll rings have been observed. In a number of instances where coral reefs have been raised by movements of the earth's crust, the reef's formation is found to be a thin veneer built upon a foundation of other deposits. Thus Christmas Island, in the Indian Ocean, is a volcanic pile rising 1,100 feet above sea level, and 15,500 feet above the bottom of the sea. The summit is a plateau surrounded by a rim of hills of reef formation, which represent the ring of islets of an ancient atoll. Beneath the reef are thick beds of limestone, composed largely of the remains of foraminifers, which cover the lavas and fragmental materials of the old submarine volcano. Among the ancient sediments which now form the stratified rocks of the land there occur many thin reef deposits, but none are known of the immense thickness which modern reefs are supposed to reach according to the theory of subsidence. Barrier and fringing reefs are commonly interrupted off the mouths of rivers. Why? Summary. We have seen that the ocean bed is the goal to which the waste of rocks of the land at last arrives. Their soluble parts, dissolved by underground waters and carried to the sea by rivers, are largely built up by living creatures into vast sheets of limestone. The less soluble portions, the waste brought in by streams and the waste of the shore, form the muds and sands of continental deltas. All of these sea deposits consolidate and harden, and the coherent rocks of the land are thus reconstructed on the ocean floor. But the destination is not a final one. The stratified rocks of the land are for the most part ancient deposits of the sea, which have been lifted above sea level, and we may believe that the sediments now being laid off shore are the dust of continents to be, and will some time emerge to form additions to the land. We are now to study the movements of the earth's crust, which restore the sediments of the sea to the light of day, and to whose beneficence we owe the habitable lands of the present. End of section 13.
Section 14 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Part 2. Internal Geological Agencies. Chapter 9. Movements of the Earth's Crust. The geological agencies which we have so far studied, weathering, streams, underground waters, glaciers, winds, and the ocean, all work upon the earth from without, and all are set in motion by an energy external to the earth, namely, the radiant energy of the sun. All, too, have a common tendency to reduce the inequalities of the earth's surface by leveling the lands and strewing their waste beneath the sea. But despite the unceasing efforts of these external agencies, they have not destroyed the continents, which still rear their broad plains and great plateaus and mountain ranges above the sea. Either, then, the earth is very young and the agents of denudation have not yet had time to do their work, or they have been opposed successfully by other forces. We enter now upon a department of our science which treats of forces which work upon the earth from within, and increase the inequalities of its surface. It is they which uplift and recreate the lands which the agents of denudation are continually destroying. It is they which deepen the ocean bed and thus withdraw its waters from the shores. At times, also, these forces have aided in the destruction of the lands by gradually lowering them and bringing in the sea. Under the action of forces resident within the earth, the crust slowly rises or sinks. From time to time it has been folded and broken, while vast quantities of molten rock have been pressed up into it from beneath and outpoured upon its surface. We shall take up these phenomena in the following chapters, which treat of upheavals and depressions of the crust, foldings and fractures of the crust, earthquakes, volcanoes, the interior conditions of the earth, mineral veins, and metamorphism. Oscillations of the crust. Of the various movements of the crust due to internal agencies, we will consider first those called oscillations, which lift or depress large areas so slowly that a long time is needed to produce perceptible changes of level, and which leave the strata in nearly their original horizontal attitude. These movements are most conspicuous along coasts, where they can be referred to in the datum plane of sea level. We will therefore take our first illustrations from rising and sinking shores. New Jersey. Along the coast of New Jersey one may find awash at high tide ancient shell heaps, the remains of tribal feasts of aborigines. Meadows and old forest grounds, with the stumps still standing, are now overflowed by the sea, and fragments of their turf and wood are brought to shore by waves. Assuming that the sea level remains constant, it is clear that the New Jersey coast is now gradually sinking. The rate of submergence has been estimated at about 2 feet per century. On the other hand, the wide coastal plain of New Jersey is made of stratified sands and clays, which, as their marine fossils show, were outspread beneath the sea. Their present position above sea level proves that the land now subsiding emerged in the recent past. The coast of New Jersey is an example of the slow and tranquil oscillations of the earth's unstable crust, now in progress along many shores. Some are emerging from the sea, some are sinking beneath it, and no part of the land seems to have been exempt from these changes in the past. Evidences of changes of level. Taking the surface of the sea as a level of reference, we may accept as proofs of relative upheaval whatever is now found in place above sea level, and could have been formed only at or beneath it, and as proofs of relative subsidence whatever is now found beneath the sea and could only have been formed above it. Thus old strand lines with sea cliffs, wave-cut rock benches, and beaches of wave-worn pebbles or sand are striking proofs of recent emergence to the amount of their present height above tide. No less conclusive is the presence of sea-laid rocks which we may find in the neighboring quarry or outcrop, although it may have been long ages since they were lifted from the sea to form part of the dry land. Among common proofs of subsidence are roads and buildings and other works of man, and vegetal growths and deposits, such as forest grounds and peat beds, now submerged beneath the sea. In the deltas of many large rivers, such as the Po, the Nile, the Ganges, and the Mississippi, buried soils prove subsidences of hundreds of feet, and in several cases, as in the Mississippi Delta, the depression seems to be now in progress. Other proofs of the same movement are drowned landforms which are modeled only in open air. Since rivers cannot cut their valleys farther below the base level of the sea than the depths of their channels, drowned valleys are among the plainest proofs of depression. To this class belong Narragansett, Delaware, Chesapeake, Mobile, and San Francisco bays, and many other similar drowned valleys along the coast of the United States. Less conspicuous are the submarine channels which, as soundings show, extend from the mouths of a number of rivers some distance out to sea. Such is the submerged channel which reaches from New York Bay southeast to the edge of the continental shelf, and which is supposed to have been cut by the Hudson River when this part of the shelf was a coastal plain. Warping. In a region undergoing changes of level, the rate of movement commonly varies in different parts. Portions of an area may be rising or sinking, while adjacent portions are stationary or moving in the opposite direction. In this way, a land surface becomes warped. Thus, while Nova Scotia and New Brunswick are now rising from the level of the sea, Prince Edward Island and Cape Breton Island are sinking, and the sea now flows over the site of the famous old town of Louisbourg, destroyed in 1758. Since the close of the glacial epoch, the coasts of Newfoundland and Labrador have risen hundreds of feet, but the rate of emergence has not been uniform. The old Strand Line, which stands at 575 feet above tide at St. John's, Newfoundland, declines to 250 feet near the northern point of Labrador. The Great Lakes is now undergoing perceptible warping. Rivers enter the lakes from the south and west with sluggish currents and deep channels resembling the estuaries of drowned rivers, while those that enter from opposite directions are swift and shallow. At the western end of Lake Erie are found submerged caves containing stalactites, and old meadows and forest grounds are now under water. It is thus seen that the water of the lakes is rising along their southwestern shores, while from their northeastern shores it is being withdrawn. The region of the Great Lakes is therefore warping. It is rising in the northeast as compared with the southwest. From old benchmarks and records of lake levels, it has been estimated that the rate of warping amounts to 5 inches a century for every 100 miles. It is calculated that the water of Lake Michigan is rising at Chicago at the rate of 9 or 10 inches per century. The divide at this point between the tributaries of the Mississippi and Lake Michigan is but 8 feet above the mean stage of the lake. If the canting of the region continues at its present rate, in 1,000 years the waters of the lake will here overflow the divide. In 3,500 years all the lakes except Ontario will discharge by this outlet, via the Illinois and Mississippi rivers, into the Gulf of Mexico. The present outlet by the Niagara River will be left dry, and the divide between the St. Lawrence and the Mississippi systems will have shifted from Chicago to the vicinity of Buffalo. Physiographic effects of oscillations. We have already mentioned several of the most important effects of movements of elevation and depression, such as their effects on rivers, the mantle of waste, and the forms of coasts. Movements of elevation, including uplifts by folding and fracture of the crust to be noticed later, are the necessary conditions for erosion by whatever agent. They determine the various agencies which are to be chiefly concerned in the wear of any land, whether streams or glaciers, weathering or wind, and the degree of their efficiency. The lands must be uplifted before they can be eroded, and since they must be eroded before their waste can be deposited, movements of elevation are a prerequisite condition for sedimentation also. Subsidence is a necessary condition for deposits of great thickness, such as those of the Great Valley of California and the Indo-Gangetic Plain, page 101, the Mississippi Delta, page 109, and the still more important formations of the continental delta in gradually sinking troughs, page 183. It is not too much to say that the character and thickness of each formation of the stratified rocks depend primarily on these crustal movements. Along the Baltic coast of Sweden, benchmarks show that the sea is withdrawing from the land at a rate which at the north amounts to between 3 and 4 feet per century. Towards the south the rate decreases. South of Stockholm, until recent years, the sea has gained upon the land, and here in several seaboard towns, streets by the shore are still submerged. The rate of oscillation increases also from the coast inland. On the other hand, along the German coast of the Baltic, the only historic fluctuations of sea level are those which may be accounted for by variations due to changes in rainfall. In 1730 Celsius explained the changes of level of the Swedish coast as due to a lowering of the Baltic instead of to an elevation of the land. Are the facts just stated consistent with his theory? At the little town of Tadoussac, where the Saguenay River empties into the St. Lawrence, there are terraces of old sea beaches, some almost as fresh as recent railway fills, the highest standing 230 feet above the river. Here the Saguenay is 840 feet in depth, and the tide ebbs and flows far up its stream. Was its channel cut to this depth by the river when the land was at its present height? What oscillations are here recorded, and to what amount? A few miles north of Naples, Italy, the ruins of an ancient Roman temple lie by the edge of the sea, on a narrow plain which is overlooked in the rear by an old sea cliff, Figure 166. 3 marble pillars are still standing. For 11 feet above their bases these columns are uninjured, for to this height they were protected by an accumulation of volcanic ashes, but from 11 to 19 feet they are closely pitted with the holes of boring marine mollusks. From these facts trace the history of the oscillations of the region. Foldings of the crust. The oscillations which we have just described leave the strata not far from their original horizontal attitude. Figure 167 represents a region in which movements of a very different nature have taken place. Here, on either side of Valley V, we find outcrops of layers tilted at high angles. Sections along the ridge R show that it is composed of layers which slant inward from either side. In places the outcropping strata stand nearly on edge, and on the right of the valley they are quite overturned. A shale SH has come to overlie a limestone LM, although the shale is the older rock, whose original position was beneath the limestone. It is not reasonable to suppose that these rocks were deposited in the attitude in which we find them now. We must believe that, like other stratified rocks, they are outspread in nearly level sheets upon the ocean floor. Since that time they must have been deformed. Layers of solid rock, several miles in thickness, have been crumpled and folded like soft wax in the hand, and a vast denudation has worn away the upper portions of the folds, in part represented in our section by dotted lines. Dip and strike. In districts where the strata have been disturbed, it is desirable to record their attitude. This is most easily done by taking the angle at which the strata are inclined and the compass direction in which they slant. It is also convenient to record the direction in which the outcrop of the strata trends across the country. The inclination of the bed of rocks to the horizontal is its dip. The amount of the dip is the angle made with a horizontal plane. The dip of a horizontal layer is 0, and that of a vertical layer is 90 degrees. The direction of the dip is taken with the compass. Thus a geologist's notebook in describing the attitude of outcropping strata contains many such entries as these: dip 32 degrees north, or dip 8 degrees south, 20 degrees west, meaning in the latter case that the amount of the dip is 8 degrees and the direction of the dip bears 20 degrees west of south. The line of intersection of a layer with the horizontal plane is the strike. The strike always runs at right angles to the dip. Dip and strike may be illustrated by a book set aslant on a shelf. The dip is the acute angle made with the shelf by the side of the book, while the strike is represented by a line running along the book's upper edge. If the dip is north or south, the strike runs east and west. Folded structures. An upfold in which the strata dip away from a line drawn along the crest and called the axis of the fold is known as an anticline. A downfold, where the strata dip from either side toward the axis of the trough, is called a syncline. There is sometimes seen a downward bend in horizontal or gently inclined strata, by which they descend to a lower level. Such a single flexure is a monocline. Degrees of folding. Folds vary in degree from broad, low swells, which can hardly be detected, to the most highly contorted and complicated structures. In symmetric folds, the dips of the rocks on each side of the axis of the fold are equal. In unsymmetrical folds, one limb is steeper than the other, as in the anticline in Figure 167. In overturned folds, one limb is inclined beyond the perpendicular. Fan folds have been so pinched that the original anticlines are left broader at the top than at the bottom. In folds where the compression has been great, the layers are often found thickened at the crest and thinned along the limbs. Where strong rocks such as heavy limestones are folded together with weak rocks such as shales, the strong rocks are often bent into great simple folds, while the weak rocks are minutely crumpled. Systems of folds. As a rule, folds occur in systems. Over the Appalachian Mountain Belt, for example, extending from northeastern Pennsylvania to northern Alabama and Georgia, the Earth's crust has been thrown into a series of parallel folds whose axes run from northeast to southwest. Figure 175. In Pennsylvania one may count a score or more of these earth waves, some but from 10 to 20 miles in length, and some extending as much as 200 miles before they die away. On the eastern part of this belt, the folds are steeper and more numerous than on the western side. Cause and conditions of folding. The sections which we have studied suggest that rocks are folded by lateral pressure. While a single simple fold might be produced by a heave, a series of folds, including overturns, fan folds, and folds thickened on their crests at the expense of their limbs, could only be made in one way, by pressure from the side. Experiment has reproduced all forms of folds by subjecting to lateral thrust layers of plastic material such as wax. Vast as the force must have been which could fold the solid rocks of the crust as one may crumple the leaves of a magazine in the fingers, it is only under certain conditions that it could have produced the results which we see. Rocks are brittle, and it is only when under a heavy load and by great pressure slowly applied that they can thus be folded and bent instead of being crushed to pieces. Under these conditions, experiments prove that not only metals such as steel, but also brittle rocks such as marble, can be deformed and molded and made to flow like plastic clay. Zone of flow and fracture, and zone of fracture. We may believe that at depths which must be reckoned in tens of thousands of feet, the load of overlying rocks is so great that rocks of all kinds yield by folding to lateral pressure, and flow instead of breaking. Indeed, at such profound depths and under such inconceivable weight, no cavity can form, and any fracture would be healed at once by the welding of grain to grain. At less depths there exists a zone where soft rocks fold and flow under stress, and hard rocks are fractured, while at and near the surface, hard and soft rocks alike yield by fracture to strong pressure. Structures developed in compressed rocks. Deformed rocks show the effects of the stresses to which they have yielded, not only in the immense folds into which they have been thrown, but in their smallest parts as well. A hand specimen of slate, or even a particle under the microscope, may show plication similar in form and origin to the foldings which have produced ranges of mountains. A tiny flake of mica in the rocks of the Alps may be puckered by the same resistless forces which have folded miles of solid rock to form that lofty range. Slaty cleavage. Rocks which have yielded to pressure often split easily in a certain direction across the bedding planes. This cleavage is known as slaty cleavage, since it is most perfectly developed in fine-grained, homogeneous rocks, such as slates, which cleave to the thin, smooth-surfaced plates with which we are familiar in the slates used in roofing and for ciphering and blackboards. In coarse-grained rocks, pressure develops more distant partings, which separate the rocks into blocks. Slaty cleavage cannot be due to lamination, since it commonly crosses bedding planes at an angle, while these planes have been often well nigh or quite obliterated. Examining slate with a microscope, we find that its cleavage is due to the grain of the rock. Its particles are flattened and lie with their broad faces in parallel planes, along which the rock naturally splits more easily than in any other direction. The irregular grains of the mud which has been altered to slate have been squeezed flat by a pressure exerted at right angles to the plane of cleavage. Cleavage is found only in folded rocks, and as we may see in Figure 176, the strike of the cleavage runs parallel to the strike of the strata and the axis of the folds. The dip of the cleavage is generally steep, hence the pressure was nearly horizontal. The pressure which has acted at right angles to the cleavage, and to which it is due, is the same lateral pressure which has thrown the strata into folds. We find additional proof that slates have undergone compression at right angles to their cleavage in the fact that any inclusions in them, such as nodules and fossils, have been squeezed out of shape and have their long diameters lying in the planes of cleavage. That pressure is competent to cause cleavage is shown by experiment. Homogeneous material of fine grain, such as beeswax, when subjected to heavy pressure, cleaves at right angles to the direction of the compressing force. Rate of folding. All the facts known with regard to rock deformation agree that it is a secular process, taking place so slowly that, like the deepening of valleys by erosion, it escapes the notice of the inhabitants of the region. It is only under stresses slowly applied that rocks bend without breaking. The folds of some of the highest mountains have risen so gradually that strong, well-entrenched rivers, which had the right of way across the region, were able to hold to their courses, and as a circular saw cuts its way through the log which is steadily driven against it, so these rivers sawed their gorges through the fold as fast as it rose beneath them. Streams which thus maintain the course which they had antecedent to a deformation of the region are known as antecedent streams. Examples of such are the Sutlej and other rivers of India, whose valleys trench the outer ranges of the Himalayas, and whose earlier river deposits have been upturned by the rising ridges. On the other hand, mountain crests are usually divides, parting the headwaters of different drainage systems. In these cases, the original streams of the region have been broken or destroyed by the uplift of the mountain mass across their paths. On the whole, which have worked more rapidly, processes of deformation or of denudation? Land forms due to folding. As folding goes on so slowly, it is never left to form surface features unmodified by the action of other agencies. An anticlinal fold is attacked by erosion as soon as it begins to rise above the original level, and the higher it is uplifted and the stronger are its slopes, the faster is it worn away. Even while rising, a young upfold is often thus unroofed, and instead of appearing as a long, smooth, boat-shaped ridge, it commonly has had opened along the rocks of the axis, when these are weak, a valley which is overlooked by the infacing escarpments of the hard layers of the sides of the fold. Under long continued erosion, anticlines may be degraded to valleys, while the synclines of the same system may be left in relief as ridges. Folded mountains. The vastness of the forces which wrinkle the crust is best realized in the presence of some lofty mountain range. All mountains, indeed, are not the result of folding. Some, as we shall see, are due to upwarps or to fractures of the crust. Some are piles of volcanic material. Some are swellings caused by the intrusion of molten matter beneath the surface. Some are the relics left after the long denudation of high plateaus. But most of the mountain ranges of the earth, and some of the greatest, such as the Alps and the Himalayas, were originally mountains of folding. The earth's crust has wrinkled into a fold, or into a series of folds, forming a series of parallel ridges and intervening valleys, or a number of folds have been mashed together into a vast upswelling of the crust, in which the layers have been so crumpled and twisted, overturned and crushed, that it is exceedingly difficult to make out the original structure. The close and intricate folds seen in great mountain ranges were formed, as we have seen, deep below the surface, within the zone of folding. Hence they may never have found expression in any individual surface features. As the result of these deformations deep underground, the surface was broadly lifted to mountain height, and the crumpled and twisted mountain structures are now to be seen only because erosion has swept away the heavy cover of surface rocks under whose load they were developed. When the structure of mountains has been deciphered, it is possible to estimate roughly the amount of horizontal compression which the region has suffered. If the strata of the folds of the Alps were smoothed out, they would occupy a belt 74 miles wider than that to which they have been compressed, or twice their present width. A section across the Appalachian folds in Pennsylvania shows a compression to about 2/3 the original width. The belt has been shortened 35 miles in every 100. Considering the thickness of their strata, the compression which mountains have undergone accounts fully for their height, with enough to spare for all that has been lost by denudation. The Appalachian folds involve strata 30,000 feet in thickness. Assuming that the folded strata rested on an unyielding foundation, and that what was lost in width was gained in height, what elevation would the range have reached had not denudation worn it as it rose? The life history of mountains. While the disturbance and uplift of mountain masses are due to deformation, their sculpture into ridges and peaks, valleys and deep ravines, and all the forms which meet the eye in mountain scenery, excepting in the very youngest ranges, is due solely to erosion. We may therefore classify mountains according to the degree to which they have been dissected. The Juras are an example of the stage of early youth, in which the anticlines still persist as ridges and the synclines coincide with the valleys. This they owe as much to the slight height of their uplift as to the recency of its date. The Alps were upheaved at various times, the last uplift being later than the uplift of the Juras, but to so much greater height that erosion has already advanced them well on towards maturity. The mountain mass has been cut to the core, revealing strange contortions of strata which could never have found expression at the surface. Sharp peaks, knife-edged crests, deep valleys with ungraded slopes subject to frequent landslides are all features of alpine scenery typical of a mountain range at this stage in its life history. They represent the survival of the hardest rocks and the strongest structures, and the destruction of the weaker in their long struggle for existence against the agents of erosion. Although miles of rock have been removed from such ranges as the Alps, we need not suppose that they ever stood much, if any, higher than at present. All this vast denudation may easily have been accomplished while their slow upheaval was going on. In several mountain ranges we have evidence that elevation has not yet ceased. Under long denudation, mountains are subdued to the forms characteristic of old age. The lofty peaks and jagged crests of their earlier life are smoothed down to low domes and rounded crests. The southern Appalachians and portions of the Harz Mountains in Germany are examples of mountains which have reached this stage. There are numerous regions of upland and plains in which the rocks are found to have the same structure that we have seen in folded mountains. They are tilted, crumpled, and overturned, and have clearly suffered intense compression. We may infer that their folds were once lifted to the height of mountains, and have since been wasted to low-lying lands. Such a section as that of Figure 67 illustrates how ancient mountains may be leveled to their roots, and represents the final stage to which even the Alps and the Himalayas must sometime arrive. Mountains, perhaps of alpine height, once stood about Lake Superior. A lofty range once extended from New England and New Jersey southwestward to Georgia, along the Piedmont belt. In our study of historic geology we shall see more clearly how short is the life of mountains, as the earth counts time, and how great ranges have been lifted, worn away, and again upheaved into a new cycle of erosion. The sedimentary history of folded mountains. We may mention here some of the conditions which have commonly been antecedent to great foldings of the crust. 1. Mountain ranges are made of belts of enormously and exceptionally thick sediments. The strata of the Appalachians are 30,000 feet thick, while the same formations thin out to 5,000 feet in the Mississippi Valley. The folds of the Wasatch Mountains involve strata 30,000 feet thick, which thin to 2,000 feet in the region of the plains. 2. The sedimentary strata of which mountains are made are for the most part the shallow water deposits of continental deltas. Mountain ranges have been upfolded along the margins of continents. 3. Shallow water deposits of the immense thickness found in mountain ranges can be laid only in a gradually sinking area. A profound subsidence, often to be reckoned in tens of thousands of feet, precedes the upfolding of a mountain range. Thus the history of mountains of folding is as follows. For long ages the sea bottom off the coast of a continent slowly subsides, and the great trough, as fast as it forms, is filled with sediments, which at last come to be many thousands of feet thick. The downward movement finally ceases. A slow but resistless pressure sets in, and gradually, and with a long series of many intermittent movements, the vast mass of accumulated sediments is crumpled and uplifted into a mountain range. End of section 14. Section 15 of the Elements of Geology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Elements of Geology by William Harmon Norton. Chapter 9. Movements of the Earth's Crust. Part 2. Fractures and dislocations of the crust. Considering the immense stresses to which the rocks of the crust are subjected, it is not surprising to find that they often yield by fracture, like brittle bodies, instead of by folding and flowing, like plastic solids. Whether rocks bend or break depends on the character and condition of the rocks, the load of overlying rocks which they bear, and the amount of the force and the slowness with which it is applied. Joints. At the surface where their load is least, we find rocks universally broken into blocks of greater or less size by partings known as joints. Under this name are included many division planes caused by cooling and drying, but it is now generally believed that the larger and more regular joints, especially those which run parallel to the dip and strike of the strata, are fractures due to up and down movements and foldings and twistings of the rocks. Joints are used to great advantage in quarrying, and we have seen how they are utilized by the weather in breaking up rock masses, by rivers in widening their valleys, by the sea in driving back its cliffs, by glaciers in plucking their beds, and how they are enlarged in soluble rocks to form natural passageways for underground waters. The ends of the parted strata match along both sides of joint planes. In joints there has been little or no displacement of the broken rocks. Faults. In Figure 184, the rocks have been both broken and dislocated along the plane FF'. One side must have been moved up or down past the other. Such a dislocation is called a fault. The amount of the displacement, as measured by the vertical distance between the ends of a parted layer, is the throw. The angle which the fault plane makes with the vertical is the hade. In Figure 184, the right side has gone down relatively to the left. The right is the side of the down throw, while the left is the side of the up throw. Where the fault plane is not vertical, the surfaces on the two sides may be distinguished as the hanging wall and the foot wall. Faults differ in throw from a fraction of an inch to many thousands of feet. Slicken sides. If we examine the walls of a fault, we may find further evidence of movement in the fact that the surfaces are polished and grooved by the enormous friction which they have suffered as they have ground one upon the other. These appearances, called slicken sides, have sometimes been mistaken for the results of glacial action. Normal faults. Faults are of two kinds, normal faults and thrust faults. Normal faults, of which Figure 184 is an example, hade to the down throw. The hanging wall has gone down. The total length of the strata has been increased by the displacement. It seems that the strata have been stretched and broken, and that the blocks have readjusted themselves under the action of gravity as they settled. Thrust faults. Thrust faults hade to the upthrow. The hanging wall has gone up. Clearly such faults, where the strata occupy less space than before, are due to lateral thrust. Folds and thrust faults are closely associated. Under lateral pressure strata may fold to a certain point and then tear apart and fault along the surface of least resistance. Under immense pressure, strata also break by shear without folding. Thus, in Figure 185, the rigid earth block under lateral thrust has found it easier to break along the fault plane than to fold. Where such faults are nearly horizontal, they are distinguished as thrust planes. In all thrust faults, one mass has been pushed over another, so as to bring the underlying and older strata upon younger beds, and when the fault planes are nearly horizontal, and especially when the rocks have been broken into many slices which have slidden far one upon the other, the true succession of strata is extremely hard to decipher. In the Selkirk Mountains of Canada, the basement rocks of the region have been driven east for 7 miles on a thrust plane, over rocks which originally lay thousands of feet above them. Along the western Appalachians, from Virginia to Georgia, the mountains are broken by more than 15 parallel thrust planes, running from northeast to southwest, along which the older strata have been pushed westward over the younger. The longest continuous fault has been traced 375 miles, and the greatest horizontal displacement has been estimated at not less than 11 miles. Crush breccia. Rocks often do not fault with a clean and simple fracture, but along a zone, sometimes several yards in width, in which they are broken to fragments. It may occur also that strata which as a whole yield to lateral thrust by folding include beds of brittle rocks, such as thin-layered limestones, which are crushed to pieces by the strain. In either case, the fragments, when recemented by percolating waters, form a rock known as crush breccia. Breccia is a term applied to any rock formed of cemented angular fragments. This rock may be made by the consolidation of volcanic cinders, of angular waste at the foot of cliffs, or of fragments of coral torn by the waves from coral reefs, as well as of strata crushed by crustal movements. Surface features due to dislocations. Fault scarps. A fault of recent date may be marked at surface by a scarp because the face of the upthrown block has not yet been worn to the level of the downthrow side. After the upthrown block has been worn down to this level, differential erosion produces fault scarps wherever weak rocks and resistant rocks are brought in contact along the fault plane, and the harder rocks, whether on the upthrow or on the downthrow side, emerge in a line of cliffs. Where a fault is so old that no abrupt scarps appear, its general course is sometimes marked by the line of division between highland and lowland, or hill and plain. Great faults have sometimes brought ancient crystalline rocks in contact with weaker and younger sedimentary rocks, and long after erosion has destroyed all fault scarps, the harder crystallines rise in an upland of rugged or mountainous country which meets the lowland along the line of faulting. The vast majority of faults give rise to no surface features. The faulted region may be old enough to have been base-leveled, or the rocks on both sides of the line of dislocation may be alike in their resistance to erosion and therefore have been worn down to a common slope. The fault may be entirely concealed by the mantle of waste, and in such cases it can be inferred from abrupt changes in the character or the strike and dip of the strata where they may outcrop near it. The plateau trench by the Grand Canyon of the Colorado River exhibits a series of magnificent fault scarps, whose general course is from north to south, marking the edges of the great crust blocks into which the country has been broken. The highest part of the plateau is a crust block 90 miles long and 35 miles in maximum width, which has been hoisted to 9,300 feet above sea level. On the east it descends 4,000 feet by a monoclinal fold, which passes into a fault towards the north. On the west it breaks down by a succession of terraces faced by fault scarps. The throw of these faults varies from 700 feet to more than a mile. The escarpments, however, are due in a large degree to the erosion of weaker rock on the downthrow side. The highlands of Scotland meet the lowlands on the south with a bold front of rugged hills along a line of dislocation which runs across the country from sea to sea. On the one side are hills of ancient crystalline rocks, whose crumpled surfaces prove that they are but the roots of once lofty mountains. On the other lies a lowland of sandstone and other stratified rocks, formed from the waste of those long-vanished mountain ranges. Remnants of sandstone occur in places on the north of the Great Fault, and are here seen to rest on the worn and fairly even surface of the crystallines. We may infer that these ancient mountains were reduced along their margins to low plains, which were slowly lowered beneath the sea to receive a cover of sedimentary rocks. Still later came an uplift and dislocation. On the one side, erosion has since stripped off the sandstones for the most part, but the hard crystalline rocks yet stand in bold relief. On the other side, the weak sedimentary rocks have been worn down to lowlands. Rift valleys. In a broken region undergoing uplift or the unequal settling which may follow, a slice enclosed between two fissures may sink below the level of the crust blocks on either side, thus forming a linear depression known as a rift valley, or valley of fracture. One of the most striking examples of this rare type of valley is the long trough which runs straight from the Lebanon Mountains of Syria on the north to the Red Sea on the south, and whose central portion is occupied by the Jordan Valley and the Dead Sea. The plateau which it gashes has been lifted more than 3,000 feet above sea level, and the bottom of the trough reaches a depth of 2,600 feet below that level in parts of the Dead Sea. South of the Dead Sea, the floor of the trough rises somewhat above sea level, and in the Gulf of Aqaba again sinks below it. This uneven floor could be accounted for either by profound warping of a valley of erosion or by the unequal depression of the floor of a rift valley. But that the trough is a true valley of fracture is proved by the fact that on either side it is bounded by fault scarps and monoclinal folds. The keystone of the arch has subsided. Many geologists believe that the Jordan-Aqaba Trough, the long narrow basin of the Red Sea, and the chain of down-faulted valleys which in Africa extends from the Strait of Bab el-Mandeb as far south as Lake Nyassa, valleys which contain more than 30 lakes, belong to a single system of dislocation. Should you expect the lateral valleys of a rift valley at the time of its formation to enter it as hanging valleys or at a common level? Block mountains. Dislocations take place on so grand a scale that by the upheaval of blocks of the earth's crust or the downfaulting of the blocks about one which is relatively stationary, mountains known as block mountains are produced. A tilted crust block may present a steep slope on the side upheaved and a more gentle descent on the side depressed. The Basin Ranges. The plateaus of the United States, bounded by the Rocky Mountains on the east, and on the west by the ranges which front the Pacific, have been profoundly fractured and faulted. The system of great fissures by which they are broken extends north and south, and the long, narrow, tilted crust blocks intercepted between the fissures give rise to the numerous north-south ranges of the region. Some of the tilted blocks, as those of southern Oregon, are as yet but moderately carved by erosion, and shallow lakes lie on the waste that has been washed into the depressions between them. We may therefore conclude that their displacement is somewhat recent. Others, as those of Nevada, are so old that they have been deeply dissected. Their original form has been destroyed by erosion, and the intermontane depressions are occupied by wide plains of waste. Dislocations and river valleys. Before geologists had proved that rivers can by their own unaided efforts cut deep canyons, it was common to consider any narrow gorge as a gaping fissure of the crust. This crude view has long since been set aside. A map of the plateaus of northern Arizona shows how independent of the immense faults of the region is the course of the Colorado River. In the Alps, the tunnels on the St. Gothard Railway pass 6 times beneath the gorge of the Reuss, but at no point do the rocks show the slightest trace of a fault. Rate of dislocation. So far as human experience goes, the earth movements which we have just studied, some of which have produced deep-sunk valleys and lofty mountain ranges, and faults whose throw is to be measured in thousands of feet, are slow and gradual. They are not to be accomplished by a single paroxysmal effort, but by slow creep and a series of slight slips continued for vast lengths of time. In the Aspen mining district in Colorado, faulting is now going on at a comparatively rapid rate. Although no sudden slips take place, the creep of the rock along certain planes of faulting gradually bends out of shape the square-set timbers in horizontal drifts and has closed some vertical shafts by shifting the upper portion across the lower. Along one of the faults of this region it is estimated that there has been a movement of at least 400 feet since the glacial epoch. More conspicuous are the instances of active faulting by means of sudden slips. In 1891 there occurred along an old fault plane in Japan a slip which produced an earth rent traced for 50 miles. Figure 192. The country on one side was depressed in places 20 feet below that on the other, and also shifted as much as 13 feet horizontally in the direction of the fault line. In 1872, a slip occurred for 40 miles on the great line of dislocation which runs along the eastern base of the Sierra Nevada mountains. In the Owens Valley, California, the throw amounted to 25 feet in places, with a horizontal movement along the fault line of as much as 18 feet. Both this slip and that in Japan just mentioned caused severe earthquakes. For the sake of clearness, we have described oscillations, foldings, and fractures of the crust as separate processes, each giving rise to its own peculiar surface features. But in nature, earth movements are by no means so simple. They are often implicated with one another. Folds pass into faults. In a deformed region, certain rocks have bent, while others under the same strain, but under different conditions of plasticity and load, have broken. Folded mountains have been worn to their roots, and the peneplains to which they have been denuded have been upwarped to mountain height and afterwards dissected, as in the case of the Allegheny ridges, the southern Carpathians, and other ranges. Or, as in the case of the Sierra Nevada mountains, have been broken and uplifted as mountains of fracture. Draw the following diagrams, being careful to show the direction in which the faulted blocks have moved by the position of the two parts of some well-defined layer of limestone, sandstone, or shale which occurs on each side of the fault plane, as in Figure 184. 1. A normal fault with a height of 15 degrees, the original fault scarp remaining. 2. A normal fault with a height of 50 degrees, the original fault scarp worn away, showing cliffs caused by harder strata on the downthrow side. 3. A thrust fault with a height of 30 degrees, showing cliffs due to harder strata outcropping on the downthrow. 4. A thrust fault with a height of 80 degrees, with surface base leveled. 5. In a region of normal faults, a coal mine is being worked along the seam of coal AB, Figure 193. At B it is found broken by a fault F, which heads toward A. To find the seam again, should you advise tunneling up or down from B? 6. In a vertical shaft of a coal mine, the same bed of coal is pierced twice at different levels because of a fault. Draw a diagram to show whether the fault is normal or a thrust. 7. Copy the diagram in Figure 194, showing how the two ridges may be accounted for by a single resistant stratum dislocated by a fault. Is the fault a strike fault, that is, one running parallel with the strike of the strata, or a dip fault, one running parallel with the direction of the dip? 8. Draw a diagram of the block in Figure 195 as it would appear if dislocated along the plane EFG by a normal fault whose throw equals 1/4 the height of the block. Is the fault a strike or a dip fault? Draw a second diagram showing the same block after denudation has worn it down below the center of the upthrown side. Note that the outcrop of the coal seam is now deceptively repeated. This exercise may be done in blocks of wood instead of drawings. 9. Draw diagrams showing by dotted lines the conditions both of A and of B, Figure 196, after deformation had given the strata their present attitude. 10. What is the attitude of the strata of this earth block, Figure 197? What has taken place along the plane BEF? When did the dislocation occur compared with the folding of the strata? With the erosion of the valleys on the right-hand side of the mountain? With the deposition of the sediments? Do you find any remnants of the original surface BAF produced by the dislocation? From the left-hand side of the mountain, infer what was the relief of the region before the dislocation. Give the complete history recorded in the diagram from the deposition of the strata to the present. 11. Which is the older fault, in Figure 198, or when did the lava flow occur? How long a time elapsed between the formation of the two faults, as measured in the work done in the interval? How long a time since the formation of the later fault? 12. Measure by the scale the thickness lie of the coal-bearing strata outcropping from A to B in Figure 199. On any convenient scale, draw a similar section of strata with a dip of 30 degrees outcropping along a horizontal line normal to the strike 1,000 feet in length, and measure the thickness of the strata by the scale employed. The thickness may also be calculated by trigonometry. Unconformity. Strata deposited one upon another in an unbroken succession are said to be conformable, but the continuous deposition of strata is often interrupted by movements of the earth's crust. Old sea floors are lifted to form land and are again depressed beneath the sea to receive a cover of sediments only after an interval during which they were carved by subaerial erosion. An erosion surface which thus parts older from younger strata is known as an unconformity, and the strata above it are said to be unconformable with the rocks below, or to rest unconformably upon them. An unconformity thus records movements of the crust and a consequent break in the deposition of the strata. It denotes a period of land erosion of greater or less length, which may sometimes be roughly measured by the stage in the erosion cycle which the land surface has attained before its burial. Unconformable strata may be parallel, as in Figure 200, where the record includes the deposition of strata, their emergence, the erosion of the land surface, a submergence and the deposit of the strata, and lastly, emergence and the erosion of the present surface. Often the earth movements to which the uplift or depression was due involve tilting or folding of the earlier strata, so that the strata are now non-parallel as well as unconformable. In Figure 201, for example, the record includes deposition, uplift, and tilting of A, erosion, depression, the deposit of B, and finally the uplift which has brought the rocks to open air and permitted the dissection by which the unconformity is revealed. From this section infer that during early Silurian times the area was sea, and thick sea muds were laid upon it. These were later altered to hard slates by pressure and upfolded into mountains. During the later Silurian and the Devonian, the area was land and suffered vast denudation. In the Carboniferous period, it was lowered beneath the sea and received a cover of limestone. The Age of Mountains. It is largely by means of unconformities that we read the history of mountain making and other deformations and movements of the crust. In Figure 203, for example, the deformation which upfolded the range of mountains took place after the deposit of the series of strata A, of which the mountains are composed, and before the deposit of the stratified rocks, which rest unconformably on A and have not shared their uplift. Most great mountain ranges, like the Sierra Nevada and the Alps, mark lines of weakness along which the earth's crust has yielded again and again during the long ages of geological time. The strata deposited at various times about their flanks have been infolded by later crumplings with the original mountain mass, and have been repeatedly crushed, inverted, faulted, intruded with igneous rocks, and denuded. The structure of great mountain ranges thus becomes exceedingly complex and difficult to read. A comparatively simple case of repeated uplift is shown in Figure 204. In the section of a portion of the Alps shown in Figure 179, a far more complicated history may be deciphered. Unconformities in the Colorado Canyon, Arizona. How geological history may be read in unconformities is further illustrated in Figures 207 and 208. The dark crystalline rocks A at the bottom of the canyon are among the most ancient known, and are overlain unconformably by a mass of tilted, coarse marine sandstones B, whose total thickness is not seen in the diagram and measures 12,000 feet perpendicularly to the dip. Both A and B rise to a common level NN, and upon them rests the horizontal sea-laid strata C, in which the upper portion of the canyon has been cut. Note that the crystalline rocks A have been crumpled and crushed. Comparing their structure with that of folded mountains, what do you infer as to their relief after their deformation? To which surface were they first worn down, MM' or NM? Describe and account for the surface MM'. How does it differ from the surface of the crystalline rocks seen in the Torridonian Mountains, and why? This surface MM' is one of the oldest land surfaces of which any vestige remains. It is a bit of fossil geography buried from view since the earliest geological ages and recently brought to light by the erosion of the canyon. How did the surface MM' come to receive its cover of sandstones B? From the thickness and coarseness of these sediments, draw inferences as to the land mass from which they were derived. Was it rising or subsiding, high or low? Were its streams slow or swift? Was the amount of erosion small or great? Note the strong dip of these sandstones B. Was the surface MM' tilted as now when the sandstones were deposited upon it? When was it tilted? Draw a diagram showing the attitude of the rocks after this tilting occurred, and their height relative to sea level. The surface NN' is remarkably even, although diversified by some low hills which rise into the bedded rocks of C, and it may be traced for long distances up and down the canyon. Were the layers of B and the surface MM' always thus cut short by NN' as now? What has made the surface NN' so even? How does it come to cross the hard crystalline rocks A and the weaker sandstones B at the same impartial level? How did the sediments of C come to be laid upon it? Give now the entire history recorded in the section, and in addition that involved in the production of the platform P, shown in Figure 130, and that of the cutting of the canyon. How does the time involved in the cutting of the canyon compare with that required for the production of the surfaces MM', NN', and P? End of Chapter 9. End of Section 15.